Bon dia a tothom, benvinguts a aquest 5è Deep Learning Symposium, que estem molt contents d'acollir aquí a la UOC, aquest esdeveniment que es coorganitza entre diferents universitats i institucions catalanes, la Universitat, la UPC, la Universitat de Barcelona, la Universitat Pompeu Fabra, Dolby, Telefònica, el CVC de la Universitat Autònoma i nosaltres UOC, que us acollim i que estem molt contents d'obrir les portes a tots vosaltres per tractar aquests temes de recerca, però també amb un impacte social i un impacte molt rellevant en el nostre esdevenir, el nostre esdevenir com a societat. Crec que avui serà un esdeveniment per compartir, per intercanviar coneixement, per donar a conèixer des d'una perspectiva molt tecnològica el que s'està fent, però m'agradaria deixar darrere fons, i la UOC com a universitat també de ciències socials, deixar de fons tot el valor que té la intel·ligència artificial en favor de la societat. Per tant, us deixo amb aquest esdeveniment, espero que ho gaudiu, espero que sigui enriquidor per tothom i, com sabeu, la UOC serà també la universitat que us obrirà les portes si voleu tornar un altre any. Endavant i gràcies.
Bon dia, benvinguts. Welcome everybody. If I can change the slides, please. My name is Dimos. They asked me to give you a very short introduction about a new development that happened over the last few months in Barcelona. So welcome first of all to Deep Learning Barcelona 2023. I'd like to take 5 minutes to speak a little bit about ELIS, which is the European Laboratory for Learning and Intelligent Systems, and the new ELIS unit that we set up in Barcelona last April. I will not take a lot of time to explain everything, but I think it's interesting to have a bit of context about what's happening in Europe in artificial intelligence. So there has been a lot of things happening over the last 5-6 years. Europe is trying to define its own way of doing artificial intelligence, which is not driven by the interests of the private sector or by the government, like in the States and China, but it's actually focused on the interests of the people. And it has been a lot of time that we're discussing about how this should happen. And back in 2020, there was a white paper that kind of is behind all the developments that are happening in Europe up to now, that define basically 2 main areas of action. One is what they say, building this ecosystem of trust that has to do with regulation. I guess everybody's following what's happening with AI Act at the European level. It passed through Parliament and the Council a couple of days ago. And on the other hand, they are speaking about the ecosystem of excellence. Everybody's aware that we have excellent research happening in artificial intelligence in Europe, but it's fragmented, and we need to do something basically to just pull resources together and make sure that Europe is a good place to work, right? We produce a lot of excellent researchers, but talent is rarely staying in Europe, and we have to kind of reverse this kind of trend. So in parallel, a parallel story is the story of ELIS that starts back in 2018 with more or less the same realizations, where that's a kind of a bottom-up initiative, where the leading researchers of machine learning in Europe, they wrote an open letter to highlight basically a number of things, some of which are, first of all, there's a lot of things happening in artificial intelligence, but at the center of everything, of this new revolution is machine learning, so we should rather focus on machine learning as the core thing that we should be promoting. We have a lot of excellence in Europe, but we're not keeping up. We have to make Europe interesting for artificial intelligence research and researchers. And also, 5 years ago, they were discussing about the closing gap between industry research and academic research, and the fact that every time more basic research happen in industry with different kind of resources and possibilities. So 5 years ago in Eurips, December, so it's kind of a birthday this month. A number of leading researchers from Europe defined and established the ELI Society. If you are working in machine learning, deep learning, I guess that you can name many people in this photo. So that started back in 2018, and ELIS is trying to promote a number of different things through a number of different actions. I'm not going to speak about everything, but I'd like to highlight 3 things which I think are important. The first thing is research programs. I spoke before about the fragmentation of research in Europe. One of the things that ELIS is trying to do, copying more or less the Canadian system of fellowships and fellow programs, is to establish ELIS fellows and then organize them in topics, therefore create the space basically to define the research agendas in different topics in Europe. This works very well. There are 16 different programs already running. More than 300 fellows are involved in these programs, and I think it's a pretty interesting thing to keep an eye on. The second thing, which I think it's extremely important, is the ELIS PhD program. That is a meta program in a sense, right? So instead of every single one of us publishing one or two PhD positions, the idea is that there is a single European call for PhDs where we aggregate basically all the positions that are related with ELIS members and fellows in Europe, with certain guarantees and with the backing of ELIS and extra mobility support and extra actions for these ELIS PhD students. This is interesting because, first of all, as a marketing exercise, because Europe kind of appears as a single place where to do a PhD in guaranteed excellence conditions. It has run already a couple of times. We are currently processing the 3rd round of applications, and it's a very selective program, right? So we usually receive more than 1,500 applications, and we accept about 100, right? So it's a pretty good thing to look into. And the last thing is the idea of ELIS sites around Europe. So if you remember in the second slide, the European Commission is looking to establish what they call the European lighthouse of artificial intelligence. Nobody knows exactly what the format of this lighthouse should be, but the opinion of ELIS is that this should be basically the same format like the EMBL, like a distributed, a group of laboratories distributed in different countries in Europe. And in this sense, they are interested in identifying sites in Europe where there is a critical mass of excellent artificial intelligence research happening. And these are the ELIS units, and hopefully some of them will grow up to become ELIS institutes and will form this distributed European lighthouse on artificial intelligence. So what happened last year is that we managed to pull efforts together and put a dot in Barcelona in this map. So we have a new ELIS unit established in Barcelona. We started with few researchers, but top researchers in their fields, and this is expected to expand to more people over the years. But the focus, of course, at the very beginning has been excellence, 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 and we have to kind of keep up with this promise. And this is a new development, so there is little to say, but in terms of the Catalan artificial intelligence strategy, just to mention that this is under the Artificial Intelligence Research Alliance, which is supported by the Generalitat. So we have also the backing of the Generalitat in this endeavor. What will be happening over the next years? Well, a number of things, but you should expect basically to see ELIS supporting a number of different events, like, for example, the Deep Learning Barcelona today. We should eventually establish support for mobility for researchers within ELIS. There's going to be a new cycle of seminars that we will be announcing probably next year. There's going to be an inauguration event next year, so watch this space. And of course, eventually we would like to be able to support ELIS PhDs directly through the unit. So if you're interested in this, depends on where you find yourselves. you can do a number of different things. If you are master students looking for a PhD, the Ellis PhD program is a pretty good thing to look into. If you're an existing PhD student, you can still become an Ellis PhD. Check the conditions and move it forward if you think that you could apply. If you are a researcher doing artificial intelligence, deep learning, machine learning, consider applying for an Ellis membership. It's pretty easy, right? If you have a continuous publishing activity in top venues in machine learning, and if you're a permanent Ellis member researcher in Barcelona and you'd like to join the unit, let us know. I think that we know more or less everybody, but if we missed anybody, let us know. And for more information, have a look at the website or send us an email. And I think that's all from my side. If there are any questions, I'll be here in the coffee break. Enjoy the day today. Welcome. Have a nice day.
Hello, everyone. My name is Christian Canton. I'm coming from Meta, and I'm going to be starting the day introducing the first speaker. But before that, I just wanted also to give a warm welcome to everyone. This is the 5th year that we do this, and for some of us, I've been attending every year religiously. This is a huge pleasure to see how, the amount of folks coming to this venue keeps growing, and it's very encouraging to see you on this very probably last day or one of the last days of the academic year coming here. One thing that I wanted, a couple of small remarks. I think it's very important to stress on the community kind of work that we are doing here. We're getting together. It's great to see that there's a young generation, a not so young generation that is getting together. It's important to keep fostering this sense of community, because I'm going to be talking from the Meta side. Out of these events, at least I recruited 3 people that are now in my organization that came out of this event. So this is an opportunity for all of you, also to broadcast the good work that you're doing, and also find for opportunities, and vice versa, for each other to learn from the work of each other. We mentioned on the quality of the work that is happening here and the work that is happening outside. So it's very important to see that we're a very mobile kind of community. We have a bunch of our speakers today are not physically working here, but hey, are coming every year and they're going to be talking to you. Likewise, some of you hey, stay here full year. It's important to see that, hey, we move around. I wanted to put my case. I've been many years in the US and I just came back. And there's a boomerang trajectory that many of us are in different stages. I really hope that some of our speakers one day will come back to Catalonia. So again, I wanted to stress how important it is that, hey, we are around, we are a community, and this is one of those events that allow us to learn about what each other is doing, and also to create opportunities for each other to learn and grow as a group of folks. Without further dilation, I'm so honored to be introducing my good friend, Fernando de la Torre. Fernando has been in the community of computer vision for a long time. He originally came from the La Salle, where he did his master's and his PhD. Then he moved to the US, where he's a professor at CMU, and he's managing a very successful team doing computer vision there, the Institute of Robotics. You'll probably tell more about this. We got to know each other at Meta, where we worked together for 4 years, and it was a pleasure to learn from him. So I invite him to join me here, and please show and walk us through all this wealth of knowledge that you have accumulated over the years. A big applause for Fernando.
Sí, tinc passat, però no està projectant. L'altre. Perfecte. Bon dia a tothom. Thanks very much for the kind introduction, Christian, and thank you to the organizing committee to give me the opportunity to give a talk in front of this very distinguished audience. It's great to see how much talent is coming out of Barcelona now. And let me start today. The agenda for today is going to be something like that. I'm going to talk a little bit about the work that we do in the Human Sensing Lab. In the Human Sensing Lab, we try to understand human behavior from sensors, and we apply in two different areas, in the area of medical diagnosis and monitoring, and in the area of augmented reality and virtual reality. Many of the algorithms that we develop here are learning-based algorithms. And when you have a learning-based algorithm, like in deep learning, the most critical part usually is the data. But nobody wants to work on data. Data is not sexy, doesn't bring you glory. It's the most critical part, but people don't want to work on it. So in the second part of the talk, I'm going to talk about some techniques that we are developing to make it fun to work with data. We are going to develop algorithms to create better data sets. We are going to develop algorithms to evaluate better computer vision algorithms without test sets. We are going to develop algorithms to debiasing computer vision algorithms. So let me start from the Human Sensing Lab. In the Human Sensing Lab, I started about 15 years ago. It was mostly inspired by the work on Joe Goldman. Joe Goldman is a professor in the University of Washington, and since the 80s, he has invited more than 3,000 couples to his lab. And his lab is called the Love Lab. He invites the couples to the lab and asks the couple to start a topic about an ongoing disagreement between the couple. One likes the dog, the other doesn't like the dog. He records this interaction, this conflict resolution, for 45 minutes, and after 45 minutes, he's able to predict with 85 or 90% of accuracy if this couple is going to get divorced or not in 15 years from now. And you wonder, how does John Goldman do that? He goes through the video and encodes every conceivable emotion that the couple shows with what is called a specific affect coding. This specific affect coding has 5 positive emotions: joy, validation, humor, and 15 negative emotions: criticism, stonewalling, contempt. He encodes all these and then does the regression to this label if the couple is going to get divorced or not from 15 years from now. But to do something like that, you need the expertise of John Gottman and very tedious amount of work of labeling. So my big dream has been always to try to recover this subtle behavior directly from data. I want the machine learning to do the work. And by the way, the outcome of this study, if you want to keep your partner, 2 things you have to do. You have to show in your relation 5 times more positive emotion than negative emotion, and never show contempt to your partner. Along these lines, we did some work a few years ago in the area of depression. Imagine if I'm depressed, I'm going to win an interview with a clinician, and the clinician has a structured interview, a structured question. They ask me, how did you sleep today? Did you have suicidal thoughts? At the end of these questions, it ranks my depressed state. With one of the gold standards is Hamilton score. 0, you are not depressed. 100, you are very depressed. But this depends on what you tell to the clinician and the expertise of the clinician, not on how you behave. So we wanted to provide a behavioral measure of depression. In collaboration with UPMC, we did a large data collection between the clinicians and the patients. And we record the face of the clinician, the body of the patient, and the face of the patient, and also the audio. And from the audiovisual information, we were able to predict with around 70% of accuracy, better than chance, if you are depressed or not. And you wonder, how can you know? So in the visual aspect, if somebody is depressed, for instance, they tend to have more gaze aversion. They don't look at your eyes, or when they smile, it's not an honest smile, it's damp the smile. When you have an honest smile, you smile with the eyes. And we were able to recover these kind of features with systems like that. This is a system that we have. It's a real-time system for facial expression recognition. Now, how do we encode emotion? A very common way is doing the facial action coding system. It's an atomic-based system that basically says that any facial expression can be represented as a combination of 44 action units. Every action unit is related to one or more facial muscles, like action unit 2 is outer brow raiser, or action unit 23 is lip tightener here. So we have this system in real time, and the challenge is here you can track the 2D points, but then you need to decouple what is the rigid and non-rigid motion. The rigid motion is the rigid movement of my face, and non-rigid is the expression. And in many of these problems that I'm going to show in human sensing here, the key problem is to recover the subtle behavior. In this case, we can have more motion of the head that the small action unit 14 or small gesture or micro gesture that we can do. And the trick is, well, how do you recover and how you decouple these things and you can recover. In this case, Takeo is smiling and you see Action Unit 12 is smiling invariably to the face. Other projects that we work also is in Parkinson monitors. More than 1 million Americans, mostly over 35, they suffer from Parkinson's. The Parkinson, you cannot treat Parkinson, but you can manage symptoms. And typically now these patients, they go every 3 to 6 weeks, they go to the clinician, and they have to self-report the behavior that they have, how many tremors they have, and also they have go through a motor control. But this has several problems. First, it's inconvenient to go every 3-6 months. Self-report measures are not very reliable. I don't know if you have seen, Dr. House, everybody lies, and it's true, And the third thing is the motor control depends highly, this test depends highly on when you took the medication and the specific time of the day. So what we wanted to do is we want to monitor continuously the tremors. And then what we have here is we have inertial measurement units that we put in the wrist. But then the challenge is we have signals like this. And we give them an app and we say, when you have tremor, click that you have tremor, and when you stop having tremor, just click that you don't have tremors. So we can learn person-specific models of tremor. But the labeling is very hard. Labeling human behavior is very hard. In these cases, for instance, the patient started in this location that they have tremor, and in this location you don't have tremor. And then in between here, they didn't have any tremor. But then we had to develop algorithms that they rely on what is called multiple instance learning to automatically label what is tremor and what is not. These are some of the challenges. Other problem we are very interested is in monitoring elderly patients. For instance, I live overseas, I have my parents at home, they are getting elderly. I would like to have a system that can monitor their well-being. And you can think, well, you are a computer vision researcher, why don't you put cameras? Well, nobody wants to have cameras. There are places like in the restrooms that you definitely should not have cameras for privacy issues. And not necessarily it's very robust to light enough focus. We could have other sensors like LIDAR or radars, but these are expensive and narrow field of view. So one idea that we start working is, what if we use the Wi-Fi signal, which is ubiquitous? The Wi-Fi signal that we have around here, you think is a signal for transmitting communication or information, but can it be used to detect humans? And that's what we did recently. What you see here is how we detect dense pulse only from Wi-Fi signal. This is only from the Wi-Fi signal that we have. It's with a regular router that you might have at home. In this case, what we got is we got a router, the router that you have at home, but we have a specific scenario where we have 3 antennas for emitters and 3 antennas of receivers. So we have kind of 2 routers. And then to model the Wi-Fi signal model mathematically is extremely hard. It depends on temperature, humidity, tons of multipath reflections that are going to go around there. So what we are going to do is what everybody does now, which is learning this from data. And in these 2 scenarios, what we are going to have is we are going to have a camera that is going to give us the ground truth. We collect the Wi-Fi signal, we collect the camera, and we are going to pose this as a supervised learning problem. We are going to have people walking around and see if this can generalize well. And this is the kind of network that we have. We have 3 emitters, 3 receivers. This is channel state information. We have 30 bands, and this factor 5 is because the video goes at 20 frames per second, and the Wi-Fi signal we sample 100. But basically what we want is we have the phase, we have the amplitude. We transform this phase in amplitude in an image-like structure, which is this one. And then we want to apply traditional computer vision algorithms for detection. This is the faster RCN. And what we are asking the algorithm is, hey, just from the reflections of the phase and the amplitude, can you, which is almost noise, it's noise what we have, can you extract this part of the noise that is relevant, to detect dense pulse in people? So that's how we learn this network in a supervised fashion. Now, in this case, we collected data in 16 different layouts, 6 in the office and 10 in different classrooms, and the results look good. So the good news is this system generalizes pretty well to different activity, different people, different clothing. That generalize well. What it does not generalize well is when you change the position of the emitter and the receiver, okay? Which was expected. There are some false positives, but the interesting thing is that, that there is information in the Wi-Fi signal to detect people. Now, we work a little bit also in the area of augmented reality and virtual reality. This work that I did when I was in Meta, and now Carlos, I saw around here, is continuing a little bit this work. So during my lifetime, we've seen 3 paradigm shifts in the area of human computer. In the 80s, we had the introduction of personal computers. In the 90s, we have the connectivity of these computers with the World Wide Web and the cloud. And in 2007, we had the introduction of the iPhone that allows computing from everyone to everyone. Right? And now we are in the verge of the 4th the 4th paradigm shift in the area of human computing, which is going to come likely from the area from the augmented reality and virtual reality. We are going, with augmented reality, these glasses that many of you have tried, we are going to be able to mix the digital world and the real world in real time, or we can have a much more immersive experience with virtual reality. And one application that I'm particularly excited about is how we are going to communicate in the future. If I would have given this talk a couple of years ago, probably would have given through Zoom, and I cannot see your faces. I cannot see if you are interested in the slides. I cannot see if you laugh at my jokes. It's very impersonal. Now it's much more fun, to see everybody here. But the Zoom, especially when you have many people in the meeting, you see little screens. It's very hard to get a sense of embodiment. So virtual reality, what can allow us is to have a much more immersive experience for communication at a distance. And one of the software or hardware that we are going to use is having this kind of virtual reality headset that has 3 cameras. From this camera, one camera pointing towards one eye, the other camera on the other eye, and this camera on the mouth. And then what we have to do is do facial expression transfer. From these cameras, we have to transfer the facial behavior, the subtle facial behavior, from the user to an avatar that looks like you and behaves like you. And this is a video.
There's a nice contrast.
Yeah. Okay.
Yeah.
What kind of yoga do you do?
I do hot yoga. I love
knew
hot
it.
yoga.
Oh my gosh. I've tried it a few times. Hot yoga, I just want to, oh my gosh. I sweat so much. I melt in there.
Yeah, I love it.
But like this session.
Now, how do we do that? This work, in principle, was done by collecting a lot of data in these capture studios. One is what is called MUXI. This is in the Meta Reality Labs in Pittsburgh. And there is the MAXI to capture the face. It has like 160 cameras, 450 lights, and 120 microphones. And to capture the body, we have this Sociopticon with 250 cameras. And Carlos can tell you all about it. No, I don't want that. He's the one suffering now some of this data capture. And this is how the data looks like. We are going to collect data, this multi-view data. These are with 50 millimeters cameras, and you can see the details that we can extract of the user. Now, you have to understand for this kind of applications, the bar is very hard. We have to do better than Zoom. So that's not an easy thing to do. So once we have these models, the first thing that we capture this data, we want to build models of you. So the first thing is we do photometric stereo for 3D reconstruction, then we do key points, and then we have a mesh. We fit a mesh in these 2D key points in 3D to make sure that this mesh is common across all people. We need to solve somehow the correspondence in 3D across people. Then there is these key points are generic, are not personalized. We personalize to every subject, so to get this subpixel accuracy, and we do the model fitting. Now, Once we have kind of normalized geometrically the data, then we need to build a model, and you can choose the encoder, autoencoder that you want. In this case, we choose a variation autoencoder. The input is the mesh and the texture, and then we are going to have a variation autoencoder that has two variables, one that encodes the expression, which is this yellow line here, and the other, the viewpoint. So we have a generative model that we change the expression, and another variable, change the viewpoint, and you change the 3D rotation of the morphable model. Or in this case, the variation autoencoder model. And then it has the encoder, and this part is going to be the decoder. The decoder can represent you and the any expression and any pose. And then it has this latent space, which is just the expression, and this the viewpoint. Now, but what is the problem here? As many cases in computer vision, the problem is the correspondence. Solve me the correspondence problem, and I will solve most computer vision problems. And the problem is I need to transfer from these local viewpoints, from these two cameras and the mouse, to the avatar that looks like me and behaves like me. Now, when I have the VR headset, I don't know the ground truth. I mean, what is my ground truth? Because I have the headset, I don't know how I look like in 3D. So that's the problem. We need to transfer, because if I have this correspondence, then I can learn a regressor, and it's a supervised learning problem. Now, what my colleagues did is a self-supervised method to learn that. So what we are going to have is, I'm going to have this decoder. This decoder is not. This decoder here is not. Now, and this video input also is not. So what I'm going to want to do is, given this video and given this encoder, I need to learn the parameters of an encoder such that when I decode these three avatars and project in the viewpoint of the VR headset, I can reconstruct the scene. That's what I want to do. I want to learn this encoder. I want to learn this encoder such that it gives me, the expression and the viewpoint such that when I project this avatar that I can reconstruct in the VR headset viewpoint, I can reconstruct this data. Now, when I project the avatar, I have RGB images, so I need here to have an adaptation network from RGB to VR. But that's the self-supervised version to solve for correspondence between local infrared images and my VR headset. And this is how it looks like. When you can see how you can superimpose the mesh and superimpose the texture, and you can solve the correspondence between these two very different domains. Now, the problem is this is good for person-specific models, but it has many issues. When you have these person-specific models, they are not robust to the variability that you are going to see in the data. People might have changes in facial hair, there can be different lighting, there can be makeup. So I need to add robustness to a system, and you cannot ask the user to collect the data in all these possible situations. So what we need to do is to have general models that I can put my headset and I can transfer this expression. And this is what we did. Now, for every subject, for many subjects, what we are going to have is the correspondence between these infrared images and my avatar. And now what I want to do is to build a generic model, a model that I'm going to learn across many users. And what I'm going to do is I'm going to learn this backbone here, this B. For many different users, I want to learn a backbone that marginalizes everything that is not expression. I'm going to marginalize lighting, appearance, everything. This backbone has to collect only features that are related to expression, and I'm trying to reconstruct each avatar. This is for each of the different people. That's how we build kind of generic models. And these are the results that we got, which are kind of interesting, because what we can see here is this generic backbone really has marginalize everything that is not expression, and I can align people across expression. And this is interesting because many of these people never have done these expressions, but I'm able to derive from the VR headset of one person very subtle expressions of other people. I have solved the correspondence across expression. Yeah, so that's it. And this is just an example of, for instance, for an untrained person, how it looks like.
All right, so tell me, do you do any hobbies in your free time? What do you like to do in your free time?
You can see
I like to mix music. So last night, for example.
Yeah. And the challenge here is basically how can you achieve this with, with transferring this really subtle facial expression. Now, while I was at Meta too, I was developing the technology for real-time augmented reality, mobile phone. We developed all the fancy applications for face mask or background blurring. And it was the time of COVID too, and then we developed all the application for online e-commerce, things like virtual try-ons for glasses, makeup, and or nail coloring was very popular because people did not want to go to the retail stores to do that. No? Now, it's very different to publish a paper than building a product, very, very different. The two things that are very important when you build a product is robustness and speed. So we had 3 billion users. 40% of the human population had these algorithms. Many of you have these algorithms. If you have Instagram or Messenger, you have it in your pocket. So the test set is 3 billion people. But you usually train from several 100,000 images. So that's, how can you guarantee robustness things or guarantee anything there? And the other thing, it has to work in many different platforms. It has to work on the latest iPhone, which is relatively easy, but has to work also on things like Motorola second generation Android phone from 2013. You might wonder why I remember this, because I suffered a lot to make these algorithms work in real time in CPU. Because India is one of the largest emerging markets for Meta, and it's important that all these applications work there in real time. So these two are things important, but there are three things that are even more important than that, which is data, data, and data. And in all the applications that I mentioned before, data is always the bottleneck. Data is always the thing, that gives me the major headache. When I was talking about the project of the operational Wi-Fi, I spent much more time collecting the data than doing algorithms, by far. When it's not only collecting data, it's to label data. Labeling human behavior is extremely difficult. In assessing depression levels, you give these interviews to different clinicians. There's not going to be necessarily much consistency between them. It's very hard to label behavior. Or when I was telling you about the Parkinson, how do you determine when the tremors start and end? How do you label this, especially with data in the wall? Extremely hard. So we need techniques not only to help us to collect better data, but also to label things more accurately, which for humans is extremely hard. And humans do not have the consistency that the algorithm is going to find later. No? Other things, how to represent a representative test set, super hard. The thing I was mentioning before. No? I developed these algorithms for mobile phone. There are 3 billion users, 40% of the human population. I learned from 100 to 100,000 samples. Which samples should I choose that are representative, for these 3 billion people that can take the mobile phone indoors, outdoors, with different lighting conditions during the day, night, different facial appearance? Very hard to do. The other thing, one of my worst nightmares is what happens if these algorithms that I develop don't work well for a subpopulation. I'm in trouble. How can I guarantee? There is no way to guarantee. It's very hard to guarantee things. In software, you have things like formal verification methods, but with data, you have the train set, you have the test set, you build this the best to your knowledge and pray that this is going to work well, but there is no guarantees. The other thing is, how do we evaluate computer vision algorithms? I want to know where my things fail. This is good. And in general, I have many times people, well, I wanted to be a machine learning researcher. Okay, let's spend 3 months with data. No, I want to be a machine learning researcher. Well, that's what it is. Spend the time with data. It's not doing the algorithm. It's 70% of the effort is on the data, labeling the data, cleaning the data, making sure the data is well curated. But it's work that, as I was saying before, it's not sexy. There are always better things to do than work with the data. In fact, when I have a student, I don't know if I want to work with him, I say, let's do a data collection. I never see the student again. So it's necessary, it's the most critical part, but still is not there. In fact, I don't know if you see the TV show Silicon Valley, highly recommended for anybody that wants to be an entrepreneur, very funny and very real. But he's Yu Yan, he's a research engineer, and he's trying to build a food detector. And he's showing this to the venture capitalists, and he showed that he can recognize a hot dog. So everybody is super excited. And then points to a pizza, and it says no hot dog. And let's look at the, at the reaction of the venture capitalists. And this simplifies a little bit the state of the art in data collection in academia and industry. Let me play.
Hold on, Xinjiang's actually put together a pretty good classifier. I mean, the core tech is valid. It just needs to be trained.
So what he did for hot dogs, he needs to repeat for every food in existence.
No, that's a very boring work. It's a scraping the internet for thousands of food pictures. You can hire someone else. We can't.
Well, that's what happened. So let me show you now some techniques to make it fun, actually, to work with data. First one is the zero-shot model diagnosis. The problem is how we evaluate the performance of computer vision algorithms. Well, what we need to have is a test set, collect data. However, test sets have 2 problems, at least. There is no guarantee of robustness and fairness. Like the problem I was saying before, I have 4 billion people, I train for several thousand images. I mean, how do I guarantee that my test set, that's several thousand images, is going to be representative of my real test distribution? I don't know. And the second thing is, even how do I collect a balanced test set? Imagine in the face, many of the things I'm going to illustrate in the face, but just because it's easy to understand, but we have extended these algorithms to other domains. Imagine the face, I want a balanced test set over age, gender, ethnicity, glasses, no glasses, long hair, short hair. It's combinatorial. Good luck with that, So what I'm going to tell you is we are going to have an algorithm that is going to evaluate computer vision algorithms without test set. Remember, I don't like to collect data. I already collected data and I suffer a lot. My job for the rest of my life is not do data collection unless they are synthetic data collection. I can do that. So how can we do that? Okay, so the key is I'm not going to have a test set, but I'm going to have generative models. We are going to, in all this work, we are going to use large pre-trained models that have been trained with millions of images, which is much more than what I can access, and we are going to distill the information from these large pre-trained models for these tasks that we want to do, from the biasing to evaluating computer vision algorithms. So again, in the context of faces, so everything is easy to understand, what I'm going to have is a controllable, a conditional generative model. It's a generative model that has been trained in supervised manner, can represent faces, but I can control the axis. For instance, I have an axis that is eyeglasses, and I can edit the eyeglasses, or bangs, which is how much you cover your front, that it can be controlled. So I have a controllable generative model that has been learned in a supervised manner, and I have this axis that has been decoupled. The other component that we are going to need is adversarial attack with fellow and friends. They show that is, back in time, that it's very easy to trick a network. In this case, we have an image of a panda, we have confidence, but I can do an adversarial attack with very small noise and confuse very easily the classifier. Now, these adversarial attacks are not semantically meaningful. So here, the idea, what we are going to do is we are going to do semantic adversarial attacks. We are going to do adversarial attacks in the generative space where I understand where I can modify, the attributes. And this is the main idea. The main idea, I have an image here. Let's say we want to build an eye classifier. I have this image, the person, these two people don't have any glasses, so the eye classifiers say no glasses, but I'm going to do an attack in the generative model space of attributes. What I'm going to say is, hey, look across all these attributes that I have. How can I modify this image such that I flip the classifier? And in this case, we can see that by removing her, the algorithm has flipped the classifier. And this is because the data is biased. And this is because when we collect the training data, elderly people that have less hair is highly correlated with having glasses. So we discover some kind of the bias here. And then here is kind of a sensitivity histogram that tells me which of these attributes, are more likely to have impact, are more likely to make the classifier to flip. And this is a little bit, these semantic adversarial examples that, if you remove a little bit the hair, gets confused, or the smile too. Most of the images that young people, they tend to be smiling. But this is, Fernando, I mean, you told me you didn't like to label things, so you have to have a generative model that has been learned in a supervised manner. So you have to label. I say, okay, I told you I don't want to label. So I'm going to do this without a generative model that has been labeled. And how we do that? So we are going to do using the CLIP model, which is going to be another large pre-trained model. So what we are going to have for model diagnosis is, let's say that I have a cat-dog classifier, and then I'm going to input some attributes that I think can be relevant to this task. And from that, we are going to build these histograms of sensitivity analysis for which kind of attributes these classifiers are likely, to be more sensitive. Now, what is the CLIP model? It's a large pre-trained model, has been trained for 100 million images. It just finds a similarity metric, normalized between text and images. So you give me an image, you give me a text, and I give you a little bit the similarity here. And then what we do, because at the end of the day, we need the generative model that is the couple, we use what is called the style clip. This style clip use the CLIP model to find this direction. For instance, smiling, I have my generative model trained in a unsupervised manner, and then I put a smiling, and this style clip finds these directions that only correspond to a smiling. So that's how I can get, I can have kind of controllability or independence in this generative model. With this style clip, I have, as before, I have these directions that corresponds to each, in the generative model space, these directions that correspond to each of these attributes. And then I do the same as before. So what I'm going to have is I have my generative model, and I have these directions that I learn. I input things like, the attributes that I have of interest. I have these directions in the generative model that represents these attributes. And then what I want to do is to minimize with respect to W, tell me the combination of these attributes that are going to flip the classifier. We apply this to classifiers, to key point detection, to segmentation, any computer vision task that is end-to-end differentiable. And here, the only thing that we do is we have 3 losses. The first loss is saying, hey, I just want to make sure that you flip, that it's an adversarial example, that you flip the classifier, or in the case of key point detection, that the points are as far as possible from the original ground truth data. And then we have 2 other losses. The first one is I have the image. I don't want to change the background. I only want to change, in the case of the face, related to the face. So we have a loss, a structure similarity loss, that the adversarial example and the original image is similar. And the final one is just to avoid, if I'm doing an eyeglasses detector, I don't want the algorithm to change the eyeglasses. So, we avoid this. And we compute the sensitivity score, like the difference of the cost between the adversarial example and the original image. And this is how you get, in really unsupervised manner, the sensitivity analysis of, or in this case, classifiers. Like in the HR classifiers, we can see that the smiling is the most sensitive attribute. And this is, again, because we borrow, this has discovered the biases that we have in my training data in an unsupervised manner with the use of large pre-trained models. I'm running out of time, so I have 5 minutes. Let me tell you briefly about the other one. We have more experiments, in segmentation, key point detection. Another important one, everybody is super excited about advances on generative AI. Since OpenAI released things like DALL-E 2 and ChatGPT in 2018, we have seen a boom of this technology, but it not always works well. If I put in a stable diffusion, computer scientists attending a talk in an international conference, I see what I see here, I see here, it's not the same. There is a lack of diversity. You guys are much better dressed up, so there is a mismatch. And even if we look closely, the headshot of a computer vision scientist is highly biased toward people with gray hair in the late 50s and with glasses. So we want to remove all these biases. We want to do something like this. You are going to try, it's very hard for a generative model to be trained in a supervised manner. In a supervised manner. It's hard to put labels. So I want to train my generative model in an unsupervised manner, but then I want to correct. So I'm going to give you, this is what I want. I want, for instance, I have an attribute of interest, which is eyeglasses, and I want the headshot of a person and then put kind of eyeglasses, and I want 50% of the images come up with people with glasses and the other 50% of people without eyeglasses. That's what I would like to do. And you can do that. You can do text-based debiasing, you can write things like, woman wearing glasses, man wearing glasses. The problem is the negative. It doesn't tend to work in these text-to-image models. It's not reliable. More importantly, there are other aspects, other attributes, which are very hard to describe by text. If I, rather than ethnicity, typically represented with skin tones. If I have 7 skin tones, how I'm going to write by text? Hey, give me the 4th skin tone of races. That doesn't work. So because we are computer vision scientists, the key here is that a picture is worth 1,000 words. What we are going to do is we are going to teach these attributes with very, very few images. So the idea is I'm going to have an input prompt, like headshot of a person. I'm going to tokenize it. This is the standard thing. But then what we are going to do is I'm going to learn inclusive tokens. These tokens are going to be learned in the case of, and this just a simple example. Imagine that I want to build a generative model that is biased, and I want to debias it by gender and skin tone. And I'm going to learn 2 types of inclusive tokens. One is going to be a man, one is a woman, one is light dark, one is light skin, the other is dark skin. And what I'm going to do is I'm going to get this prompt, and I'm additively going to sum all these combinations, and each of these generative models are going to output each of these subclasses. And that's what I want. And the trick is how I'm going to learn this inclusive token such that I can additively combine them to avoid the combination of the combinatorial explosion of attributes. And the idea, and probably I have 3 minutes, Christian, or something like that? Yeah, so let me finish. The idea here is again, we are going to use a large pre-trained model because these large pre-trained models have a lot of knowledge, and especially the CLIP model. The CLIP model can translate visual difference into natural language difference. What I'm going to do is I'm going to have few images, 10, 20 of people without glasses, and 10, 20 images of people with glasses. We get the CLIP embedding. And then what I'm going to do is I'm going to learn these inclusive embeddings that are going to be completely disentangled, and that's the idea, such that this direction and this direction, the direction in the visual space and in the language space is aligned. There are many details here, but the idea is when we learn these inclusive tokens, we are able to debias these generative models much better. And not surprisingly, we do better than existing methods. This is the Kell divergence that shows, the Kell divergence between a uniform distribution, which is what I want, and what the algorithm gives. It works better, and then, the interesting thing about this method is what I mentioned before, is that it scales very nicely across attributes. In this case, we have generated a table that is uniform across 4 attributes like gender, eyeglasses, age, and smiling. And in this case, just with very few images of each of them, and we need very few images because all the knowledge is in these large pre-trained generative models, we were able to debias for these particular 4 attributes. And interesting enough, what was our surprise is these inclusive tokens was working very well for other we did not train for these other models, but still was working well. So this is the input image, and this instruct pics to pics that transfer from men to a woman. And then we input the skin tone, and we can see how we can vary the skin tone in an algorithm that is completely, or was being learned with completely different data. And these are examples of control net we can apply to other things. I skip this one because not interested. Let me finish now. I finished too fast. I just want to thank, just want to say a couple of things. Conclusions. The interesting problems in human behavior is when we represent subtle human behavior. This is the problems that have not been solved. And mostly, many of the problems have to do with data. That's where we are going to spend most of our time. At least let's have fun. Let's develop algorithms that help us, that make it fun to work with data. And I want to thank everybody. Some of this work was done at Meta, some of it work at CMU, and these are some students and collaborators, and I want to thank everybody. Now it's time to wake up now. I want to thank everybody for your attention, and I think that's it.
Thank you, Fernando. The course of gathering data.
Yes, the course of gathering data.
We are pretty much tight on time. We'll have time for one question, but then we'll have probably the coffee break that people can come. Any question? Okay.
Who likes to collect data?
Yeah, okay, Petya.
When you were showing this image where, for example, scientists were looking so awful, because you are doing unsupervised in a supervised way, you don't control it in any way. So there is always a risk that the data you generate are also artificial in some way. So how do you control this?
Yes, no, absolutely. I mean, when we learn with generative models like diffusion models, there is the hard part is there is no guarantee that the output is what you want, no? And in particular, if you look at the papers nowadays, this thing, the state of the art is solved. What happened? Everybody cherry pick results, everything looks good, and then when you try, nothing works. It's visual overfit of the results that you choose. So in the case of faces, could be relatively easy. So two possible things you can do in diffusion models. You can use kind of a GAN strategy where you use a discriminator to make sure that look like faces, or you can put just classifiers to make sure that there is a good object that you want. So I think for things like faces, it's easy to do. For generic objects, I mean, we need to do more, because even things like FID score is not representative. You can have a great FID score, but the output, might not be visually what you expect to be. So there has to be more research in coming up with metrics that the quantitative measurement of this metric is aligned with the visual human system. And there is a mismatch still there. Yeah. We need better metrics, basically. Metrics that are aligned with human knowledge.
Thank you.
Yep, thanks.
So, hi, good morning. So we're having small technical issue before starting the next session. I think we're going to fix it soon. So we'll start with a Q&A between Peter Radeva and Aleix Martinez. So please hold on to your seats. So it's not the end of the session. It's just that we are struggling to find some information. Okay, but we're going to start very soon.
Hello.
Is it working? Yeah?
Yes.
Hello, hello. We're here. We solved the problem.
Thank you for your patience. Today we have the pleasure to have here Aleix Martinez. He is a principal scientist and director of an Amazon science team in Seattle and an Amazon science team in Barcelona. He's also a professor at the Ohio State University. Prior to joining Amazon and OSU, he was affiliated with Purdue University and the Sony Computer Science Lab, and he's a recognized expert in computer vision, machine learning, cognitive science, and neuroscience. So thank you very much, Aleix, to stay here and to come and to be able to talk to you, and also to see all work that is doing in deep learning in Catalonia and from Catalonian people. We have a few questions and we are very interested in knowing your opinion. First question is, how do you see the future of computer vision, machine learning, natural language processing, deep learning in the Barcelona metro area?
All right, good question. Hello, everyone. It's good to see you here. It's good to be back. I was actually here in 2019 when you guys invited me to give a keynote talk. So really, really happy always to come back to Barcelona. What do I see the future? I think it's a bright future. I believe that there is just so much talent here because I think it goes, at least that I know of, back to the 1980s when people started working in computer vision, machine learning, NLP here. I mean, seriously building big teams. And it shows, right? When people have worked on something for long enough, it's created this center of excellence that people have recognized over the world. We just saw Fernando's talk. I think he has demonstrated over the years how good the research that's come from Barcelona and the Barcelona area is. He's been a forebear for all of you, so take advantage of that. We have had many other previous speakers here at the symposium that have demonstrated that as well. I see Antonio right here, who's going to be another chair today, who is obviously undoubtedly demonstrated all over the world the quality and the impact of people that come from here. Other people that have been speakers here before. I think there's Marta here, Oriol has also been a presenter in previous years, and so on and so forth. So I believe that there is recognition all over the world of the quality of the talent that you have here. I believe it's growing and only growing. And there is one thing that you all should know. There is a tremendous need for talent, top talent in the world in computer vision, machine learning, NLP. You might have heard in the news. And people are looking for places where they can go to grab that talent. And I believe Barcelona in particular is one of those places. I myself have created an Amazon Science team here in Barcelona, just because the talent is here, and many other companies and institutions are doing so. There are also a lot of people in the EU, very high talent in the EU, that want to move to Barcelona, and who doesn't? So obviously, there's just a tremendous future for all of you here.
Thank you very much. Fernando was speaking about data. I want to say just one curiosity about Aleix also, that many of you have been working on face recognition. So there is one very, very old data set that is called AR. A comes from Aleix. AR.
That's
and
a long time ago. Yes.
I'll
say one thing about this. I think it's important to state, because I really like what Fernando said. But I always say this: if there's something from this symposium that you should take away from this, if you want to work in machine learning, specifically machine learning, there is data without machine learning. There's no machine learning without data. Take that as a message. I slightly not disagree with Fernando, but I meant a little bit what he said. If you want to become famous, build the best data set ever. That's what made me famous at the very beginning of my career, the AR face database. Nobody cares about it now, but back in the day, I actually had to program a frame grabber. You don't even know what that is, but it's basically an analog to digital converter, because cameras were analog back then, believe it or not. And like you need to program your GPUs. Well, we need to program other things back in the day. So, the AR, obviously Antonio built a lot of data sets that became famous. You've all heard of Pascal, VOC, ImageNet, Lion of late. You want to become famous? Trust me, that's a good way.
Right. And also, this is a very excellent example that you begin from here, from Barcelona. This AR was compiled in Computer Vision Center, and then you come up in the best places. So, and best place is also Barcelona. So a very, very encouraging and exciting example. My other question is, many of our attendees are graduate or recent graduate students considering a scientific career in a tech, as we are discussing. What would be your advice for young scientists?
All right. Well, first, let me start with what's not good advice. And everything I'm going to say, obviously, is my personal view. But what's not good advice? And this is advice that you will probably get, and you have probably already received in the past. Follow your passion. Terrible advice. Usually, this advice comes from two types of people. One, people that have followed their passion. They have found they're really good at it. They've been very successful and concluded, hey, correlation means causation, so that's the advice I'm going to give. The second type is millionaires, multimillionaires. Usually they have made their money not following their passion. I don't know, maybe mining, gold or gas or who knows. And they'll say, just follow your passion. Yeah, like mining, right? So don't do that. So what should you do? Here's my recommendation. There are 3 steps. Number 1, identify what you're good at. Now, this requires trial and error. Hopefully by now you know what you're good at, but if not, trial and error. And then number 2, work really, really hard at this. Make that one thing the thing that you really work at. And if you really are worth for this, you will become one of the best people in the world at this. And believe me, when you're one of the best in the world at this, people will seek you out. They will treat you really well, and they will pay you really, really well. That will make you really happy, you'll have a sense of accomplishment, and importantly, you have plenty of money and time to devote to your passions. As a hobby, for fun, not your job. Number 3, be lucky. I'm sorry, it's true. You just have to be lucky. Sometimes, well, actually, probably most of the time, if you're not lucky, if you're not in the right place at the right time, things just don't happen. Now, if you're never anywhere, you're never going to get lucky. The more places you are, the more times that you are in those places, the higher the probability that you will be lucky. I myself, I've been very lucky in my life. I'm sure there are plenty of people out there that started at the same time I did. They're equally talented, that they work as hard as I did, and they weren't as lucky. You just have to be. So be in places a lot of the time. Now, having said that, my other piece of advice is make a plan. Now, you know that I come from Amazon. Amazon has a writing culture. It's very different from every other company. So at every other company, you do a PowerPoint presentation, like here, right? Okay, that's good. But it's very easy to hide mediocre work, within a PowerPoint. If you want to have a plan, you have to write it down. That's what we do at Amazon. We write 3 to 8 page documents for everything. Our meetings start with 15 to 30 minutes of everyone sitting around a table reading the doc. I'm not joking. And then there's a discussion on that doc. Why is that important? Because when you write this down, you really have to think about it. You have to do a deep dive, understand what you need, what you want to do, what's the problem, how am I going to solve this problem, how am I going to go from here to there. Do the same thing with your life. You only live once, believe me. Live the life you want to live. How do we do that? Write it down. Make a plan. Don't give me half a page with bullet points. Give me a 6-pager. If you need more, good. Full sentences, full paragraphs, short margins, small fonts. Write it down. Think about, what do I want to do in my life? What is my goal? Put in the must-have. What are the must-haves? What are the nice to have? What are the things I want to avoid? Do I want to get married? Do I want to have children? Do I want to travel the world? Do I want to visit every single country? Do I want to win every single award in science? Or some awards? If some awards, which ones? Put it on paper. Take time off work and do it. Don't do it at 11 p.m. at night when you're tired and saying, okay, now that my day is over, what am I going to do with the rest of my life? Think it through. Take a week, 2, 3, whatever it takes. Think it through. If you have a partner, talk to your partner. What do you guys want to accomplish? What do you want to do? What's your future? What's your 5-year, 10-year, 20-year, 30-year, 40-year plan? Seriously. Write it down. Be very specific. Give me specifics. I have never heard anyone complaining, oh my gosh, this plan is too well planned. Planned well. Now, nothing's written on stone. Pencil it in every year, at least once a year, maybe every other year. Go back to a plan. Amend it. Change it. It's fine. Life changes. Your goals will change. But I have seen so many times, so many people that they've reached my age and older, and they've realized, I just followed what I was supposed to do, and you know what? It was not fulfilling. That's not what made me happy. What would have made me happy would be, ooh, too late. Right? Make a plan. If you give me a 6-pager, great. If you give me an 8-pager, good for you. It means that you're really thinking about it and you're planning for your future. That's my side.
Thank you very much. Thank you very much for your inspiring words, and I'm very sure that a lot of people will think about this. It's always time to think about this. Thank you very much.
Okay. All right. Okay, so I'm going to chair the session. Thanks, Petya, for the questions. Hopefully my answers were appropriate. So I'm going to present speaker one by one, and then we're going to have questions, I'm being told, at the end after all the presentations. So first I'm going to present Germán Barquero is a PhD student in computer vision at the Universitat of Barcelona and the Computer Vision Center. He holds a double bachelor's degree in computer science and mathematics from the University of Barcelona, and master's in computer vision from the University of Autònoma of Barcelona. His research interests include human behavior understanding, human motion modeling, and generative models. All right, I already like this guy. Please bring your hands together.
Okay, so yeah, great. Hope everyone is hearing me well. Thank you, Aleix, for the amazing introduction. I'm here today to present our work presented a few months ago at ICCV, which consists of human motion prediction. So I'm going to, okay, right, yeah. I want to briefly present the problem to those of you that do not know what human prediction is about. Well, we have a motion sequence, which is called our observation, and we want to predict the continuation of this motion sequence. Yeah, but we don't want to do it in a deterministic way. As this example, we want to assume that the future is multimodal. So we have several futures that are equally plausible, so we need to predict instead a distribution of futures, right? This is a generative approach that we call. Why is this important? Well, this is very important in many applications. For example, autonomous driving, we want to anticipate the behavior of the pedestrians to adapt the car, right? It's important for robotics, for virtual avatars, and also for anomaly detection, for example, in surveillance. Yeah. So our work is based on an observation. We went through all the prior works that they were doing generative human motion prediction, and we observed how they were very focused on predicting the diversity, right? On predicting high diversity for these motion sequences that they were generating, right? This might be important for many applications, but we were more interested in generating differences that can be subtle in terms of behavior and not very diverse in terms of coordinates. Yep. So we analyzed how was this diversity that they were predicting, and we proved that they were generating very diverse poses very early in the beginning of the feature, right? As a result, they were predicting very fast transitions towards this feature, which if you look at them in motion, they are not realistic, right? So if we quantitative analyze this problem, we observe that if we plot, here this is the plot of the velocity of the joints across all the predicted motions, we observe that they have, in the very early of the future, they have this acceleration in velocity that is not representing what we have in the dataset and not at all how human behaves, right? So our contributions in this paper, in this work, are threefold. First, we propose a method for generating more realistic and coherent predictions with respect to the observation. We also propose the first cross dataset for evaluating this task. And trying to help with this problem that Fernando mentioned about the metrics, because evaluating generative models is hard. We proposed 2 new metrics for not missing anymore the problems that I described before. Right, to explain the methodology, I'm going to explain first how we build a behavioral latent space, and then how we leverage this behavioral latent space for human motion prediction. So first of all, we don't have labels. Data is hard, as Fernando mentioned, right? So we don't have labels of behaviors. We don't have atomic actions, right? So we came up with this unsupervised method for learning this, for disentangle this behavior in the latent space. And what we did is we built a variational autoencoder with 2 decoders. And these 2 decoders, they are playing against each other in an adversarial fashion. Okay, so this is what we call the auxiliary decoder, which has to autoencode the motion sequence, right? This is a very basic autoencoder, right? And there's another decoder, which is the behavior coupler, that it also needs to reconstruct the motion, but there's 2 differences. First, there's an additional information in the input, which we call the target motion. This is providing information about the context, about posture, velocity, and acceleration. And it also has a negative term of the other loss, right? So it needs to make the other decoder do a worse job, okay? But since it only has access to how the latent space is built, it cannot modify the decoder, the other decoder. It has to make small modifications in this latent space that penalize the decoding, the reconstructed motion, right? Since it has access to this extra information of posture, velocity, and acceleration, it can destroy it from the latent space. And by destroying this information from the latent space, then the auxiliary decoder will not be able to reconstruct the posture because it doesn't have access to this extra information. Yeah, and eventually, after a long play, we have eventually in this latent space a higher level representation of the motion, which we call behavior or action, right? Eventually, the behavior coupler is able to transfer any of this behavior to any ongoing motion. For example, here we observe this behavior in the left, which is like moving backwards and then forwards, and we are able to encode this and apply it to very different contexts, and we are able to generate this behavior in different contexts, right? So now all we're left with is, okay, we have this latent space, now we need to sample from this latent space, and then we can decode this into our prediction, right? And anything we do, it has a behavioral meaning, okay? So which are the models that are really good at modeling conditional distribution, conditional probabilities, diffusion models, right? So we train a diffusion model to conditional this observation to predict which is the distribution of behaviors that will follow this observation. Once we have this distribution of behaviors, we can use the behavior coupler to generate this motion sequence that coming from this observation, it makes sense, it's smooth, and it transitions realistically to this feature. We only train the latent space in this second step because everything is pre-trained before. And yeah, we also use we use these standard laws in the latent space, but we also use the reconstructed laws because we are using the X0 parameterization, where instead of predicting the noise, we are predicting at every step of the diffusion, we are predicting the denoised motion, or in this case, the denoised behavior code. We also propose an implicit diversity loss, which is instead of predicting a single prediction, we predict k predictions, and we only backpropagate through the prediction that is closest to the ground truth, which leaves the model with more freedom to learn. We showed that we are very good at, especially for realistically generating motion, and also for adapting the diversity. What does that mean? If we cluster the ground truths and we compute the diversity of the ground truth in several of the class labels that we have in this data set, we observe that there's a fluctuation. You need to look at the box plot, at the white box plot. It depends, depending on which class we are in, of course, the diversity intrinsic in the data set, it's different because there's more determinist or more uncertainty, right? And diffusion is the only one that is also fluctuating very well and adapting to this context, right? Instead, diff sum, for example, the purple one, is predicting very diverse movements, no matter which class we are looking at. We also show that this implicit diversity loss is very good at increasing the diversity of the predictions. And also, this is very interesting, with one single step, when the K is sufficiently large, we are able to, in one single step, already denoise the motion very well and very fast, of course. But if we need very accurate and especially very diverse and realistically looking motion, we need to go through all the chain, right? But this is a very nice application for real-time scenarios where we need to be really fast, right? Especially in human motion prediction. So if we look at the samples visually, we observe how Bellfusion, our work in the last row, is able to generate a diversity that increases, right, with the uncertainty in the future. In earlier feature, there's less uncertainty that in 2 seconds mark, right? It adapts very well. Here, for example, the person is eating in the observation, so this diversity is focused in the upper body, right? And it doesn't do very extreme poses because the person is eating, right? If we look at this in motion, we observe that Bellfusion predicts more realistic and smooth results than state-of-the-art of the methods that are diversity-centric, right? And very interestingly, it's better at generalization. For example, this is an example of the cross data set, a scenario where this movement has never been seen, but still it is able to predict this rotational movement in the future and slowly stop it or start performing other actions. Of course, this does come with some limitations. We're using diffusion models. Even if it's latent diffusion models, we're still going through 10 denoising steps, which is slower than GANs or variational autoencoders. We still struggle with high frequency motion. And if the domain drift is very high in the cross data set scenario, then we are not able to do good predictions. The future work, we are planning to extend this for other signals like objects or people. We also plan to see how it performs with longer observation windows. And also, what if we had labels, right, for doing a better behavioral disentanglement. So thank you very much for your attention. And I will be happy to answer any questions.
All right. Next speaker is Wen Tong. He's an applied scientist at Amazon Science here in Barcelona. His research focus is on generative AI, specifically on image generation, and before joining Amazon, he was a PhD student in computer vision at the Hanover University in Germany. Wen Tong.
Thank you for the introduction. Okay, good morning, everyone. My name is Wen Tong Liao from Amazon Home Innovation Team. Thanks for the opportunity to introduce our work in this symposium. This work is a cooperation with my colleagues Qianli Feng, Raghupdeep Saget, me, Edward Lamont, Alice Martinez. So in this work, we propose a novel, simple, but yet effective semantic segmentation algorithm on style guide sensitive image. Now let's talk more on details of this work. The problem we study in this work is semantic segmentation on synthetic images. We will start by describing our solution for style guide 2, and then briefly mention how do we go beyond style guide in the later stage of this presentation. Semantic segmentation on style guide is really not a new problem. Many world has done it by taking advantage of the rich semantic structure learned in the style guide generator, such as dataset guide, label for free, some segment in styles, for guide, and so on. But all the previous methods have a common feature, is that they use a masking network branch that takes the intermediate feature of style guide generator as input, and then produce output mask. This is somewhat problematic because for every new generator, the masking branch has to be retrained. In the case of the new generator architecture, the masking branch even have to be redesigned. Also, due to the high dimensionality of the intermediate features, the previous methods often face challenges on GPU memory limitation for high-resolution synthesis output. So, in this paper, we proposed a novel, simple, but yet effective semantic segmentation method that, first, it does not need to train an independent masking branch, and is an unsupervised method, so no pixel-level human annotation needed. It has highly accurate. We achieved this by deriving from our key observation that in StyleGAN 2, pixels that belong to the same semantic class change their color together across different style mixings. Further, let's first talk a little bit about the background of style mixing in StyleGAN 2. Style mixing happens between the two latents of the StyleGAN, or two latents for the StyleGAN generator. Here, latent 0 and latent 1, it happens in the W space representation space of the latent. That is right after the mapping network, and then replicate it for the synthesis network's input. So you will see the multiple layer of multiple vectors of the latents in the W plus space. And if we say we want to preserve the structure of the first image and the style of the second image, we can define a layer cut of C and saying everything before C is for the structure and everything after C is for the style. Then we simply mix the two latents and pass it to StyleGAN generator and generate an image that has the structure of the first image and has the style of the second one. So, knowing this, let's recap what we said on the key observation. In StyleGAN 2, two pixels that belongs to the same semantic class, they change the color together across different style mixing. So, what more specific do we mean? Let's take a look at these four images as an example. In this fourth image, we can first extract the background pixels. Let's do two patches here, 1 and 2 on the background. And we can do the same for two patches on the clothing, and two patches on the face, and two patches on hair. And we can do this just for latent 1 and latent 2, 3, and 4. And remember, 1 and 2, 3 and 4, 5, 6, 7, and 8, they are each pair corresponding to a different semantic class. So if we group them together, we can somehow notice that for the same object or same semantic class, the color change across different latents, across different style mixing, they are highly correlated. On the other hand, when the pairs or colors and pixels, they are coming from different groups or different semantic classes, their color changes across style mixing is of very low correlation. So this is the key observation that we divide up our algorithm upon. And once we know this, the algorithm design is super simple. So for a given input to our algorithm, just have the following 4 steps. First, generate a style variance by the style mixing. For example, in StyleGAN 2, or it can be used by the other methods. Second, we concatenate all the style variants to get n by c by h by w tensor. N is the n number of style variants. Then we cluster the pixels. So here is h by w pixels into k clusters by flattening the n by c dimensions. And 4, we performed a foreground identification heuristic for foreground-background classes. These algorithms can be extended very easily to object in the instance segmentation with the help of a detector. Simply do the detection first in the original image and then run through steps from 1 to 4 just within the crops. And we can do this because our algorithm is solely operating in the pixel space instead of the intermediate feature space from StyleGAN 2 generator. So in the experiment section, we tested the foreground-background segmentation test directly on synthetic image. Our method has the comparable performance on the benchmark data set. But it's worth noting that again, our method is network-free, and it does not need any data to train. And for the instant segmentation on sensitive image, where we have an advantage in terms of the design as previous methods, find a very hard time to extend to such task. Third, we test on generating sensitive segmentation data for downstream training. We trained the segmentation method of Deep Lab version 3 on the images generated from the FFHQ model, then test on the SLIP 8 mass HQ dataset. We can see that the model trained on the sensitive data generated by our method has the best performance. Now, let's show some qualitative results. Here are some examples of face segmentation. The result is very precise. And here are segmentation of cats. Also, segmentation on various animals. Here are two examples on object segmentation, as well as the comparison with the previous methods, label for free, segmentation in styles, and our methods. Unlike previous example of face segmentation, segmentation in lifestyle scene is much more challenging because of the complex background and layout, multiple objects, and the object of interest can be anywhere in varying size within the images. You can see the challenge the previous phase on the extending to object-specific segmentation. For the label for free methods, they cannot segment anything. And for the segment in style, the segmentation result is not so good. So for our method, the sulfate is well segmented, and we also can separate the sulfate and the table next to it. So thanks for your attention, and please check our paper. Thank you.
All right, our next speaker is Rita. She's a PhD student in computer science at University of California, Berkeley, affiliated to the Berkeley AI Research, better known as BEAR. Born in Ukraine and raised here in Spain, she received her bachelor's degree in data science from the UPC and set in motion her grad studies at UC Irvine before transferring to Berkeley. She has led research on multiple deep stereography and image processing groups at the UPC, has interned at Stanford and Amazon. I can attest for that, as she's been an intern with us a couple times. And she is very active in event planning space in San Francisco Bay Area. And currently, Rita is the TechStars community lead of the San Francisco chapter. All right, take it away.
Thank you for the introduction, Aleix. Sorry. It's a pleasure today to present a recently published paper at NeurIPS. Actually, it was last week in New Orleans, titled Adversarial Learning for Feature Shift Detection and Correction, work led by Miriam Barabés, Daniel Mas-Montserrat, and with the collaboration and advice of myself, Xavier Giró Nieto, and Alexander Ioannidis. Work joined between Universitat Politècnica Catalunya and Stanford University. And as the title suggests, we have two parts. We have detection and correction for the problem of feature shift. And before going with the explanation of the method, let's briefly explain what is a data shift. A data shift is a phenomenon where certain features have a significantly different distribution between two different data collection processes. You can think of the training dataset collection process and the test dataset collection process. In this example, we have the reference dataset and the query dataset collection processes. And to quantify the divergence, we can use any valid statistical divergence measure specifically F divergence measures, Kullback-Leibler, Jensen-Shannon, or the total variation distance, which is the one we used in this work. And the data shift problem is a really common problem. Almost in every field you will find it, especially in ours, which is the biomedical field. Let's see an example. Imagine a scenario where we have researchers that want to combine their data sets to do some inferences and make some studies on a rare disease. And well, what we would do, we would merge data sets from different institutions, different labs. And if we just run on the raw merged data set some inference algorithms, probably the results will be not correct or biased. And why? Well, first thing is that the labeling might be different in one data set. In one data set, maybe the sex is labeled as 1 and 0, and the other one is 0 and 1. Maybe in one data set, the quantities are precise, while in the other they are clamped or clipped or approximated or simply biased. Maybe in one data set, we have different units. Maybe something is in Celsius, in the other one is in Fahrenheit. And all that, of course, if we run on this raw data, it won't work. So here's where we propose DataFix. DataFix is a framework to fix these data shifts. And it has two parts. The first one is DataFix Locate, which does the localization of the features that provoke this data shift. And DataFix Correct, which imputes in a smart way all these features that have been localized in the previous step. So first of all, we would take the reference, the clean data, and the query data set, which is the one that has the data shift. We would run the DataFix Locate to localize the smallest set that if you get rid of it, then the data shift will be gone. And after this localization step, we would run DataFix Correct, which again uses the reference data set to constrain the search space to impute it in a way that it makes sense with respect to the reference data set. So let's go step by step. The first step, the localization step, as I mentioned, we have to find the smallest subset of features that if we remove it, the divergence will be small enough. And this problem can be formulated as an optimization problem where you maximize the mutual information of some components of this pipeline. I will refer you to the mathematical derivation to the paper, but I want to give you just the intuition. And the intuition is the following. We would take both the reference and the query data sets as a whole, and we would get a sample from it. And once we get a sample, we don't know from which data set it comes from. We would run it through a classifier, specifically a random forest classifier, and this classifier will try to classify whether it comes from the reference or the query. And once we train this classifier by randomly taking samples from the reference or the query, as you know, random forests, you can get feature importances. And if one feature starts to have a really high feature importance, maybe something is very peculiar about this feature because it allows you to discriminate between which data set it comes from. So that's the basic idea. Why would you use feature importances to find these features that might be causing the data shift? So once we have the feature importances, we would sort them, normalize them, and then we would remove the features that have really high feature importances. After that, once we have this filtered, first step filtered query data set, we would compute the divergence. And if the divergence is not good enough, we would run again the same thing, but with the filter query instead of the original query. And so on. We would like removing all the features until the divergence is fine. That's the localization step. After that, we would proceed with the correction step, which is the smart imputation. Again, the imputation step can also be formulated as an optimization problem, where we try to minimize the divergence between the reference and the query data sets, constrained on the search space, constraining on the reference data set so that the search space is within the values of the reference data set. And again, all the details of the algorithm refer to the paper, but basically the idea is that first we would do a simple imputation, for example, with k-nearest neighbors, or linear regression, or a combination of both methods to impute initially all these missing features. And then we would run a data fix correct, which makes some proposals, and we choose the best proposal that fits in these missing features. And after, again, we would compute the divergence. If the divergence is not good enough, then we would run it again. If the divergence is good enough, then we would output the filtered, imputed query. So that's it. Experiment-wise, we run experiments with 12 real data sets, which are here in this table. And also we run experiments with simulated artificial data sets, which you can find in a paper. And basically the strategy with each data set is that we took 50% of the samples for the reference data set, and 50% of the samples for the query data set. And for the query data set, we corrupted some features to provoke this data shift, either using introducing some uniform noise or random permutations or any other sort of manipulations. And the results were pretty satisfactory. We benchmarked data fix locate with localization, data shift localization methods used in practice currently. And as you can see, data fix gives the highest F1 scores across all the methods that we have tried here. And same behavior with data fix correct. We benchmark it with methods that are being used to impute features after finding data shifts. And again, it gives the smallest divergence. This divergence is not the total variation distance. It's another one that upper bounds it. Details again in the paper. And like both of these results place us as the state of the art for data shift correction and localization. So to conclude, adversarial learning from the title, we use adversarial learning because we're training several discriminators with random forest to distinguish between two distributions, the reference and the query, to detect and fix corrupted features that provoke the data shift. And as an insight takeaway is that tree-based classifiers combined with iterative heuristics can localize and correct feature shifts, outperforming all the existing currently popularly used techniques, placing us as the state of the art for data shift correction. And good news is that our method is publicly available on GitHub. So you can scan this QR code or find DataFix. The repository would be happy to hear feedback if you start using this in your learning pipelines. Please keep in touch. And Miriam, the first author of this paper, she's also here today presenting a poster. I'm happy to meet you guys. Thank you.
All right, thanks, Rita. And we have one more talk this morning. Xavier Suau is a research scientist at Apple's machine learning research team. His research focuses on structured representation learning and understanding structures of latent spaces in general. Before joining Apple, he co-founded a machine learning first startup in Barcelona, working in human activity recognition using computer vision machine learning. And prior to that, Xavi earned his PhD at Telecom Barcelona.
Thanks, please. All right. Bon dia a tothom. I'll present this work called Duet to Destructured and Approximately Equivariant Representations, which was presented at this year's ICML. This is joint work with Fede, Andy, Arno, Chen, Jason, Dan, and Luca, and I just highlighted those that are based in the office in Barcelona. Okay. Okay, this doesn't work. So the main objective of self-supervised learning, multi-view self-supervised learning nowadays, is to learn representations without the use of any labels that are useful for as many tasks as possible, so we can reuse them, right? But the main problem behind that is that the key learning procedure in SSL is to discard task-irrelevant information by contrasting differently transformed images. And this is ill-posed because what relevant means is dependent on the task. For example, we might need color to classify fruit ripeness or to segment images, or scale is super important if you work with medical images. So the key idea behind this work is to preserve as much information as possible in the representation space while still being, while still learning good features. And we do that by structuring the representation space. And also we show in the paper that through this structure, our features become equivariant, meaning that transformations in the input consistently map to transformations in the feature space. So we have an additional property, which is controllability. In the next slides, we'll see that using this method, we can improve discriminative performance of these features, but also improve transfer learning. And in addition, we have controllability for generation. All right, so why structure and why equivariance? Structure is important when we want to have an efficient learning of a representation space, because we know how to organize it, or at least we have an idea of how to organize it. So we can use less features, and in addition, we can also interpret this representation space because we know how we organized it. Equivariance is a more stronger condition on structure, and basically it allows us to have a correspondence between transformations in the input and feature space. So the organization in input space and feature space has some strong relationship that is explained by two different transformations that we'll see afterwards. So by these two constraints, to achieve these two constraints, we propose to learn two-dimensional features instead of one-dimensional ones. These two-dimensional features have two axes, and one is related to the transformation structure that we want to learn, and the other to content. To compare with SimClear or other traditional self-supervised methods, there's only one dimension, which is the content. So this is structured in the sense that differently transformed images will be encoded in different parts of the representation space. And it's equivariant, meaning that transformations in the input space will be mapped to a transformation in representation space, and we show in the paper that this one has a closed form and thus enables explicit controllability. We base our method on the SimClear architecture, although we could take other multi-view self-supervised learning architectures. In this SimClear architecture, an image X is augmented twice and then mapped to a representation here in green. These representations are contrasted using a contrastive loss or any loss that compares views and to gain invariance with respect to the augmentations. And then once trained, these vectors are used for downstream tasks. In our case, as we said, we learn two-dimensional representations, and this allows us for more flexibility. For example, we can marginalize in the vertical dimension, and then we remove the effect of the content, and we're left with what we call the structure marginal. This is a distribution over the transformation parameters, if you want. Let G be, like, for example, the angle of rotation, or any parameter that parameterizes the input transformations, right? So since we have access to the transformations that we applied during training, because we sample them and we transform the images, so we control that, we can design a target distribution for this one. The one in red, we choose a Gaussian. It could be another one. But Gaussian is useful because also we can control with sigma, we can control the uncertainty. And then we minimize the Jensen channel divergence between these two. In a similar way, we can marginalize in the horizontal dimension, and then we remove the effect of the transformation, and we're left with the content. And this content is explicitly invariant to the effect of the transformation. And then these two contents are contrasted using the same contrastive loss as in SimClear. So the final loss is a weighted sum of these two, where lambda controls the amount of structure in our representation space. Then finally, these features are flattened and used for downstream tasks. And if you wonder, like, this is just a reshape of the features in SimClear, so there's no additional features here. It has the same number of beans, let's say. So what can we do with duet representations? As we mentioned, thanks to equivariance, we can control them. And I'll just show you a visual example. So this image, this number 4 image, is our input image, and we map it to a duet representation that we show here. This is a real one. It's just shown as with a color map. And then we forget about the input image, and we decode it using a trained decoder. It's not a high-quality decoder, just for the sake of illustration. But what we can do then is with this transformation T, we can transform the features and still decode. And as we transform the features and we decode, and we're not using the input image anymore, we preserve the content and we transform and we observe the effect of equivariance very clearly. We see that the transformation is really transferred from input to the feature space. In this work, we've worked with other transformations that are usually used in SSL, some geometric and some color ones. And in here, I show you some more examples of the same experiment we did before. Qualitatively, we encode the image on the far left, and then we decode the transformed features of that image. And we see that for different digits or different transformations as flip, we can recover the effect of equivariance pretty clearly. Same thing for color images. These are cipher 10 images. And here we learn structure for contrast or for hue. So again, the quality of the decoder was not optimized here. It's just to visualize the effect of this equivariance being learned. Now for quantitative results. Here in this experiment, we have a linear head on top of our features that is trained as the SSL method is trained. So it's not a fine-tuned one, it's just the online one. And we show the test accuracy for SimClear in gray, and for ESSL, the state-of-the-art method, meaning equivariant SSL, in blue. And in this experiment, what we use is random resized crop plus one augmentation that we show on the x-axis. And we learn structure for each of these augmentations. And we see that our method outperforms SimClear for in all the cases, but for horizontal flip, which is on the verge. While ESSL outperforms SimClear for geometric transformations, but it really doesn't work for color transformations. So our method seems robust to any sort of transformation, and these results also hold for other slightly more complex data sets like Cipher 100 or Tiny ImageNet. Another experiment related to classification. In this case, we use the full augmentation stack. So we're applying a composition of transformations on the input image, and then we'll learn the structure for the color transformations. And this is the average performance when we learn structure for each of the color transformations. And we see that with Duet, we scale with the complexity of the task. So for more complex tasks, Duet starts to shine. So the structure is learned, it's more effective. While ESSL, which it's a method that encodes some sort of structure, but it's not explicit. It's not equivariant, as, even if the title of the paper is equivariance. Kind of fails when the data becomes more complex. And finally, some results about transfer learning, as we said at the beginning. In this case, we transfer from features learned on Tiny ImageNet to other data sets that you see on the x-axis. And we show the accuracy improvement with respect to SimClear. We tested that for all different transformations, so learning structure for all different transformations. And in gray, we show the transformation that led to maximal improvement. And we can see that, for example, for cars and flowers or food data, color transformations lead to maximal improvement, while for other data sets, geometric transformations are more important. We can see also for Caltech 101, we improved by 21% with respect to SimClear, which is a great improvement. All right, so to conclude, we've seen that with Duet, you can learn structure and equivariant representations via self-supervised learning. We didn't mention this, but this method doesn't add any parameter to the network, and it just involves a little bit of computational overhead because we have 2 losses instead of 1. Then in terms of results, we saw that we can improve discriminative performance and transfer learning, and also we gain an additional property on SSL that was not available for unstructured methods like SimClear, which is controllability for generation. And finally, we also gain some better understanding on the transformation impact in SSL. So if you want some more details, we have open source code in this GitHub. There's also the link to the paper, or just drop me an email. Happy to talk. Thanks.
All right. Wonderful talks. Unfortunately, we are completely out of time, so please look for the presenters during the coffee break. to ask as many questions as you can. And thank you so much to all the presenters for such a great work. Let's hear it again.
Hi, just one logistic thing. We have now the poster session and coffee break. So coffee is like in a room behind this wall. So you go to the corridor and towards the right. And then for the posters, there are posters along the corridor and also at the entrance. Okay, thank you.
Funciona? Sí. Hola, bon dia, benvinguts una altra vegada. Welcome to the second session of talks of this morning. Today is my pleasure to introduce you the chair, Antonio Torralba. Antonio, as many of you know, is Professor of Electrical Engineering and Computer Science at the MIT. He's also the chair of the Artificial Intelligence and Decision-Making chair. and the head of the Laboratory of Computer Science and Artificial Intelligence. His research is very well known. It includes the areas of computer vision, machine learning, and human visual perception, trying to make systems that can perceive the world like humans do. He and his massive amounts of collaborators and mentored researchers at many levels that have passed by his lab are solving computer vision problems, sometimes including other modalities such as audition and touch. As you know, he has also made many contributions on understanding neural networks, artificial intelligence at different levels, appropriate dataset creation also, computational photography, as many more. Today, we are going to take advantage of his massive knowledge and experience in these fields. Antonio, I have some questions for you. Let me start by the first one. The past years, we have seen a lot of advances in language and vision generative models. And the question is, are these systems also the solution to, for instance, recognition problems?
Okay, well, thank you for the introduction, and hi, everybody. The question if these generative models are the solution to all the problems that we have now in vision. So I think that it's obvious that the field has made enormous progress in the last few years. Like, really, it's just amazing to see all the things that kind of work right now. And I think that it's dangerous to fall into the impression that everything is done. I think that is sometimes you see the systems working and solving tasks that are just, were our kind of dreams when we started the field, and it seemed like it will take decades to get addressed, and now they are kind of working, not completely, but working pretty well. And it's very easy to fall into the impression that there is nothing else to do, that everything is done, and you just need to wait and see what OpenAI does, and that's it. And I think that that's not really true. It's always been difficult to know what the right questions are and what you should be working on. I don't think that's any harder now than it was 20 years ago. It requires you to have to know the field, to have perspective, and to understand what are the right questions to ask now that will allow you to do the next advance. The question should be not too easy so that what it's out there already solves and answers the questions that you have, but not too hard that you cannot make progress on it. So just having that right balance that will be this question that you can actually answer, that will lead to answering the next question or formulating what the next question will be. Finding that question has always been difficult. So sometimes we find excuses to why it's difficult to do now. And one of the excuses could be, well, these generative models work so well, so there is nothing else to do. It's just an excuse. It's always been hard, and I always heard excuses, and I formulated my excuses on my own when 20 years ago, and it doesn't matter. It's just, there is always more to do. You can see if you look at the conferences, there is not a decline on the number of papers that get submitted. If anything, just the contrary, there is even more work now than it was before. So there doesn't seem to be a sign that there are no questions to ask. Otherwise, people wouldn't be publishing papers. Because, of course, not all the papers ask questions or answer questions, but many do. And I think there are a lot of interesting questions. Generative models, generative AI was emerged with the idea that you will not need so much data to train. But that has not happened. If anything, they need even more data than they needed before. So how do you train, how do you build a model that has the right architectural priors so that it really doesn't need so much data to train? So I think there are a lot of questions we can ask.
Yeah, good points. Yeah, let me go to move to another question. In the past ICCB, yeah, sorry. In the past ICCB, you expressed an opinion. You said that the vision community could contribute more to robotics field. How do you think this interaction should be?
So the reason why I say that is because in the new era of generative AI, and in particular with the big progress that has been made on large language models, I think that computer vision is going through an identity crisis. And many of you, and if you're doing computer vision, and if you see what is happening in the top conferences in computer vision, you will see that most of the papers are actually about language. They incorporate language and they do something with language. So language is kind of the big component, and then there is a little bit of vision. So I think there is an identity crisis on the computer vision community. And part of that crisis is because computer vision has been developed really a little bit without a task in mind. It was something that was open loop. You get an image and you output something. Why? It doesn't matter. Just try to output something, because it was so difficult to output anything that people focus on that a lot. So we kind of lost sight of the fact that perception is part of a big loop that is perception, reasoning, and action. And in order to close that loop, that loop is what gives meaning to perception. It is what it provides the excuse, the reason why you are building a perceptual system to start with. And I think that if we connect with robotics more, and I think there is a big trend now, a lot of people and a lot of labs are starting to do that, by connecting with robotics again, there was a big connection many years ago, but it kind of got lost. So by recovering that, making that connection strong, we will kind of provide a new ground in which to start providing some grounding to perception, why you need perception, so that you can do perception without language. Okay, language is important, you can still put it there, but you don't have to. There will be a reason why you are building a perceptual system. So I think that, that's one of the reasons why I think that robotics has to play a bigger role. The problem is that there are no robots, but anyway, that's another question.
But when you mean robotics, you include robotics having the perception language perception, hearing perception, because for instance, for people having impairments,
Yeah, so robots in the sense of mechanical beings, but with perception. I mean, they need to have a strong perceptual system.
Third question. In the first edition of the Deep Learning Barcelona Symposium in 2018, you proposed, in a very political speech, an investment similar to the Forum of Cultures, but focused on artificial intelligence. This has not happened, as all of us know. Can scientists do anything to promote this type of event happening?
Yes. So I remember doing that. So I suggested that it would be good to have a big event in Barcelona, similar to the forum, where there is a big discussion around AI. And I still think it's a good idea. Maybe it was just too early at that time to suggest that, but now is the right time. Like now, I think that it cannot it cannot wait any longer. We have the AI law that the European Commission created. I think that it's time to have a long debate that incorporates scientists, the public, politicians, and have a debate just similar to what the Forum of the for Cultures was, something where you have an encounter between human intelligence and artificial intelligence. And I think it will be great. It hasn't happened, and there are several possibilities. Maybe it's not a good idea, and some of you decided that you wanted to do it, and then you thought more about it, and then you realized it's not a good idea, and this is why it hasn't happened. Or maybe it's a good idea and no one took the lead. I don't think the community has to wait for someone else to do it. Like, who? A politician, a government? I mean, who should be doing this? I think it's you. Someone should take the lead and do it. I don't have time. So, one of you.
Well, it's almost time. Therefore, let's move to my last question. I choose this one. We heard that you have been working on a computer vision book that will appear now or next year. Can you tell us a bit about this book?
Yeah, I don't think we have enough time. So, yeah, we just submitted the last version of the manuscript yesterday for publication. So now it's on the hands of the press, of MIT Press, and hopefully will appear on the spring. And it's been a long process. We started in 2010 writing this book, and it was part of the lecture notes for the computer vision class that we are teaching at MIT. And when we started that, there were 40 students in the class. Now there are 400 students. So the field has changed so much since we started. And some of the material become obsolete, so we had to do some rewriting and so on. But most of it is part of the what the final book will be. When we started writing this book, we wanted to write something that it was going to be very comprehensive, like really cover the full field. And so it will be a very big book, a very large book. Then we realized that we didn't have time to write that, and also that you wouldn't have time to read it. So we decided to write something really short, and we decided to have the goal of writing chapters of 5 pages, no more than 5 pages, so that will keep us to the point and you'll have time to read that. We also failed at that. We couldn't do it. So the result is what we have now, which is none of the two. But I think that the goal of the book was to have something that was inspirational. So we tried to make the connections between perception and artificial vision and human perception, giving the foundations of the field, but also try to inspire people to be not engineers but scientists. Not trying to make systems that work, but to understand how they work. And so that's kind of the focus of the book. And it's intended for undergrad and graduate students, and whoever wants to read it. It's going to be big. At the end, it's more than 800 pages, which is more than I thought that we will be able to write. It's been a torture to write this thing, but also very enjoyable. I don't know, like running a marathon, that when you're in the middle, you wonder, what are you doing? And then, but when you finish, you actually are happy that you did it. This is probably worse than that. Anyway.
Very interesting. I'm looking forward to it. Let's thank Antonio for his very inspiring answers and ideas. And let's move to
Okay, now I'm going to be chairing the next session, and it's going to be a series of really exciting presentations. I think, Ginger, you can get ready. So the first presentation will be by Ginger Delmas. She's a PhD student here in Barcelona at the Institute for Industrial Robotics, IRI, and also Naval Labs. And she's done really, really interesting work on human pose understanding, and she's going to be talking about that. Thank you. I'll control 10 minutes.
Yeah, thanks a lot. So I'm going to present 2 works on linking 3D human poses with natural language. These works were published at the last ECCV and ICCV, and these were joint works with Philippe, Thomas, Francesc, and Gregory from Institut de Robotica Informatica Industrial and Naval Labs Europe. So language and vision have long been a hot topic for research, with works like CLIP and DALI, and language and 3D geometry have been exploding these last few years. And here we focus mostly on language and 3D human poses. So you can see at the bottom right here, downward dog yoga pose that comes with a description of it, explaining a bit what is happening here. So for example, the head is down, the legs are straight, the hips are raised, and so on. So this gives you a bit of an understanding of what is going on here. And this is interesting for several reasons. This opens the door to several applications as soon as we are able to understand human pose. So for instance, digital animation for pose generation, pose modification. It could be for searching for complex poses in a large-scale datasets. For pose teaching, if you have a description of the pose you should be doing, or even feedbacks on how to correct your pose. Pseudo 3D annotation when it's not possible to deploy a mockup system. Maybe you can just get away with it with a nice description of the pose. Or to guide pose estimation in fair cases. So for example, with text feedback, maybe you can correct a bit more the pose. So semantic comes in part from language, and language can take many forms. One of them is binary relations. So for example, is the left hand above the hips? Yes, no. It can be a label. For example, this is a sprinting motion. Or it can be natural language, basically a description. And here we focus on natural language, as it's a very intuitive way to communicate ideas and super flexible. Prior datasets focused mostly on motion descriptions, so this is nice to constrain sequences of poses, but it only weakly informs about the body part relationships or even the state of body parts. So this is what we are interested in here. So we came up with two datasets for this task, and in particular we distinguish between two kinds of text. One of them is a description, so basically a description of a pose that you could reproduce just by reading the description. And the other one is a modifier, be it an instruction explaining how to go from one pose to the other, how to modify it. So the two of them are complementary because the description is absolute, whereas the modifier is relative. And yes, so we introduced two datasets for this. The first one is called postscript, and the second one is called postfix. So I'm now going to explain how we built these datasets. So both datasets were created in a similar way. First, we had to select pose from this. We selected 100,000 poses from the IMAS dataset, which is a huge dataset of motion sequences. And we wanted the pair poses to be quite similar because we wanted to learn about fine-grained differences. And at the same time, kind of different because otherwise we would collapse to over simple instructions. So we still wanted to learn from rich information. Once we have these pairs of poses, we collected around 6,000 human written annotation on Amazon Mechanical Turk, the crowdsourced annotation platform, by showing the poses under different viewpoints, so we really have description about the 3D information. The thing is, this is pretty expensive to obtain, so we came up with a pipeline to automatically generate text for a data-hungry algorithm. So I'm now going to explain how this pipeline works. This pipeline takes as input 3D human poses, in particular the 3D key points of the pose. And what we do first is extract low-level information. So basically, we're gonna measure for the key point position, the relative position between two key points, and then interpret these measurements to understand a bit better the configuration of the pose. So maybe the left arm is bent at a right angle, maybe the 2 feet are wide apart, and so on. And once we have this low-level information, we can combine them together to obtain what we call superpose codes. So for example, if the 2 knees are bent, you can say that the person is kneeling. And we do the same for a pair of poses. So basically, we extend these previously introduced pose codes to pair codes. And this can be combined as well with pose codes to help for summarization, formulation, refinement, and so on. So in our goal to obtain this text description about a pair of poses, this is really just the first step, code extraction. Once we extracted the code, we want to select them to have descriptions that are more fluent, more concise. In particular, we will remove trivial postcodes, we will remove redundant postcodes, and also sometimes keep randomly some of them because humans are not exhaustive. So yes, and then next we aggregate codes based on shared semantic. So if you have 2 codes talking about bending the left elbow, bending the right elbow, then we can say that we bend both elbows. Then we order code, because in text description, otherwise you would have information scattered everywhere in the text, which is super hard to read as a human. So to get a bit of logic, we will talk about codes by body part proximity. So maybe we will talk about all codes related to the right leg, and then all codes related to the left arm. And at the end, we plug this information into template sentences. So if we concatenate all these template sentences, we end up with a description in natural language. So this automatic pipeline was used to generate both pose descriptions and modifiers. It has the advantage of being highly modular because you can change the codes, like the configuration you want to study, you can change the way you merge information. It's randomized in several aspects, so you can generate lots of text for the same input. And it's cheap. It makes it possible to generate hundreds of thousands text in the time it takes to write one. So let me show you here an example of an annotation. Here is a pair of poses that comes with an automatic annotation produced by the pipeline I explained before, and then a text written by a human. So usually the text, the automatic annotation is more detailed, whereas the text obtained by the human is more concise, more to the point, and also would tackle more subtle details. But both of them are quite complementary. In particular, it's pretty useful to use the automatic annotations for pre-training, for example, and fine-tune only on the clean human-written data. So once we have this data, that is for the postfix dataset, made of 2 poses and 1 modifier text, we studied 2 different applications, where the goal is to generate 1 element from the other 2. So this first application is text-guided pose editing. Basically, you have the source pose and the modifier text, and you try to generate the target pose. So at this time, you have the source pose and the text. You encode them, fuse them together in a fusing module, and get a distribution from which you will sample to decode a new pose, which is basically the pose you like to see. At train time, we train this as an auto-variational encoder and also encode the target pose as a distribution, sample from it, decode it as a new pose that will then be compared to the initial pose for reconstruction. And since you want to condition on the query, you will align the 2 distribution of the query and of the pose. So here are some results of our model where given the source pose and a modifier text, we can generate several samples that have the requirement given by the text. For example, move your left hand to the right, while still preserving properties from the source pose, for example, the leg opening. The second task we study is called correctional text generation. This time, we try to generate the text from the 2 poses, like the instruction on how to correct one pose into the other. So we build on top of a regular autoregressive text generation model, which given the first k tokens, tries to predict token k plus 1. So how does it work in practice? We provide the tokenized the tokens as input to the transformer decoder and get a probability over the vocabulary for each of those tokens. And this model is trained with cross entropy so that the target of each token k is token k plus 1. So the model will really learn to autoregressively generate the next token. So now, how do poses come into the picture? So the poses are encoded, fusing together, and injected via cross attention into the model. At this time, we begin with the beginning of speech token and iteratively decode the next token by taking the token that maximizes the log likelihood, and so on until we get the end of sequence token. So here are some results of our model, where it's able to generate text instruction for a given pair of poses. In particular, it's able to take egocentric relations, for example, lower your arms to your chest, and it focuses mainly on the main differences. So what did we do so far? We designed 2 pipelines to generate automatic text to increase the size of the dataset limited by human-written annotations. In the first pipeline, it was mostly for description, and in the second, for modifiers instructions. And we used the 2 of them to tackle the 2 tasks I presented before, basically text-guided pose editing, where the goal is to edit the pose based on the initial pose and the text, and correctional text generation to get the instruction from 2 poses. These are actually evolution of a previous work where we had only 1 pose and a text, so we would generate the pose from the text or the text from the pose. And we also have some retrieval models. These were particularly useful for evaluation, but you could also design application related to these retrieval models. Let's say you have images associated with 3D human poses. You could retrieve images of people in a certain pose by querying it with a description of the pose you're looking for. So yes, that's it. Thanks a lot for listening. Code dataset available.
That was perfect on time, just 2 seconds left. So the next speaker will be Luis Castrejon. He's a research scientist at Google in Zurich. He works in machine learning, computer vision, natural language processing. He was actually a visiting student in my lab before he finished in Barcelona. And since then, he's been doing a lot of really great work. So thank you.
Thank you, Antonio, for the great introduction. Sorry. All right, so today I'm presenting Encyclopedic VQA, which is joint work with all these authors, which were at some point at Google. And this was presented at ICCB 2023. And this is a paper about data, going back to Fernando's talk, and it's basically a language paper with a bit of vision, going back to Antonio's remark as well. So let's start with a question. Who knows the answer to these visual questions? So fear not, we are all computer vision scientists, so we go and we take the latest and largest vision and language model. At Google, this is PALI, and we ask for the answers to this. Now the question is, do you know if these answers are right? And in reality, they are not, they are wrong. And we argue that these foundational models, they have a lot of difficulty with this kind of encyclopedic knowledge because it's about long-tail information that it's hard to encode in the model's weights. And not only that, they also provide answers without attribution, so it's hard for the users to verify if they are correct or not. One possible solution to this is to use retrieval-augmented models, which are models that use information retrieval techniques to fetch a piece of information from a knowledge base and use this to generate and justify an answer. However, these retrieval-augmented models, they are often tested on OKVQA and AOKVQA, which are two data sets for visual question answering. You have on the left examples of the kind of questions they ask. And they are great because they do require knowledge that is not visible in the image. However, they focus primarily on common sense knowledge, so we conclude that they are not good test beds to test this encyclopedic kind of knowledge. In fact, we did a very extensive literature review, and we concluded that none of the data sets that are out there for VQA are good for encyclopedic VQA. Therefore, our latest paper, Encyclopedic VQA, which is a data set that we built to challenge foundational models and also to hopefully showcase the usefulness of retrieval-augmented models. Here are some of the design principles for our data set. So first of all the questions in our data set are encyclopedic. We define encyclopedic questions as questions about detailed properties, so long-tail properties of fine-grained categories or instances. So again, long-tail entities and long-tail information about those. We provide a control knowledge base, which is a snapshot of Wikipedia. And for each question in our data set, the answer is attributed to a part of this knowledge base, so we can verify where it came from. Our data set is really large scale. We have millions of questions. And it is truly multimodal. We made sure that the questions cannot be answered just purely from the textual part or just the image part of the question. And finally, we also have many different question types that have different levels of complexity and challenges. So let's look at some of these question types. First, with the first two rows, which are templated and automatic, it's what we call single hop questions. And we call them single hop because they require a single piece of information from Wikipedia to be answered. So for example, on the left, who founded this monastery, you just need to identify this monastery. And then you, given, for example, the Wikipedia article of this monastery, you can find who founded it. And for example, this is a good way of seeing why it is really multimodal, because we always use the super category in the textual part of the question, who founded this monastery, instead of who founded the church of whatever. And that way, you need to identify the entity in the image to be able to answer the question. Basically, this question could be paired with any other image of a church or a monastery, and then it would be a valid question. These are templated because we use templates to generate these questions, and I'll go maybe into more details after. Automatic single hop questions are same kind of questions, but they were generated with an automatic pipeline. Then we have automatic multi-answer questions, which are single hop as well, because they require a single piece of information from Wikipedia, but the answer is a list of entities, so they are a bit more involved. And finally, we have two-hop questions, which are the most complex ones, and they require fetching more than one article from Wikipedia to answer them. So for example, what amusement park is located in the city where this square is located? So to answer this question, you first need to identify the square, then you need to figure out the city that it is located in, and then you need to figure out what amusement park is in this city. And that way, you see how you have to jump across different pieces of information in Wikipedia. All the images in our data set come from Google Landmarks and iNaturalist, which are data sets about very fine-grained locations in the world or natural species. Here's an example of how we built the single hop templated questions. So we start with the super category, monastery, and then we can formulate a question that is universally valid about this super category. For example, when this monastery was built or who founded this monastery. Then we pair it with a particular instance, in this case, the Horizon Monastery. And for this is an image that comes from one of these data sets, and we also match the entity to its Wikipedia article. And then what we do is we send just the Wikipedia article with the question to a human rater that provides the answer and identifies which part of the Wikipedia article the answer is found. And by doing this, again, we enforce that it's truly multimodal by design. And then there are different things, different trade-offs to the different kind of questions. For example, the templated ones are truly multimodal, but it's limited the number of questions that we can pose because we cannot come up with such a big list, and they are less scalable than automatic questions, which I won't go into the details, but basically we generate them automatically from the Wikipedia articles. For more details about the data collection pipeline, you can find them in the paper. But also one thing I would like to note is that all our questions, whether they're created or verified by raters, so even though we are really large scale, the data is quite high quality. In terms of statistics of the data set, so we collected around 250K pairs of questions and answers. And then by matching them to multiple images, we created more than 1 million image question answer triplets. And here are, again, some of the examples. And now for the last part of the talk, I'm going to go into some of the experiments we did with this data set because I think it provides very insightful information about how these foundational models work. So let's start with the fact that PALI, which is the state-of-the-art VQA model right now, outperforms all these CAT and reveal retrieval models on OKVQA. But then when we go to encyclopedic VQA, from 64% VQA accuracy, it goes down to 13%. It doesn't work at all on encyclopedic VQA. And not only that, we also ran other foundation models that are only LLMs, just language-based, and they perform even better than PALI, which means that just with the language prior of the questions, you can do better than such a big vision and language model. And this is really shocking because PALI, as it is right now, it's really the state of the art in most of the questions. It's a model that works really, really well. Then we created a few Oracle setups where we test some of the retrieval experiments, but having ground truth to check what is the upper bound of what these models could do if the retrieval mechanism was perfect. The first one, which we call this subject C, the idea here is that we provide to the model the name of the entity in the image, so that the idea there is to disentangle the effect of recognizing the entity in the image versus finding the right information about that entity in the model weights. And all these oracles, the way we implement them is all these models have a prompt, a textual prompt, and we add this extra information in the prompt. So for example, we pass the question, we pass the image, and if the context is the name of the entity, then we add the name of the entity in the context. What you can see here is when we add subject C, the entity name, things improve, but they are not so good. And this kind of highlights, again, the idea that it's hard to encode this very long-tail information in the model weights. We also provide, when we provide the knowledge base article as part of the prompt, the performance jumps a lot. And this means that this task can be solved if you have a good retrieval setup. And then you can also figure out the specific section of the Wikipedia article that you pass to the model, and it improves things a bit more. We then also provided a practical implementation of this setup, where we use Google Lens to identify the entity in the image, and then the results here, reproducing the knowledge base article and knowledge base section setup, are somewhere in between, meaning that more or less 50% of the times we can recognize the entity, but even then, it's not a solved research problem. And those results were only for the single hop questions. Actually, for the multi-answer and the two hop questions that I talked about, the models don't work so well. So we need a lot of more innovation to deal with these more complex question types. So to conclude, I presented Encyclopedic VQA, which is a VQA dataset on detailed properties of fine-grained categories and instances. Our dataset is truly difficult for standard foundational models, but adding a retrieval augmented component improves results. But yet, our dataset leaves significant headroom for future research. And I added the QR code of the website where you can find all the data and some of the baselines. And with that, thank you all for your attention.
Cool. Thank you. So the next presentation will be by Didac Suris. He's a PhD student at Columbia University, and he works on multimodal machine learning, video representations, and self-supervised learning. And he was also a visiting student in my group, and he's done a lot of really great work, and now he'll talk about ViperGPT, which was like a great presentation at ICCB. Thank you.
If I can, okay, awesome. Awesome, yeah, so thanks for the introduction. So yeah, I'll present ViperGPT visual inference via program execution for reasonings. This is joint work with Sachet and Carl. And same as Luis, I will introduce the presentation, like motivate the paper with an example that state-of-the-art visual language models cannot solve. And this example is just like, I made it up, but it basically says, how many muffins can each kid have for it to be fair? And it kind of involves like reasoning about the question. It involves obviously some visual capabilities. So you may be wondering, okay, how does this like GPT-4 vision perform on it? How does Blip2 perform on it? Or like any other of these? Like I haven't tried Poly, but you get the idea. So I asked them, well, and they just don't perform well. Like Blip2 says, like there's 2 muffins per each kid, which is not true. There's 2 per kid. GPT-4 Vision starts rambling and says that I would need to count the number of items, and unfortunately I cannot count, which is also probably not true because it has access to the image. If I prompted to say like, please provide a specific answer, like try to make your best guess or something, then it says that there's 7 muffins, 7 muffins on the cooling rack, which is also not true because there's 6. There's a total of 8 if you include the 2 here in the hands. So basically they don't really work very well. And obviously this is just an example, but I think it exemplifies much deeper problems, like I would say like foundational problems with these end-to-end big vision large language models, right? And these models, among others, they have some limitations that are like, they are not well suited for math and logic. Explainability is also pretty bad. Compositionality can be bad. They have hallucination problems and so on. So can we try to find different approaches to solving this kind of complex visual queries? And if we look at the image again, what we can see is like, let's think about what is needed in order to answer a query such as this one. Well, you first need to parse the question, right? So you need like some natural language capabilities. You need to reason about it. And then after you reason about it, you will see that what you have to do is you have to find all the muffins and count them. You have to count the number of kids. And you have to divide the number of muffins by the number of kids because this is what fair probably means, right? So there's certain operations here that can be very hard for end-to-end models, like counting. Like there's entire papers of like vision papers on counting, and it's hard. Like division, like mathematical operations, like those are also very hard for large language models, and they're not naturally suited for it because they kind of have to learn to perform all these operations implicitly during the training of the model. So what if we instead use explicit, like models that have been explicitly trained to perform these operations separately? And that's what we do. So in the ViperGPT framework, basically works something like this. We have, basically we have like these different models and we connect them through code like this. Given a query, the framework generates some code that when you then execute this code, the result of the output of the code is the answer to your query. So here, first we generate some code that first finds all the muffins, then counts the muffins by looking at the array of muffins and finding the length of the array. That does the same for kids. It first finds the kids, then it counts the kids, and finally it divides the number of muffins by the number of kids. It returns 4, which is the correct answer. And here what we did is we use like, you'll notice that we use like this method find. Well, this find basically calls an object detector. right? Like we have very good object detectors in the community. Like there's people whose whole career is just an object detection. Same for like object segmentation, same for like depth estimation and so on. So can we use those? And what we do is we use these and then we combine them through, Python code. More specifically, we use this like framework of synthesize then execute, where we define an API that basically provides the different functionalities that we have available to us, like the find method. Then we send that API specification to a code large language model, as well as the query that we're interested in. So those are the inputs to the code large language model. This code large language, we use Codex at the time from OpenAI. It is not available anymore. So I guess you can just use like Code Llama or like GPT-4, GPT-3 also works pretty well, it's just very expensive. Anyway, you get the idea, right? So this generates some code. And then this would be like the synthesize stage where you get the code. And then you have the execution stage where you execute that code and get the final result. Right? So the first part is the reasoning step. The second part is more of the perception stage. And this framework basically has a few advantages, or like a few good characteristics, which are, first of all, we reuse previous modules. Like we don't train anything here. Like I didn't run a single backpropagation step in the whole project, right? We reuse existing modules. We compose existing modules. Also, all of these work zero-shot. Again, I don't train anything. Like this is because of the zero-shot abilities of large language models, right? In this case, a code large language model. It is also interpretable because you can go and see the code and see all the steps that are being executed. You can see the outputs, intermediate outputs at every stage and so on. And also, it can use all the properties that Python has. So like Python has for loops, it has like logic, it has like other kind of libraries that you can use. You can use all of those. So those are the advantages of the method. And just like a little more explicitly about how this API specification works, this works like any other API specification that you have for a Python library, for example, like the PyTorch. You go online, the PyTorch library API specification, you have like the definition of you have the name of a function, like matmul, whatever. You have a definition of what it does, inputs, the outputs. You have a couple of examples of how to use it. So that's exactly how we define our modules, right? Like the module find, for example. We just say, oh, inputs a string, outputs an image patch, and so on. And then in the background, this is not, the API specification is given to the large language model. In the background, what you have is the actual implementation of the method find. That's basically a call to an object detection module, right? And then such that when you execute it, it finds all the muffins. Another example would be a function that we call module that we call compute depth. Well, it takes as input an image patch and outputs the average depth of the patch at a certain location, such that when then you execute it, it returns values at every patch. So in the background, again, like we just provide to the model the functionality, what it does, a description, and then in the background, we implement this calling the state-of-the-art depth estimation module, whatever you like. In this case, we use miras. I think there's something better already. Anyway, so that's the idea. And then at the end, you get this API specification with all of these functions that we define, which they're not that many, just like basic vision functionalities. But also, the large language model has access to all the Python, like, let's say, functionalities like control flows, like for loops, sorts, and so on, as well as any other libraries that people has used, because these language models have seen the whole GitHub probably. So anything that's in there, it can use to solve the question. So finally, I'll just show a couple of examples so that you get an idea of what this can do. So here I'll show an example that exemplifies how it can use knowledge, for example. Why can ViperGPT use knowledge? Well, because we define a module that's just a call to a knowledge base. In this case, we use GPT-3 as a kind of pseudo knowledge base. You could use some kind of connection to Google, whatever. So in this case, example is return the drink with 0 alcohol. ViperGPT generates a code that first finds all the drinks in the image. Then for every drink, it queries, it finds the name of the drink. Then it queries for that drink whether or not it has alcohol. And at some point, it finds the drink. In this case, this is gin. It says, oh, gin does have alcohol. OK, let's look at the next one. At some point, it finds Dr. Pepper, and Dr. Pepper doesn't have alcohol. And therefore, it returns the Dr. Pepper patch. So that's an example where it can use external knowledge. Another example would be spatial reasoning. This looks pretty simple, but it's not as simple as like you think end-to-end. Return the second man from the left, right? Like here it does is like, it finds all the men, then it sorts them from left to right, and then it returns the second man from the left. All of these are like zero shot. We didn't provide any single example that looks like this. I have more examples. I'll just skip a few of them. I'll just go to this one that I like. So you can also take as input videos. Let me just play this. So there's an example of just like this teacher like handshaking the students. And there's this query that's like kind of complex. Return the two kids that are furthest from the woman right before she hugs the girl. Okay, I will not go through all the execution of this, but basically the model understands this temporal reasoning, ideas that are required to answer the question, like before, right? At some point, it finds the hug, which is like the action that it has to find. Then it goes before, like it goes back a few frames, and then it detects, it finds the kids and so on, and eventually, well, I will not go through all the execution, and eventually it returns the two kids that are furthest from the girl. So there's like temporal reasoning capabilities as well. There's also this idea of adaptive computation where you can basically, it doesn't have to process the whole video, right? It just has to process the parts of the video that are important to answer the question. So that's also an interesting idea. And finally also evaluated this quantitatively on different data sets. We got very good results in like zero-shot settings and also for like referring expressions, visual question answering, also for video question answering and so on. And yeah, like we have more results in code and I guess access to the paper and so on the website. So that's it. Thank you.
Okay, right on time. So thank you so much. So the next presentation is by Victor Campos. I think looking for a computer. What do you need?
A laptop.
Oh, there is one here, or any laptop?
The presentation. Who has it?
Okay. Okay, so Victor is a senior research scientist at Google DeepMind, so now we'll have 3 presentations from DeepMind, just by chance. And he works on several aspects of computer vision and machine learning, and he's going to be talking about how to make playing Atari games 200 times faster than humans. So it's going to happen. Yeah, okay, we'll swap the order of speakers just to solve a few technical difficulties. So instead of Victor, Maria Bauza will talk now. She's also from DeepMind, so that serves the same introduction, kind of helps. She is also a research scientist at DeepMind, working on robotic manipulation. She got her PhD from MIT, working on robotic manipulation and introducing tactile sensing into manipulation, which was a really interesting PhD. And okay, let's
go for it.
Let's go for it.
Okay, there we go. Hi everyone, thank you Antonio for the presentation, and actually thanks a lot to all the organization here. I think it's amazing to see this happening. I'm very happy to be here. And I'm gonna do a bit of the robotic side of the vision. So I'm gonna present today a word that is called RoboCat. And the idea is that this is a self-improving foundation agent for robotic manipulation. I'm gonna go into what this means. But maybe before, the most important thing is that we work with big teams. This is amazing, I really like it, and it's important to just take a moment and acknowledge all the people involved in this project. So I think there is almost 40 people. This is just some of the faces of some of the people there. So let's go with RoboCat, where it comes from. So the first thing is that, let's say 2017 or so, we used to have one robot solving one task, and that was about it. We were putting all the effort in robotics to get data. And then we got transformers. I think most of you know about it. And after that, at DeepMind, there was some work called Gato. Gato is about, well, let's just have a transformer that can do a lot of things. One of those is robotics, but there's also going to be captioning, chat, and many others. And robotic people were like, oh, this seems useful. I think we should just do a foundation agent, something that can solve robotics, but let's say you give me some new data, and it doesn't take me too long to learn how to use it for robotics. And I just want to say that we are not the only ones. Other people, also from Google, did some other words, in this case based on language, that are Arti1, Palmi, But today we're going to talk about RoboCAD. So what is RoboCAD? The first thing is that this is going to be one single agent that can do many tasks, but also do them on many different robots. I think that's the key important thing. It's not just that now I have one embodiment, we're going to be able to deal with different ones. So many tasks, many embodiments, and also different data sources, different control frequencies, different degrees of freedom, which is something relevant when you think about robotics. The other thing is going to be adapting to new tasks. It's not like one single model that is never going to change. We want it to improve over time. And with that, what we are going to do is something that seems sensible. If you're in industry, you're not going to spend 2 months collecting data, but you might be fine spending 1 or 2 days collecting a few amount of demonstrations. So this is what we are going to show here, that with this small amount of demonstrations, you can still get to learn new tasks. And finally, there's going to be, again, this idea of self-improvement, which basically, by collecting this data, having the agent to practice a bit more, it can self-improve and get better. So with that said, how it works. So the first thing is the model. The model is a transformer based on Gato, but also with a VQGAN encoder. The only things that are worth mentioning here is that the VQGAN is pre-trained on many images. Not all of them are robotics. Of course, some of them are. And the other thing is that VQGAN allows us to just train things faster and iterate faster, which was an advantage. The other thing that is important is that how do we tell the robot which embodiment, which task? Well, for the task, what we provide is a goal image. So you can see here an image. There is 3 blocks, one on top of the other. So what we are asking the robot is, can you put these 3 blocks, one on top of the other? This is how we tell the robot what to do. Just take a picture. This is the setting that I want. Now go ahead and solve the task. And also figure out from what you're seeing what robot you're using, kind of. And the other thing is that this is vision-based. So we're going to provide visual images, also propio, which is basically where are the joints of the robot. And we are going to output actions. So you get an observation, images, propio, you pass them as encoders, you also get the action, you take the action, gives you a new observation. And this kind of sequence, this is a history, because if you want to think about velocities, you just need more than just the last observation. This is what we pass into the transformer to then output the next action. And now this is how we can close the loop. And then one more thing is that the output is actually something variable, so we can predict different lengths of actions, which again allows us to deal with different types of robots, different embodiments, different control frequencies. So with that said, let's just see how the training pipeline works. So to train this model, the first thing is that we're going to do kind of a loop. It's not just going to be we train it once, we're going to get new data and keep improving it. So we start with a large data set. Let's just make an assumption. Let's just say this data set is data. It has a lot of tasks, it has some embodiments. Obvious thing, we use a transformer, we train it, and now we have the first version of RoboCAD. The next thing is what I told before. Now let's just say I am interested in these few tasks that I would like the agent to be able to perform. So we go into the lab, we collect some demonstrations. Doesn't take very long if you have the right teleoperation system, which luckily in robotics now we do have very good teleoperation systems. Now we have a small subset of data. What happens then is we fine-tune the model. We don't need to retrain it. That would be very expensive. We just adjust the weights so that it can add this new data. And then I think that's the nice thing. We went from very small data on these new tasks to just, well, the robot is fine-tuned. It knows how to do them more or less. Let's make it do it a lot. But now that's kind of for free, just the robot on the lab collecting large amounts of data for this new task. And now we are closing the loop. All this data goes back into the large data set. And now, as you can see, you can keep iterating on this, keep adding new tasks. And I think the question is going to be, how is this going to work in practice? Well, we have a paper, so not too bad, I guess. But let me just show you a bit. Like the good thing if you work in robotics, and I wish many of you come to robotics, is that you have nice videos that you can show. So this is one of them. Here we're just specifying the goal image. So now we're going to take an image, and they say, OK, I want you to insert this gear into the gear base. And now we let the robot do it. Our robots are not the fastest. This is something that all robotics wants to do, but no one is really doing. But we're going to get there. But here you will see how the robot is actually going to insert the gear. So we are happy it did the task. This is another one. And I think you can see now is 5 degrees of freedom. Before it was 7. This is a different embodiment. Same model can solve this task. Now we are going to collect the image. The goal image is just put the red on top of the blue, something simple. What I want to show you now is that we can be reactive. And I think to me that's something very exciting about robotics. It's not one thing. Now we are going to perturb. We can close the loop. We can keep reacting. We keep improving from any errors that we are doing. And this is not a surprise. This is what the model is expected, like you would expect from any robot. You need to be able to recover from failures. And with that said, I just want to give you some quantitative results, because that's important. So one thing that was very surprising is that we started training with a small amount of data, keep increasing, and the question was, are we going to do better or worse? And it wasn't obvious. It turns out that for the training task, which is where the training tasks are in both the small iteration and the big iteration, kind of, the initial RoboCat, the final RoboCat, well, the results are these ones. We actually got better, which I think is surprising and exciting. It means that as you added more data, data was not too far away from distribution, so it was useful. Some of the IDS data were relevant so that you could perform better in your training tasks. So there is this transfer across new tasks that helps even the initial ones. So that's exciting. It means that the foundational agents, the more they learn, the better they get, even at the beginning. So this seems to point in that direction. And then another thing that might be obvious, but it's also exciting, is that when you fine-tune RoboCat, and then you add this data, and then you see how it performs, you actually get better results. So this is, again, very simple. If you fine-tune it just once, you get the lower bar. If you add then this data, and then see how RoboCat performs, you get something on the other side. So again, an improvement that to us it's very exciting, because it means that you don't need, maybe some videos here, you don't need a lot of data to really get good at some task. This is very simple, but we have others that are more complex. Still, I think this is nice to be able to put it into the right bowl. And with that said, I'm just going to wrap up. So RoboCat is this multitask, multi-embodiment, just to see the kind of how much, 250 tasks, about 4 embodiments. The thing that I'm more excited is the one that I'm not sure if it's showing. Well, that's a pity. Wait, how do I go back? Sorry, now I made a mistake. Well, now it's playing. This is the thing that I really wanted to show you. I'm very glad now. So this is a new embodiment. It has multiple fingers. It has many more degrees of freedom, 14 instead of 5 and 7. That's 5 and 7 is what we have in the training set. It has never seen 14, multi-finger a hand, about 500, 1,000 demonstrations, and it's able to do this task. It's able to do now more complex ones, but it's really promising that with just this a small amount of data, you get something that is reactive and that can really perform in our environments. And finally, self-improvement, as I was already mentioning. So that's it on my end. I hope everyone thinks about robotics. I think it's very exciting and there is a lot to do. Thank you.
Okay, great. So, Victor, are you okay? So now we are back on track. So Victor Campos, senior research scientist at Google DeepMind, working on different aspects of computer vision and machine learning, and he's going to be talking about Atari games. Yeah.
Yeah, right. Well, thanks, Antonio, for introducing me twice. I'm going to talk about this paper we presented at the Clear 2023, which is human-level Atari 200 times faster. So let me unpack this. It's actually split into 2 parts. So first of all, let me explain what we mean by human-level Atari. And for this, I need to go back to a paper of some colleagues of mine. It's called Agent 57, which is, I'd say, like the last agent in this like VQN family of agents. So it's of policy agents, value-based agents that use some sort of experience replay. And then they add a bunch of stuff. So it's a distributed version of the QN in the sense that you have a bunch of actors collecting data, putting the data in some replay, and then you have some centralized learner taking data from there, learning from the experience. Then it has some intrinsic reward to encourage exploration in certain tasks. It trains a population of agents. In this case, the population is a bunch of combinations of discount factors and intrinsic reward weights. So you try to learn all of them using a universal value function approximator, so single set of weights, learning key values for all of those. Then there's some meta controller that selects which agent you should be using to collect experience and also test time. And finally, they have some tricks like separating the weights of the Q networks for intrinsic and extrinsic reward streams, because that makes it easier to learn. So what do you get with all of this? So here you have results for agent 57 compared to mu0. mu0 is like one of the state-of-the-art agents in RL, and agent 57, despite it has a slightly lower mean and median human normalized scores across the 57 games, it's able to beat the human benchmark on all of them, meaning that it gets to above average human scores on all games. I think it's important to highlight the bottom row here. So some agents are very strong, like say on aggregate on these 57 games, because some games are relatively easy. If you do well on say 40, 50 of them, you get very, very high average scores, for example, when you average over the 57 games. But we want general agents that can learn everywhere, right? So if you just disregard the hardest tasks and get very high scores, that doesn't mean you're able to learn in any situation, and that's something that agent 57 achieved to do here, and that's why we care about this particular line of work. And then, after this brief intro of agent 57, I know it was a big bag, let me explain what we mean by 200 times faster and why it is important actually to learn faster here. So this is a plot we reproduced from the agent 57 paper. It is showing on the y-axis the number of games that are already above human score versus the number of environment steps you took in every environment. So you can see this kind of goes up, but you need to really take like almost 90 billion. So you need almost 90 billion interactions with the environment to achieve this. This, just to give you a reference, this is like 70 years or so of uninterrupted gameplay. That's a lot, right? And whereas this might be fine for Atari in the sense that Atari is very fast and very easy to simulate, when you get to more complex tasks, you need to be more efficient. You cannot be, simulating or taking so many actions in the environment. You want to learn faster. So what we do is, basically with a bunch of tricks I'm going to describe later, make this much, much faster. So actually 200 times faster. This small blue line here is our agent. We call it MIM. Let me zoom in. So we're able to essentially reproduce these kind of results, but using 200 times fewer interactions with the environment. So below 500 million interactions, we're already able to master everything in the Atari suite. Very similar information here, plotted in a different way. These are all the 57 games. Note there's a log y-axis here. This is showing how many frames you need for agent 57 in orange or for MIM in blue to surpass the human baseline in every Atari game. And we see massive speed ups, so across the board. So from around 10 times less data in some of the easier games up to, more than 700x improvement in some of the hardest games. So it's not just that we're able, obviously, to surpass the human baseline on all the 57 games, but actually this agent is also very competitive with other state-of-the-art methods that don't really care about all those 57, but actually, just they try to maximize mean or median scores across the 57 games in the suite. So maybe there's too much information here, but just what I wanted to say is we're very competitive with things like Muesli and mu0 in a very standard setting in the Atari benchmark, which is the 200 million regime. So you just get 200 million frames of a budget per game. You get to some scores, you average, take the median, whatever statistic you want for all these 57 games. Depending on whether we look at things like median that disregard more games, I guess, or mean, we are, on par or above some of these methods. So this generality doesn't come at the cost of, losing like peak performance on all the easier tasks, but actually we're able to do quite well across all of them. All right, so how did we get here? I didn't want to go into too many details and too many equations here because really it's a bunch of improvements that we have here. It's hard to say, okay, this is the one thing that make it better. Actually, it's just a bunch of them. So we classify them in 4 categories, and I will refer you to the paper. We can discuss offline if you want more details about this. But I'd say the main idea here is that you want to be learning as fast as possible and extracting as much juice as possible from every single transition that you have, because that's costly, while being very stable and being very robust, right? Especially in RL, if you try to move too quickly, you can break the policy completely, then you're lost, you cannot recover from that. But on the other hand, if you just try to be too robust, I guess you're gonna move too slowly, you won't be data efficient here. So one of the things that we do is to propagate signals faster. One of the things we can drop is the use of target networks for bootstrapping. This is something that was introduced many years ago in the DQM paper. So basically, you kind of freeze one version of the network because you're kind of bootstrapping on your own predictions to compute the targets for your losses. That means that information is not propagated very quickly because you're essentially freezing that information for a while. So we have some ways, some tricks to basically drop these target networks. I think that's a big deal here. By using a trust region mechanism. Then we have other new losses, like what we call a soft Watkins Q lambda loss. This helps you propagate information faster by having longer traces. So basically, you sum a bunch of rewards you see in the future, then bootstrap with your Q value. How many of those rewards you can sum and propagate depend on the degree of policiness. Sorry. And note that here, the degree of policiness is very high because we have, obviously, a replay. We have multiple agents with different intrinsic reward weights. You have multiple discount factors. So, all this data is mixed. You need to try to extract as much information as possible. And we achieve that through this new target that we introduced here. Then when you're learning so many different value functions for so many different agents, things can become unstable pretty quickly because, for example, you're using different discount factors, meaning that the range of the targets you're going to have can change drastically from the smaller discounts to the largest discounts, for example. You need some normalization strategies for this. So we introduce some normalization on the TD errors to deal with this. We train all agents on all the data. So this is something that didn't happen with agent 57. So you have 16 or 32 agents. If one agent produces some transition, you're only training the Q values for that agent in agent 57, which is a bit of a waste because that transition using off-policy learning, you could learn all your Q values essentially, and that's something we introduce here, but you need to be careful in how you implement it. We have also some deep learning improvements, like we use NFNets, that's normalizer free networks. We saw normalization strategies are a bit tricky to get right with this type of agents, so using an NFNet really helped here. We combine a few losses, and we also introduce a policy distillation mechanism that again helps us with a policy correction. We use it in the soft Watkins Q loss to have longer traces in the end that are still correct. Which of these help the most? Well, they all do to some extent. There's a lot of information here, but the legend is sorted according to the performance. So basically, you see meme, and we remove one component at a time. So for instance, you could argue that the trust region and the online bootstrapping are the ones that help the most. But again, only with those, you don't get to these results. You need almost everything, really. We have lots of ablations in the paper, so please have a look. And that's all. Thank you so much for your attention.
Okay, perfect. So the next presentation, the last presentation, is from Ferran Alet. He's also a research scientist at DeepMind. And he works in machine learning, in particular trying to improve generalization abilities of machine learning systems, and uses different techniques like meta-learning, learning to search, program synthesis, and so on. He did also his PhD at MIT, and now he's going to be talking about leveraging GNNs for skillful weather forecasting. So everybody has been within 10 minutes. Let's see if you can.
Thanks, Antonio, for the introduction. So today, I thought I would make a presentation on purpose for this conference that is a bit more social. I'm going to tell a story in 2.5 papers. One is from academia when I was at MIT, called Graph Element Networks. And then the second is made in two parts. The first one was the GraphCast when we submitted to arXiv. Sorry, it's in 2022. And then 2023, eventually we submitted to Science. 6 months it took from one to the other. They have roughly the same goal, but you will see that the type of contribution is quite different. So let's start with Graph Element Networks. So the inspiration is inductive biases, right? So designing good architectures, and we know that convolutional neural networks are a useful inductive bias because they exploit structural properties like locality and shift invariance that are satisfied in a broad set of tasks like many computer vision tasks. Then we know graph neural networks are also a useful inductive bias because they exploit structural properties again, like entities exist, and when you model them, they should be permutation invariant. And these are satisfied in a broad set of tasks when you model entities and relations. For instance, the original work was modeling graphs of web pages. Then we moved on to molecules, and finally physical interactions like bouncing balls. Here there is work by DeepMind, and as well here one from Antonio, so I thought I would put a deep learning badge, Deep Learning Barcelona badge. So now we are interested in spatial function transformations. So what is a function transformation? Imagine you have a metric space, in this case the sphere, like the Earth. You have an input function, like humidity and wind today. And note that this is a function that goes from x, the metric space, to y, the humidity. And then we have an output function, like the rain tomorrow. And this is another function that goes from x, the Earth, to z, the rain. And we want to map these two functions. We want to go from f to g. So we take an input function x to y, and we output another function x to z. And in practice, we deal this with examples, with samples from each function. So we are going to have sampled functions in January 1, January 2, and so on and so forth until maybe yesterday, of humidity to rain pairs. Now we have the humidity and wind today across many places on Earth, and our goal is to predict maybe the rain tomorrow in Barcelona or on other places on Earth. So how would we go about creating inductive biases for these functional transformations? So our inspiration was in partial differential equations. As you can see, this is a function that is changing over time. So maybe from the input time step, we could predict the output time step. And these partial differential equations, they look a bit like this, like the heat equation or the wave equation on the right or the Navier-Stokes equation. And we notice that there's a few conditions that they satisfy, right? You don't see the position in these equations, so that means that they're translation equivariant. We also notice that they're a composition in time of simple functions that are local. We use local differential operators. And notice that this locality is given by the domain. So we cannot use a CNN, which is usually a discrete, and also we have to adapt to the domain. If it's a sphere, then we have to map the locality, what it means to be local on a sphere. And third, we are time invariant. So if we want to predict over time, maybe we want to use an autoregressive model. We were inspired by finite element methods in physics and engineering. And you can see that basically they decompose the space in small regions, and they basically turn the problem into a graph problem. They have two very nice properties. The first one is that you can add less or fewer or more nodes. And as you increase compute, you're going to get higher accuracy. And the second thing is that if there are easier regions or harder regions, you can allocate more compute where it matters the most. So let's take a look at how this works. We have this metric space that I was talking about and input to output samples. And as it's usually in deep learning, we're going to go through a latent space. So we're going to encode this into the latent space, and then we're going to decode this into the output queries. The issue with this is that this is purely local, right? So for instance, if there is a hurricane in Cuba, we cannot inform the weather tomorrow in Miami. So what we do is we embed these latent codes via attention to a graph. We initialize the nodes of this graph. Then we do message passing to inform not just the particular region, but everywhere on Earth. And then once the message passing has communicated the information across, we are ready to then decode the information back and make the final prediction on the rain tomorrow, for instance. Weather was our aspirational goal on that paper, but of course, being academia, our actual experiments were much more disappointing. And we did basically the simplest PDE, which is the Poisson equation. Think about it as the boundary condition, which is how cold it is outside, and then we may have some heaters in the room. And you want to predict the temperature anywhere on that room. And so basically we use these graph element networks to predict this. Here it's 2D. We also made it in a sphere as well, because graphs can be embedded in a sphere. So what was nice about this work, it's basically we can, as I was saying, trade compute with accuracy. So at the beginning, with a small graph network, we would do it worse than the baseline. But with the same number of parameters, just increasing the size of the graph, we eventually did much better. And the second is that we control the graph. In previous graph networks papers, the graph was given to us by the user. Here, we are the ones creating the graph, so we can put the nodes wherever we want. In particular, we can optimize them via gradient descent, and that made the graph much more efficient. And so you can see that with already 49 nodes, we did the performance was very good. And keep in mind this number of 49 nodes, because we'll see the comparison to the new work, which is this 2023 paper that we did at DeepMind, about actually now solving, well, not solving, but like making progress in global weather forecasting. So our goal there was predicting surface and atmospheric weather up to 10 days ahead at 0.25 degrees latitude and longitude resolution. So as an example, here is the surface east to west wind. We have the surface temperature, or the temperature at 800 hectopascals. Think about it as some level of the atmosphere. But there is more than 200 variables that we were modeling all at the same time. And the intuition is that machine learning can learn approximate physics directly from data. Right now, weather prediction is made with actual physical equations that scientists have derived, but they are implicitly making approximations because the data is noisy and because the computation is finite. And machine learning maybe can discover new approximate physics that does even better than this. And we find out that, at least for deterministic weather, we seem to be doing much better than the previous state of the art. Notice that weather is pretty large by ML standards. In particular, if we compare an image to MNIST or ImageNet, a single variable in this ERA 5 weather data set is already much larger. But not only that, but in regular vision, we have only 3 channels, RGB. We have more than 200 variables that we have to model. And then we have kind of predicting kind of a video, right? Because we have to predict multiple time steps, in particular 40 frames. So that comes about every output example is roughly 35 gigs, which is roughly like a 30-minute movie. So that really puts a lot of constraints in the engineering. However, the model really looks quite similar to what we had back in 2019. It is autoregressive, right? Because we know the weather today is the same as the weather tomorrow, so we can apply the same function over and over again. And then the function essentially encodes the state of the weather, the raw variables, into a mesh. Then we propagate this information, and then we decode it back to the Earth to make the final predictions. One innovation that we made was this multi-mesh message passing. Basically, we had local edges, many local edges, and then a few global edges that had long-range connections. And one change that from kind of previous work is the raw scale of this problem, right? Right now we moved from 50 nodes to 41,000 nodes in the graph neural network. This gives very good results comparable to HRES, and lower is better here, and you can see that we seem to do about 10% to 20% better. Of course, as I was saying, there is more than 200 variables across many time steps, and here aggregates the results. You can see in blue, we do better than HRES on 90% of the targets. And the newest model, which makes some simple modifications, goes up to 97%. But also we're having real world impact. We were predicting cyclone forecasting, and the press initially was not very keen on AI for cyclone prediction. Then when the forecast went live in August, we started having a cyclone in September, and then Twitter basically broadcasted how the predictions were going. And basically it was AI versus traditional physics going on. And eventually AI, and in particular GraphCast, seemed to be able to convince the weather community, and in particular the original press article. Basically, to conclude, I wanted to kind of reflect back, similar reflection that Antonio made on, if you're a PhD student now, what's next, right? How do you contribute? Well, a thing to notice is that the focus for the first paper was more about the idea, thinking about new questions. What is a function-to-function transformation? How would you go about it? But the execution was poor. And I think it's pretty hard to compete with industry in that point. In contrast, the archive version, with clever engineering, you can really deliver on that and achieve state-of-the-art. And then finally, if you want to have science and real impact, it's about showing that the system can be deployed. And this really took about 6 months, and showing that you can have real-world impact and not just impact on a data set. Thanks a lot for your attention.
Okay, thank you so much. So now we have some time for questions. We have around 10 minutes, so I'll invite the speakers to come here. And so you have 10 minutes to ask some questions. So you can also take a microphone that you can share in case, you know. So I can start a little bit by saying that if I look at all the presentations, so everybody, all the presentations were amazing, and I will kind of group them into two. Ones that were like language with some vision, and then another set of presentations that were more grounded in robotics or weather prediction, playing games, something that is more like part of a bigger loop. So I wanted to get a sense from you about what do you think are the next things we should be working on? What is, do you think it's important to start thinking about closing the loop with things, or do you feel that it's still good to work in isolation in specific problems?
My answer is going to be very obvious. I think we should be closing the loop. I think we should be moving beyond, and I think there is a lot of cases and a lot of areas that would really benefit with all the expertise that we already have in computer vision and AI, and I think showing progress data really makes a huge impact. So I would definitely go for that. But I wonder if someone else...
I mean, I think it's both. Like, we need to close the loop for sure. Even like in my lab, we're not like a robotics or anything, but we're always like thinking about collaborating with other people and so on. But at the same time, when you try to close the loop, you figure out like, oh, this doesn't work. This other piece doesn't work. This other piece doesn't. Trying to solve all of these pieces at once may be hard, right? So like that gives you like some signal to what specific pieces you need to first approach separately, and then use them to close the loop. So it's like both at the same time, and there's like space for everyone and like to work on their own stuff.
Yeah, I want to add also that I would argue that maybe learning like tabula rasas from scratch every time is not the best idea. And I'm going to introduce back these LLMs, I guess, but they encode some knowledge. Obviously, they tend to hallucinate as well, so that's something we need to improve. But using those as priors, for example, I think it's super important. Like, you should see these, Atari agents on their first iterations. They are so dumb, really. Like, we need intrinsic rewards and things like that, just because, they do very stupid things. Language models, I think you could ask them, like, I'm seeing this, this, and that. What should I try next? What should I do? I think those are very strong priors, and probably this applies to many other tasks as well.
Another thing that I would add is that I think we need to look beyond and check for other problems, and in particular, many scientific problems. I've presented one, weather forecasting, but I think machine learning and artificial intelligence was initially very linked to human intelligence, and we were trying to solve whatever humans could solve and computers could not solve, right? And now, maybe AlphaFold, this weather prediction project that I explained, there's also algorithmic discovery projects. There's a lot of things to do in broader science, and it's just waiting to be impacted. And if you talk to people on those fields, they are really eager to use machine learning. And also, there is a different data efficiency reason, right? That you cannot use images from the internet to help you with weather forecasting or predict the structure of proteins. So really there's also a lot of algorithmic invention that is waiting to be done.
There's one question over there.
Hi, it's a question, I guess, for both Farhan and Maria. So when you were talking about the algorithm predictions and like weather forecast, and it was pretty accurate, that was good, but it was also like observing something that was happening. But then like, when I translate to the robotics project like Maria's working on, it's like, well, now you're not only like trying to like see what's going to happen, but you're actually going to do something about it. And the yields that you were showing were like 74%, which in industry, that would be still pretty low. And so like, how do you, what mechanism, what's the direction to like close that gap to like, I mean, I guess in industry, they'll be expecting like 95%, 98%. And like, so what does that look like? I guess I'm curious about that. Thanks.
I can go a bit more in detail on basically, your question is very related to the difference between our archive work and our science work. It took us about 5 months to show that our gains in the ERA5 dataset, which is basically a historical archive of data, would actually matter in the real world. The details of it don't really matter, but basically there was a different data distribution on the 8.5 data set than what you would see in operational systems making forecasts in the real world. Basically, weather takes observations real time, and you want to make sure that the data set is created with the same setting than the real world impact. And just showing that this was the case and making it work in the real time took about 6 months, so there is a big gap. And that's one thing that if you're working with closed data sets, you need to be very careful.
And I think the same goes actually for robotics. If you think about it, yeah, our performance is 70. How do you get it to 99.3 more nines? It's not obvious. And that's actually a big research question that I think we all need to think about. And you cannot just go with the same hammer, which is the large language models, because if you ask something to the large language model, it's going to give you a sentence, it's going to be perfectly right. But there's going to be another sentence that is also going to be perfectly right, just a slightly different words, and you can keep going. Like the notion of precision is something that is very much there in robotics. You need it for industry, you need it in your house, but you don't need it with some of the tools and some of the other applications that right now large language models are applying. So I would say this is a very big research question. I don't think it's obvious how do you get to these 999 levels, but we are looking into it, and I think most of us should look into it, because for many domains, science is the same, right? You cannot just say, oh, I kind of do it. You need to do it right. So it's an open research question, and I hope and I think there is more people looking into it right now.
Hi, this question goes to Farhan. In the presentation, you said that you could choose the nodes arbitrarily, or that you could learn them by gradient descent. Can you elaborate on?
Yeah, thanks for the question. So basically, in previous graph neural network work, the user was telling you, this is my graph I care about. Like maybe I have these 4 bouncing balls and they interact between themselves and the wall, or maybe I have this molecule which has these atoms and so on. Now with what I was calling graph element networks, and this doesn't apply to the weather work. The weather work used a fixed graph, but in graph element networks, the idea is you are the one constructing your graph. You basically say, I'm going to have a mesh of 4 nodes or 50 nodes, and then my nodes are going to be placed here, here, and here. And now you can use the XY coordinates of those points as parameters, and this is differentiable end-to-end as extra weights, if you think about it. And now you optimize performance of your system also back to the positions of the nodes. And if you do that, you eventually see that the nodes tend to move towards the hard places where you want to allocate more computation.
Okay, this question is also for Farhan regarding, I'm sorry about it, and it's just a matter of curiosity. It's nothing super technical, but you mentioned that at some point you used like multi-resolution, let's say mesh on the Earth, meaning that you pass messages from longer distances. And I was just wondering, maybe you didn't because it's something just for me funny. But did you perform any ablation study in order to see how long or what is the impact? I don't know how to formulate the question properly, but what is the maximum impact that you can get from farther distances? For example, if there's rain in Cuba is affecting to me, did you perform such analysis?
Yeah, that's a good question. So we kind of only did that. So basically we did, in the paper, there's ablation of using the entire multi-mesh and not using it. And we see that it helps in certain fields and not others, so basically smooth fields. Then later on, and this is still work in progress, we realized that we could drop maybe the last two, like the very, very long ranges. We don't know if it's like, it actually maybe hurts generalization actually. And also, if you think about it, the graph neural network is also making message passing steps. So you can actually reach very far away with 16 steps of message passing in a kind of more local network.
So we are now at the end. So I wanted just to ask one question, and reserve the last question for me, for Ginger and Didac, is that we see that all of the rest of the students here have gone into industry. What will keep you staying into academia?
I'm looking for jobs, so in industry, but maybe her.
Thank you for the hard question. So actually, I'm doing a PhD between a company and a university.
What made me state? I don't know. The freedom. The lack of resources. I don't know. Anyway, this is it. So thank you. Let's thank the speakers.
Hi. Please, don't leave. Just give us a few more minutes because we have a couple of announcements. So, 1 second. Yeah, we can take that one.
Is it working?
Yep. L'has d'engegar. Ho engegado i te l'enxufaran.
Hello. Yeah. Hi, everyone. So I'm Ignacio Sarasua. I work for NVIDIA. I in particular lead this initiative called the NVIDIA AI Technology Center. Some of you, particularly in the first row, you already know about it because we've been working together for the last year. So what we do is basically we help researchers scale up their research, either using our technology, but mostly trying to help you access the resources that you have available in your country, basically, particularly for Spain, so the Mare Nostrum and so on. So we try to help you scale up, use our technology the best way possible, and access these supercomputers. Very important, it's for free. So if you have questions about that, you want to talk, you want to see how we can relate, I'll be here all day, and so will be my boss. I'll introduce you later. Just come to us. Second announcement from my side, or second thing, is tomorrow we're giving a workshop on data parallelism. Probably some of you are already signed up. Important, it's at 9 a.m., not here in Campus North. I know 9 a.m. is a very bad time to go to the wrong location on a Friday before Christmas. So please make sure that you check the location before that. I think emails have gone through today reminding you if you have a place or not. Ask me questions if you haven't received the email or anything. But yeah, I think that's it from my side. Agatha?
Thank you. Okay, so last announcement is that we now have the lunch break, and we have lunch served here in the same room behind this wall that we had the coffee break before. And then the next oral session is starting at 3 p.m. So enjoy the lunch.
Hi. Okay, we're about to start session 3. Okay, so yeah, okay. So we are on air now. So thank you all for coming back after lunch. Hope you enjoyed. My name is Xavi Giró. I'm one of the local chairs for this edition of the Deep Learning Barcelona Symposium. And I'm happy to be, an honor to be here with Marta Ruiz Costa Jussá, who will be the session chair for this session. So first, let me tell you a bit the short bio about Marta. So Marta is a research scientist at Mech.ai since February 2022. She received her PhD from the UPC in 2008. Her research experience is mainly in machine translation. She has worked at LIMSI CNRS in Paris, Barcelona Media Innovation Center, Universidad de Sao Paulo, Institute for Infocom Research in Singapore, the Instituto Politécnico Nacional Mexico, the University of Edinburgh, and the Universitat Politécnica de Catalunya, co-leading the MT UPC group. She has received an ERC starting grant and 2 Google Faculty Research Awards. Recently, she has participated in the No Language Left Behind and Symbols projects. She has published hundreds of scientific papers, and she is co-author of the novel in terms of book, El somni de la Mia. So welcome, Marta, to the symposium.
Thank you, Xavi.
It's not the first time that you are here. You were already a keynote here some years ago. And I would like to have some questions for you. So the first one is about this latest point in your bio, which is this book, El somni de la Mia, so that's Mia's dream. Why did you, so maybe you can tell us about the book. Why did you write this book? What is this book about? Should we get that in our Christmas list?
Yes, please. Well, the book is the result of a project, of a 3-year project, okay? And it came with a need to explain to the young people and not so young what is behind the marvelous things that you all do, okay? Artificial intelligence. And the thing is that the general public does not know what is behind the models. And well, it came, the book came out after ChatGPT, okay? So I think that the timing is right, because right after that point of inflection, everybody started to be an expert in artificial intelligence, no? And it's like everyone can speak about football, everyone can speak about politics, and everyone knows about. And then I have never had that feeling because I don't understand about football, no? But now I understand professionals who listen, no? And when you hear those people talking about artificial intelligence and thinking that they know everything, so yeah, the book is to solve this need, okay? So it's like, what are the limitations of our systems? What should we be scared about? And it basically puts you in a wall of fiction, okay? So basically vectors are the roles in the characters in the book, okay? And we explain backpropagation, perceptron, and so it's just to do that, okay, to arrive to the general public.
Yeah, you convinced me, so I'll add that in my Christmas list, okay, for Santa Claus or the 3 wise men. So another question I have, so you've been working so long on machine translation for a long time with deep learning and before without deep learning. And for now, for me, it seems like this seems to be solved. So this year you were involved in a project that was chosen about the 200 best inventions by the Time magazine, right? And so is it solved? Is there anything else to do in machine translation?
There are plenty of challenges. I mean, we have been working on progressing on this, but I mean, the entire community is working on this, no? So there is a huge, very relevant groups in the world working in machine translation. So there is great progress. We have, in my case, the projects that we have presented. So we have worked in machine translation system from text to text, working in 200 languages. And we have worked in speech-to-speech translation, working from 100 languages to
like 40, okay, and the latest version of this system that we have launched, it's able to do translation streaming real time, and also with expressive, keeping the expressivity, okay, so keeping your voice and the prosody in the translation, okay. You can try these models online, they are open, and you can judge yourself the quality of it, but you can see the challenges. No? So for example, one very important thing is that translation is different from language interpretation, okay? So for us, our North Star would be like those amazing people that are translating real time in the European Commission, and then they have this I mean, I don't know if you have had the opportunity to be dubbed or translated by a human interpreter, but it's like me, that I'm not a native speaker in English. When I speak in Spanish and they have dubbed, interpreted me, it's like, wow, come on, did I say that? Because they have the capacity of improving your speech. Okay, and suddenly you seem like a much more communicative person. Okay, so for example, what's the challenge for me? It's that our systems translate; they do not interpret. They do not do this abstraction and improving the. For example, that's one thing. Another thing is sign language. Okay, you are an expert on sign language. Come on, Xavi. So what are the challenges? I mean,
my students are probably.
So sign language is we are very far from that, and these are just a few things. So no, there is a long way to go.
Good. So we're gonna still have papers here in the symposium about machine translation for a long time. Then my next question is related to your previous keynote. I think it was 2018 maybe, or 19 probably. In Telefonica. I think that was probably the first time that I heard about this problem of the bias in data. So we have our data, we train our machine learning models with this data, and then we see that our machine learning models, they have biases, right? But okay, we need the data to train the models. This data has bias, but we don't want the bias. So how can we fix that?
Yeah, this is another challenge of our models, no? So I mean, our models just inherited all the biases that we have because we train with data, and at some point when you say, okay, it's data only, we have several works that prove that our models also amplify this bias, okay? So it's not just about data. The fact that we reproduce stereotypes, we amplify stereotypes, that this is one problem that it's not solved. We are still showing working on uncover the biases and the unfairness that our models have. Okay, so just one thing is uncover them, quantify them, and then mitigate them. Okay, and yeah, in this direction, there is plenty of things to do. But one thing that that I'm optimistic is that, okay, so we as person, we come with our own biases, and it's very difficult to reset them. I mean, yeah, you can travel, you can live in different countries, and you can see different cultures, but your bias, it's so much inside you. But for machines, we can always retrain them with other data, no? So if we come up with a way of balancing data, better representing all cultures, all nationalities, all, I think that they can be much fair than any one of us.
Okay. So thanks a lot. That's going to be the end of the conversation. So please, let's give a big round of applause for Marta. And now I give the word to you because we kick off the session. I have it here, Marta, if you want, for the first one.
Sorry about that. Okay. Sorry for this interruption. Our first speaker is Adrià Mayol Ragolta. Adrià is a PhD candidate at the Department of Computer Science from the University of Augsburg, working at the Chair of Embedded Intelligence for Healthcare and Wellbeing under the supervision of Professor Björn Schuler. Did I say it right? My German is terrible. And well, Adrià is going to present us his work on face mask type and coverage area recognition from speech. Thank you, Adrià.
Thank you, Marta, for the nice introduction. So yes, I'll be talking about a new dataset which we named the mask flick corpus, which is about face mask type recognition and coverage area from speech. So first of all, COVID changed our life, as we all have experienced. What we realized is that face masks are an effective instrument to help us control the spread of COVID-19 and also to reduce the number of deaths. However, we have seen a lot of people not wearing the mask comme il faut. So for instance, wearing the incorrect type of mask or just wearing it with the mouth covered and the nose outside and these kind of things. So this observation of the reality made us come up with this hypothesis. So can we develop AI-based models able to recognize different face mask types and their coverage area from speech with computer audition techniques? So before going any further, let me introduce my co-authors, Neil Ubach, Shuo Liu, Anton Badlina, and Björn Schuler. So this is the agenda for today. I will start with a brief introduction, presenting a bit more in detail the mask flick corpus, then talking about the methodology, the preliminary experiments that we run on this dataset, and finally I will conclude my presentation. So the development of face mask monitoring tools can contribute to the spread control and the mortality rate reduction of airborne diseases such as COVID-19, but not only for COVID, so for any other respiratory-related disease. In the literature, there are a couple of datasets already available. So one is the mask dataset, which contains only speech samples from participants wearing a surgical face mask. This dataset was collected before the pandemic, and therefore this was, back in the time, only the surgical face mask was considered. Newer dataset was this Brave mask dataset, which was collected after the outbreak of the pandemic, and it already included speech samples from participants wearing different types of face masks, such as the tissue mask, medical mask, FFP2 and FFP3 protective masks, respirators, and protective face shields. However, what we learned is that not only the face mask type is important to control the spread of airborne disease, but also wearing the face mask over the mouth and the nose is a very important aspect. So this is what we try to do, or what we try to capture in this new data set. So it stands for the mask Augsburg speech corpus using FFP2 and surgical mask with the airways covered halfway and completely, mask flick for short. Here you have a QR code to the Zenodo repository of the data set. It was collected using a Xiaomi Mi 10 smartphone to try to stimulate the research using wearable or like data collected with wearable devices. It contains 2 hours and 27 minutes of speech samples from 30 German participants. In this case, we did an effort, as Marta said before, to try to gender balance the dataset. So it included 15 females and 15 males as well. And the voice of the participants was recorded under 5 different conditions. First of all, without wearing any kind of mask, then with 2 different types of face masks, the surgical mask and the FFP2 mask that you can see on the right-hand side of the slides. And then also, it was recorded and using or taking into account 2 different coverage areas. So covering only the mouth or covering both the mouth and the nose of the speaker. This dataset was new. This is a task that was not previously explored in the literature, and therefore, in order to investigate whether the computers were able to detect these issues, we tried to record the dataset in a very controlled environment. And for this, the recordings took place in a quiet room, and we tried to maintain the speaker smartphone distance as close as possible to try to avoid or neglect this variable from the data collection. And we proposed to the participants 2 different tasks. One was a free speech task. The other one was a guided speech task. So for the free speech task, we showed a picture to the participants and we let them describe what they saw there. And for the guided speech task, we provided some sentences that they were supposed to read aloud. In this kind of data sets, let's say, where you have one stimuli, let's say, but you try to record several conditions, one problem usually is like this habituation effect. And in order to minimize this habituation effect, we created 5 different but yet equivalent exercises for each task. And also what we try to do as well is to collect each tuple of picture and set of sentences using the 5 conditions in order to try to make sure that the dataset was as balanced as possible and to try to avoid a single couple of data to be recorded in a specific condition and these kind of things. And then what we did is like we took our recordings, we segmented them in fragments or segments of 1 second length. And here you have the numbers of the 1 second length segments that were included in the dataset. So we had these 5,600 for training, this 1,500 for development, and this 1,700 for tests. And we provided these training and development and test partitions in order to encourage the research community to follow them as well for reproducibility purposes. Of course, as this was a new problem, we tried to explore different representations of the data, and these were the features or like the representations that we consider. So first of all, we started with the IG Maps feature set, which is a very well-known feature set in the effective computing literature, and then it's also a 1D representation of the data. And then we also extracted the MEL spectrograms and the spectrograms of the audio samples, which are to the representation of the data. To model the 1D features, so the IG Maps, we tried 3 different models. So we started with a linear kernel-based supervector classifier. Then we also implemented a radial basis function, kernel-based supervector classifier, and also a simple neural network classifier, which was implemented using just one fully connected layer. And in order to model the 2D features, we implemented the full network, which was composed of 2 main blocks. The first, what we call the encoder part, and then the classification part. The goal of the encoder is to learn some sort of embedded representations from the input data, while the classification block takes care of the actual classification of the data. So for consistency purposes, we implemented the same classification block as the neural network classifier that I've previously defined. And then we tried 2 different encoder blocks. So the first one was a convolutional neural network, which we trained from scratch. These are the acronyms that you will see in the table of results later on. And then we also wanted to include some sort of transfer learning paradigm here to explore its performance. And we picked up this ResNet 18 pre-trained model. But we, of course, took out the last layer, and we explore this architecture in 3 different scenarios. First, using the architecture by default, let's say, but initializing the weights at random and training it with our training routine. Then in the second scenario, we froze the pre-trained weights of the network, and therefore we use them as pre-trained. And finally, we fine-tuned the ResNet 18 with our data. So some results from our experiments. So because of the nature of the dataset, we can investigate the problem from 3 different perspectives. The first one is the face mask type recognition, so a 3-class problem here. The second one is the face mask coverage area recognition, also a 3-class problem. But then a more complex problem, which is the face mask type and the coverage area recognition, which is a 5-class problem. So starting with the face mask type recognition, the weighted average recall, which is the metric that we use, it's set at 33.3% as the chance level. And what we can see here is the best score was obtained with the RBF kernel and with the IG Maps, almost 49.3%. For the face mask coverage area recognition, same chance level here. In this case, however, the best performance was obtained with the neural network classifier, also using the IG Maps, 47.8% of unweighted average recall. And with the face mask type and coverage area recognition problem here, the chance level goes down to 20%. And in this case, the IG Maps feature set modeled with the neural network classifier obtained the best result of 35% of accuracy. So to briefly conclude my presentation, so here we introduced this MathFlick corpus and we provided some baseline results. What they indicate is a suitability of the IG Maps feature set for this task. And these are the performances, or like the best performances that we obtained in the 3 problems that we investigated. And yeah, here you have the QR code if you want to download the data from the Zenodo repository. And answering our initial hypothesis, yes, the preliminary models trained are able to recognize the face match type and their coverage because the results are better than chance. And therefore, the next step is to try to improve this performance. So thank you very much.
Thank you, Adria. Just in time. Now our next speaker is Ioannis. Ioannis Siamas is a PhD student at the UPC, currently doing an internship at Dolby, and he will be talking us about segment, maximizing the utility of speech translation data with segmentation-based augmentations. Thank you, Ioannis.
Thank you, Marta. Let me see if this works. Yeah, cool. Okay, so let's begin with an introduction. Oops, microphone, yeah. Yeah? Okay, okay, now it makes sense, yeah. Okay, so what is end-to-end speech translation? It's the task of translating speech directly to the target text without an intermediate transcription. So there are several advantages compared to the traditional cascaded approach, where we use an ASR system and then an empty system. And these are no compounding errors, less information loss, applicable to spoken-only languages, more compact architecture, and faster inference times. But there is an issue, and namely data scarcity. So the task of speech translation has a lot less data than ASR or MT, and that makes it difficult to train competitive models. So we make the interesting observation that most ST corpora are based on documents, but only a single and static sentence level version is provided. And this is potentially hindering the utility of the speech translation corpus, which is already limited. So our solution to this is Segueix-nos, which is an in-dataset data augmentation technique, and works by generating alternative sentence-level versions by resegmenting the document-level examples to different plausible sentence-level examples, and then by using alignment methods, we can get the target translation. So we'll give some brief background. So this is how how the dataset provides the sentence-level examples. So in the top, you can see the speech transcription and translation of a document-level example. So these are usually long TED Talks, for example, at 20 minutes. And then we split transcription and translation on strong punctuation to get sentences. Then we align them, and then we do an audio alignment step to get the segment boundaries, which are the start and end points of every segment within the speech. And this way we get like M sentence level examples. It is provided with a dataset, and this is the single and static level view that I'm talking about. Another important thing is audio segmentation. So this is very useful in realistic speech translation scenarios where no tested segmentation is available and automatic one has to be inferred. So we'll be using SAS, which is a classification model based on WAF2VEC2, and use a segmentation algorithm that splits the audio into segments of min and max segment lengths. And the different min-max parameters will result in different plausible segmentation, and this will be very important for our method, as we will see. Okay, so let's dive into the methodology. So in the bottom, we can see the sentence-level examples provided with a dataset. So these are M examples. And on the top, we see the alternative sentence-level examples that we want to obtain. So the first step is to do segmentation with SAS. So we forward the speech through the classifier, and then the segmentation algorithm using L is the min-max parameters, can provide different plausible segment boundaries. Then we do a step of force alignment. So we get the timestamps of each word in the transcript, and then we can map them back to the new segments within this range. And then the final step is to get the target text, and this is done with an empty model, which basically for us it works like an alignment model. So we overfit it in the train set in order to recover the target translation for this specific example. And this is how we obtain K different sentence level examples for this document. And then we can repeat this process because the segmentation algorithm can provide different segmentations for different parameters. We can provide it many times, and this can give us many different sentence level views of the same document. A bit of experimental setup. So we will be testing our method in various different speech translation datasets that cover different aspects of the data, like English source, different directions, the resourcefulness of the data, and whether it's originating from documents or it's by default a sentence level. Most of our experiments are done with standard baseline of speech-to-text transformers with 32 million parameters and ASR pre-training in the encoder. We will also be implementing a very strong baseline based on WAF2VEC and MBERT with 800 million parameters. So when we're using SegAugment, we provide 4 different synthetic level versions of each document, and we just simply concatenate it to the original data. So let's discuss the results. So first we test MASC with the standard baseline. So these are BLEU and CRF2 scores on MASC test. And we provide the results with a FFERSEC ST baseline and a baseline that we implement. This is a speech-to-text transformer. And then by adding the synthetic data, we can obtain consistent and significant gains that are 2.4 BLEU on average. And this shows the general applicability of our method. Then by doing an extra step of including the SegAugment ASR data in the pre-training of the encoder, we can obtain a slightly better performance, but in other scenarios, this is more important. So next, we test how good is this data augmentation method when we have a very strong baseline. So here you can see on the left on English to Spanish and English to French of MASC, previous state-of-the-art models, and the baseline that we re-implement. And this is without SegAugment. So by using SegAugment, we can actually surpass the previous best, which is nice. But the important thing to note here is that the method, the synthetic data are still important in the presence of very large amounts of data, as manifested here by WAF2VEC and MBERT. So this is a nice finding that our method is still useful in very good quality models. Next, we test low resource speech translation. So this is Spanish-English, Portuguese to English, and Spanish to French. And it's important to know that Spanish to French only has 4,000 examples. So this is very extremely low resource. So by using SegAugment, we can obtain some nice improvements here. And well, this is kind of expected because data augmentation is better when we have fewer resources. But it is important to note here that the method is robust because this is an in-data set augmentation method. So we are dependent on the amount of data to have better synthetic data. So this shows that the synthetic data that we give to our models are of very good quality, even in the presence of just 4,000 examples. Next, we test how good is our method on a sentence-level corpus. So this method is tailored for document-level corpora, like MASC and MTEDx. So here we tested on COVOST on English-German, which is just sentence-level examples. And what we do is we take the sentence-level examples, which are already short, but we segment them to even shorter examples. And then we provide this data again to the model. So we can see that the method is still effective and it brings significant gains to the baseline. Finally, we test our method on the realistic scenario where the testset is not segmented and we have to infer a new segmentation. And usually there is a loss in translation quality. And this is the realistic scenario. And ideally, we want to bridge this. So SegAugment actually bridges the training inference segmentation mismatch because now in the train set we already have examples that have similar segmentation as the one that the test set will have. And as we see here in this rather complicated table on the right, so we can focus maybe on the average in the bottom. So we are comparing for each language pair 3 models. So the baseline, no data augmentation, then data augmentation, and then another step of providing a special tagging to the model to be aware of from which kind of segmentation does the example come. And as we see in the average, the baseline when evaluated on the manual, the gold segmentation is losing 1.6 BLEU when evaluated on an inferred one. Then by adding SegAugment, we get an improvement in both scenarios, and we close a bit the gap. And then by, again, using the special tokens, so basically to prompt the decoder with a segmentation that we want, we can almost bridge it. So we can get 27.3 comparing to the manual segmentation with 27.4. And in general, the takeaway is here that if we see the individual languages, there are a couple of them that we can get a better performance on an automatically segmented test set. And this shows that the manual segmentation is not the gold standard, and we can even get better segmentations. So maybe this could be pairing different contexts together, and maybe being able to translate the article in another language. So this is an interesting finding. And finally, we analyze the reasons behind the effectiveness of our method. So the first one is contextual and positional diversity. So examples that are presented inside different contextual windows at different absolute positions. And this gives more variability and generalizability to the model. Then there is length specialization. So we provide to the model many more examples of extreme length, so very short or very long. And this gives an advantage to the model when translating very long examples, for example, in the test set, that otherwise wouldn't have seen many of them in the training set. And finally, there is an effect of knowledge distillation because of the machine translation model that we use to generate the target translations. So just to close off with some conclusions, we presented Segueix-nos and demonstrated its effectiveness across multiple data sets, language pairs, and research conditions. We can obtain state-of-the-art results when paired with a strong baseline. There is applicability in standards-level datasets, and we can completely close the gap between the manual and automatic segmentations at inference time. And we should jump to the final slide, but well, there is a thank you note at the end, but it doesn't want to go. Thank you very much for your attention.
Ioannis, remember that you can keep your questions for the end of the talks, okay? So please note them and then ask questions. I encourage you not to miss this opportunity. And our next speaker is Gerard San. Gerard is a researcher in artificial intelligence and telecommunications, currently pursuing a PhD studies in sign language processing at the University of Zurich. His areas of expertise include language modeling, speech recognition, and predictive algorithm. Gerard is going to talk us about analysis of acoustic information in end-to-end spoken language translation. Remember, Gerard, that you have 10 minutes. Thanks a lot.
Thank you, Marta. So, okay, sorry. So this paper, so the motivation of this paper was to understand how end-to-end models extract acoustic information and to see if there is any benefit of the transfer of acoustic knowledge between encoder and decoder in end-to-end speech translation models. So, as a paper goal would be understanding the flow of acoustic information in these models, and to be more concise, our objectives would be understanding the encoder's role in processing acoustic features, examine the acoustic information significance and transfer within the model, investigate the effect of the downsampling layers on learning acoustic features, and finally observe the correlation between the semantic domain and the speaker labels in some dataset like MASI. So our proposed methodology is built upon the speech-to-text transformer, which has been presented by the last presenter. And we came up to use two proving tasks in order to track the speaker information, which are the speaker classification and the spectrogram reconstruction. Okay. So we also wanted to try to test the robustness of acoustic information, forcing the model to eliminate the less relevant information via the use of bottlenecks. So we will do this also. And going to the experimental details, we use MASI dataset and covers2 dataset, both in English to German directions. And for the robust dataset, we had to create a test split from the training split, because the test split do not have enough utterances per speaker to train any speaker classifier. And we also created a synthetic test split from the MASI dataset, where all the utterances are spoken by the same voice, which is made from a TTS model. So our architectures, our baseline, as I mentioned before, is a speech-to-text transformer from FirstSec, and then we train also a deeper model, or a variation of the baseline, which is deeper, and a less deep variation of this baseline. And regarding the proving task, the spectrum and reconstruction is done via two deconvolutional layers, and the speaker classifier is a single layer perceptron. And finally, the bottleneck are two feed-forward neural networks with a Latin dimension, which is the half of the normal dimension of the model. So going to the analysis, I would like to summarize the key relevant points of the paper. So the first thing that we see is that the convolutional layers project the input representation to a highly rich acoustic representation space in which speakers classifiers achieve more than 90% of accuracy. And this accuracy is maintained along the encoder layers until the last encoder layers where the speaker classification accuracy decreases until around 50% of the model, which this suggests that the first encoder layers learn to decluster the acoustic content, and the last ones eliminate the less relevant acoustic information for the final objective. And then moving to the decoder part, we can see that there is a discrepancy between the models trained in the different data sets. So the one in Cobos goes from almost 50% at the end of the encoder layers to 20% at the beginning of the decoder layers, which at the end is bigger than a random classifier. So this reinforces the idea of that the decoder needs acoustic information in order to improve the metrics of the task. So reinforcing this idea of the beneficial from this transfer of acoustic information between encoder and decoder. And then in the must-see, we do not see almost any kind of drop of accuracy, which highlights a highly correlation between the speaker labels and the semantics domain of the speaker. So moving to the acoustic information flow analysis, and also, as we said in the last slides, convolutional acts as a feed-forward neural network that over-parameterizes the input representation, and we tried to train a model without this over-parameterization, which ended up with a drop of performance of 1.8 points of Pleo. So the mean square error goes from the 0.1 in the beginning of the encoder and increases exponentially until 0.434 by the last encoder layer, which is the same tendency that we observe on the speaker classification. And then if we have a look to the spectrum and reconstructions, we can see how the silences are preserved throughout all the encoder layers, but by the end of the encoder, there is a significant loss of detail in this acoustic space. So as a key takeaway, the convolutional layers and over-parameterization plays a crucial role on learning acoustic features. Then we can see the same pattern that we have been seeing before in deeper models, but if in less deep models, we can see how the amount of information in the encoder is very few. So this translates in a significant loss of performance. So this also reinforces the idea of the encoder being responsible for initially declustering the acoustic information and then removing the less relevant part. And the models that do not achieve to do so suffer from a significant loss in performance. Then moving to the bottlenecks experiments, we can see how the acoustic features, the amount of acoustic information decreases in the specific layer where the bottlenecks is situated, but the models try to recover this highly acoustic representation space in the subsequent layers. And models that do not achieve to recover at least a 50% of amount of acoustic information suffer from a drop of performance from 1 to 2.16 points of Pleo. This suggests that this is the need of a transfer of acoustic information between encoder and decoder. But this pattern is not seen in must-see. As we have seen before, the accuracies in the decoder are pretty high. So this is experiment during the training phase, so as more trained, more to the right. So we can see how the model struggles to classify the speakers until the 20% of the training progress. Then we can see that overall, all the encoder layers have achieved high accuracies in order to classify the speakers. And we can see also how, as more the training progresses, the accuracy in the last layers of the encoder decreases, which indicates a shift towards a more semantic representation space. So this also reinforces this idea of the encoder that we have been telling in previous slides. And finally, of this analysis, we have seen in the decoder for the MASI that the accuracy was very high, which this highlights this high correlation between the semantics domain and the speaker labels. So we wanted to analyze this via two experiments. The first one was using this synthetic MASI, which all utterances were spoken by the same synthetic voice. And then we achieved speaker classification accuracy of 23% by the end of the encoder and almost 30% by the end of the model. And we also train a TF-IDF coding over the test translation, and we achieve a classification accuracy bigger than 22%. In both cases, in both experiments, the classifiers do not have any kind of acoustic information to classify the speakers, so that means that predictions were entirely based on semantic information. So moving to the conclusions, so we are the first to highlight this encoder role as first the clustering, the acoustic information, and this shifting towards more semantic representation space. Then we also have showed this beneficial transfer of information between the encoder and the acoustic information between the encoder and the decoder in end-to-end models, and how the models tries to recover this acoustic information even after trying to delete it via the use of bottlenecks. We also have seen that convolutional layers are not only important for downsampling layers, but also to perform this over-parameterization that projects the input representation to an acoustic-rich representation space. And finally, we highlighted the need of finding data collection techniques whose labels do not rely in any dependent of semantic domain or anything label different labels of the dataset, and this would ensure that our encoder does not rely in any non-acoustic information, and then this would improve generalization of the model. So as a key takeaway, we try to provide valuable insights for future research on spoken language translation analysis. So thank you very much.
Thank you, Gerard. Our next speaker is Pedro Ramoneda. Here, Pedro. Pedro studied piano performance and computer engineering in Zaragoza. Following this, he pursued a master's degree and is currently working on his PhD thesis at the UPF in the music technology group, focusing on artificial intelligence and music with Xavier Serra. Pedro is going to present predicting performance difficulty from piano sheet music images. Thank you, Pedro.
Thank you to you. Okay. Hello, my name is Pedro Ramoneda, and today I am going to talk about our advances in estimating piano performance difficulty this year. My PhD thesis tries to answer to the question, can I play it? Let's say I am a beginner piano student and I want to find my next piece to study. And I have these two options. is the second. Who thinks the first piece is easier? Can I see the hands, please? Okay. Actually, more or less, have the same difficulty, because estimating the piano performance difficulty is not easy as classifying cats and dogs. Okay. I'm sorry. Okay. Okay. Music performance involves multiple dimensions. For example, the second one involves more hand movements, but the first ones, on the other hand, requires much more expressive maturity. On top of all of these dimensions, there is also one more challenge, the subjectivity, because what is difficult for me can be very easy for you. But luckily, most music schools actually agree on more general patterns on the issue of difficulty, which implies that the task is not subjective as it seems, which is a good thing, and implies that it can be solved with deep learning techniques. Okay then, what do we mean by multiple modalities? In the first example that I showed you, in the first slide, you can listen the audio and also see the sheet music, which corresponds to the 2 dimensions here, audio and images. However, there is even a more informative modality for piano difficulty estimation, which is the machine-readable score. As you can see here is the first one. Ideally, it would be great if we had machine-readable scores, because in that modality, the information is fully accessible in the machine. However, collecting data in this format is not always possible. The data availability improves as we go in the image and audio direction, but the information is less useful for our task, as you can see in the arrows. Then we go to the first paper, which focuses on machine-readable modality, accepted for publication at ESWA. To address the lack of data, we present a novel data set, Can I Play It? Pronounced CP, a machine-readable piano score data set with difficulty annotations obtained from a renowned publisher. The data set is created by pairing public domain scores with difficulty levels from this publisher, then reviewed and corrected by an expert pianist. It has 29 composers, 9 ranking levels, and 652 scores, and is much larger than the previous dataset proposed. As a second contribution, we get inspiration from the musicology definition of what is music performance to design this research. We generate 2 other modalities with existing deep learning models from the machine-readable score. The physical gesture is generated with one deep learning model, and the expressive sound is generated with another deep learning model. From the 3 representations, we fine-tune models which combined predict the difficulty of a piano piece. We have conducted multiple experiments to establish and promote the task. We use this simple recurrent neural network model with attention. We also worked on modeling the task as an ordinal regression, because as you can remember, we are trying to predict like rankings of difficulty. And then we proposed several metrics for the task and conducted experiments with multiple losses. Finally, a simple ordinal regression loss shines over the rest of loss that we have tried. Finally, the prediction combining multiple dimensions works better with an ensemble than other future fusion techniques that we have tried. The improvement of combining the 3 dimensions is significant, with a 39% of macro accuracy in 9 levels and a 1.1 points of macro mean square error. But yeah, machine readable is not a real scenario for music education industry, as we have said. That is why we present this paper presented at ISMIR. ISMIR is the major venue where papers related to deep learning and music are presented. Here, we explore the hard task of directly predicting score difficulty from images, including PDFs. Yes, without requiring machine-readable scores, we can classify all the piano corpora by label online, directly from PDFs and images. We consider 5 data sets, more than 7,500 scores with up to 9 difficulty levels. 3 of them were never used so far for a computational task. We also tested on out-of-domain composers. I want to remark the hidden voices dataset, composed by black female composers, a repertoire never used on our community. Drawing from past studies, we have integrated an only decoder model with a mirror representation for sheet music analysis. After pre-training with self-supervision on the larger music sheet collection, we fine-tune in the task of estimating the difficulty. One challenge is that the difficulty annotations are for the whole music piece. So we modified this GPT model to handle large music sequences. Another challenge is that the difficulty ranking is different for each dataset. That is why we simultaneously train models on each dataset and a multitask model on all the rankings. Ablation studies suggest our multitask training is helpful in difficulty classification. Our proposed approach, directly from images, works at the same level as working in machine readable, and is better than previous bootleg encoding, and consumes 8 times less memory. We also conducted experiments to find the answer to this main question. Can our model help promoting diversity in music education repertoire? Well, I don't have time now, but we can talk about after the presentation. What are we doing now? We are working directly from audio data, the perfect scenario for music students' engagement, and also modeling physical gestures performance directly from a collected data set of 1,000 videos with this camera position. What is the next? Modeling the task as a multimodal task, creating models that work independently in one modality or in another, which can improve the performance of the task and unify all the research carried out in this PhD thesis. We also want to merge the difficulty task with automatic music generation focus on music education. Before finishing, you can try our models by scanning this QR code. And well, this is a social implementation carried out by undergrad students if you want to try it in order to explore the largest music library available online. Thank you so much for your attention.
Thank you, Pedro. And now we are moving to Joan Serra. Joan Serra is a senior staff researcher at Dolby Laboratories, Barcelona. His research interests are in generative modeling and representation learning for sequential data, especially time series and audio. He currently leads a geographically distributed team of researchers working on advanced and machine learning topics for audio and multimodal analysis synthesis. Joan Serra is going to introduce mono to stereo through parametric stereo generation. Thank you, Joan.
Thanks, Marta, for the introduction. Hopefully the slides are visible. No. Okay, good. So, mono to stereo, work done with my colleagues at Dolby, here listed. Yeah. Okay. So first, everyone knows what a stereo signal is. So it's two signals, one for each ear. We have 2 ears. So we want to hear different things in order to have a better experience rather than listening the same thing through both ears and not having, for instance, a notion of a space. So thanks to stereo, you can say, oh, the guitar is there on the right and the singer is here on the left, right? So why is this still in it? Why does it make sense even nowadays? Well, there are many historical recordings that are only in mono. So one may want to have a better experience by having them in stereo. There are mono recordings. Maybe I'm rehearsing with my band and I only have one microphone and I just use that microphone. Or there are recordings that even though there are 2 signals, they are not really stereo. For instance, if I record with this in this position, this has 2 microphones or 3, but the space, the left-right space is super small. So it's not really a stereo signal. So you better treat it as a mono and then do the stereo, etc. Plus, there are many algorithms that only process mono nowadays, so we want to still go back to stereo. And the main point of our work is to claim that this is a super nice generative problem, because, for instance, especially in music, the stereo image is super creative. So there are artists and producers that really on purpose put some things on the left, some things on the right, and use that to create their sound and to define their product. It's not a one-to-one mapping. That's why it's a perfect ground for generative modeling. So a guitar can be on the left, can be on the right, can be on the center. It just obeys to the context and to the aesthetics of the composer, right? So surprisingly, there were no works treating this as a generative problem, as far as we know. So which are our contributions here? So first is to cast the stereo generation as a generative problem. Second is to use this tool of parametric stereo to perform the generation in this space. Then we propose 3 machine learning techniques to generate stereo. We also propose some objective measures to evaluate the task and some subjective protocol. So first of all, what is this parametric stereo thing that I mentioned? Parametric stereo is a coding technique. So you want to transmit a stereo signal with less bits. So what do? You transmit the mono and then some parameters that will define the spatialization of this mono signal, right? And this compresses the data. And it's quite cool to do that because, with quite few information, you still have a full representation of the stereo image. And if this technique is done, this coding technique is done right and implemented right, you hear very few artifacts. So now we have just a mono signal. We need to generate these parameters. That's our main problem. How do we do it? So, well, we will use a machine learning model, and then we will generate a plausible version of these parameters, and then we will use a standard decoder from parametric stereo, signal processing based, to decode the 2 things, the mono and the parameters, into the stereo signal, okay? And now it's about how do we generate these parameters. So we can use machine learning. Let's do it. But first of all, let's use quite a naive approach or classical approach based on nearest neighbors. So here you have a frame of audio, you search a data set, training data set, which is the closest frame, plus its neighbors, and then you say, okay, I have the parametric stereo parameters for these neighbors, so I impute it to my current sample, then I create a sequence of these, because these parameters is a sequence of parameters, right? And then from this sequence, I generate the stereo signal. This kind of actually works. You need to apply a couple of tricks, like this smoothing and so on, because otherwise it's a bit ugly to hear. An alternative approach, let's use deep learning. Let's use an autoregressive transformer model like BERT to predict this sequence of parameters from the audio signal. You condition on the audio signal, and then you just go sequentially from left to right, from past in time and then in frequency also. And we can also leverage recent techniques like classifier-free guidance. Plus, we can develop, given the specificity of the problem, some weights for the loss, such that it focuses more on parts that really have stereo information and discards more or pays less attention to parts that don't really have stereo information, or where signal is quite convoluted and everything is more or less mixed and so on. So the details of these weights are in the paper if you are interested. But autoregressive models are a bit slow, and we are here talking about very long sequences, so this can be minutes or hours of audio. So maybe we want to work with a faster model, and in this case we leverage this technique for image, which is maskgit. We apply it to the audio domain. And for comparison purposes, this is exactly the same setup as the autoregressive approach, including the classifier-free guidance and the loss weighting, etc. The only difference here is the sampling, how we sample the signals, right? So in autoregressive, it's causal from beginning to end and one by one. Here it's random and taking into account the whole signal, so end, beginning, and so on. Right. So and here let's go to some results. First of all, of course, there is not a well-established evaluation protocol. Actually, people didn't even think that this was a generative task before, so we have to do a bit of our best here. So the first evaluation we did was a subjective experiment, so asking expert listeners to judge the width of the mixture that we were generating and comparing it with monosignal and with some references. Implementations of classical approaches we had here, signal processing based, or the same transformer, but instead of being generative, just applying a mean square error loss, therefore being deterministic and so on. And what we observed is that the generative approaches were in general judged or preferred over the classical approaches. And among those, the performance of the nearest neighbor was quite surprising. So it was in the middle of the two generative approaches and sounding quite well. But the approach that worked better was the maskgit based one, which is this red one you have here on the right. We also developed some objective metrics, or tried to develop some objective metrics. We are quite happy with them, but they don't fully correlate with the preference judgment that we collected in our subjective test. So for the moment, you may use them maybe to tune some hyperparameters. You cannot query the expert listeners for every little change of the combination of your hyperparameters, but you shouldn't fully rely on them. It breaks the rankings for some approaches, right? Then a second thing worth considering is the speed of these approaches. And here what we see is a couple of things worth mentioning. One is that the autoregressive approach is super slow. I mean, you will not be able to run it on your mobile phone or in another device, right? While the maskgit approach quite improves that, but still would need some further modifications in order to be able to run faster than real time. This is real time factor, so we want something less than 1 here. On the contrary, the classical nearest neighbor approach, without any specific fast neighbor retrieval, it already does the job faster than real time. So it's worth considering because it was not bad at performance and it performs quite fast. However, I mean, informally, when you listen to that, you see it lacks quite of inventiveness. It's very conservative because of the smoothing we apply. It performs quite always the same thing, so it's not really creative. It misses a lot of the inventiveness of the generative models. And yeah, here I had some examples, but unfortunately the system does not reproduce stereo well. So I invite you to come to the laptop with some headphones to listen it better. And I can show you now offline. And yeah, that's it. So which are the contributions of this paper? So first, we cast the problem of mono to stereo as a generative problem. And to perform generation without many artifacts, we leverage this parametric stereo coding technique. And then our task is to generate only these parameters, these parametric stereo parameters from the mono signal. And we propose 3 different techniques to do that, one based on nearest neighbors, another based on an autoregressive modeling, and another based on masked tokens. We find that the approaches significantly outperform the baselines we consider. And some of them are suitable for fast inference, so some of them perform fast. We also develop some objective measures, and we also adapt a subjective protocol for testing this type of generative approaches, and you will find some discussion in the paper about technical details and the protocol. So that's it. Thanks for your attention.
Thank you, Joan. And from Joan to Juan. Juan Montesinos is an engineer at the Swiss Center of Electronics in the Robotics and Deep Learning Group, where he's currently working in event detection and graphs for time series, as well as 3D acoustic source localization. Juan is going to introduce speech in painting, context-based speech synthesis guided by video. Thank you, Juan.
Hello. Yeah. So thank you very much for the introduction. I'm glad to be here another year in this edition of Barcelona Deep Learning Symposium. First of all, I would like to thank the organizers for all the effort. I know it's very hard work. And yeah, let's get into it. I'm going to present speech synthesis guided by video. And so I usually start this kind of talks trying to convince public why multimodal is very important. But now with ChatGPT and Gemini, it's pretty much more clear that multimodal is future. But just to put some facts, for example, YouTube has some billions of hours of unprocessed data, and it's very typical that it's unfeasible or very costly to label video, and also it requires high expertise to label audio. And here multimodal can play a very important role, because in the end, multimodal, right, can help in self-supervision. And we often, with audio and video, can rely on the other modality to train many networks or solve many problems. Some examples why we're interested in this: also machines, it's very ideal. Machines can understand the world as we do, and this can help, for example, in robotic assistants or cinema industry. Also scene understanding, and of course, as I mentioned, large language models, because most of the content we ingest is nowadays audio and video in social networks, media, and so on. So, little bit now the bit of audio background. An audio signal is usually a 1D signal, but often we preprocess them to map it into the time frequency domain. And the reason why is because this way audio becomes some sort of image, and then we can borrow many ideas and architectures from computer vision, but also because it's more interpretable. So here we see a spectrum, so it's frequency time, and we can observe a male and female saying the word psychology, and we already see that the frequency of female is higher than male, right? So it's actually more interpretable and more intuitive in that way. And now let me quickly introduce the problem we're trying to solve here. So we have an audio signal, which in this case is in a spectrum, and often this can be corrupted. So what we want to do is reconstruct the corrupted segment based on the known audio segment, but also on the other modality, which is the video. And we solve this problem in a specific case of speech, so actually people talking. So we manually generate these masks, which indicates where do we want to reconstruct the signal. And we try to do so, just passing the video and the known audio to a module, and then merging the known audio and the reconstruction at the end. Okay, so the way we do this, surprise transformers. But let's try to get in details how do we do this. So this transformer architecture, which actually ingests audio and video and somehow decodes audio, it's trained in 2 stages. So first we have some sort of Hubert training style. And for those who doesn't know what Hubert is, Hubert, let's start by BERT. BERT was developed for NLP, and the idea was self-supervised way of training by masking tokens, right? So we have sentence, we mask the input, some parts of the input, and we would like to predict the word that is missing or masked. And this works very well because actually words are unit, or they are units with meaningful, which are very meaningful or complete meaning, right? However, audio is not like that. Audio, if you take a chunk of audio, it could be just a vowel or it could be an entire word. And so the BERT training couldn't be applied directly to audio. However, some developers or some researchers developed HUBERT, which stands for Hidden Unit BERT. And the idea is, okay, if we don't have meaningful tokens or tokens with full meaning, we can just get chunks of audio and then extract pictures, cluster them, and then we can apply masking and predict those clusters. So the idea is they clustered, they masked and predict the clusters, and several times they train this. Then again, you repredict the clusters, and you do this iterative process of clustering and predicting the clusters. So ideally, we train this video encoder network that way, because once it works for audio, it can be extended to other modalities, this way of HUBERT training. And it was further fine-tuned for audiovisual speech recognition, which means this video encoder here, it already has a notion of words or text. So the features are pretty much aligned to words and text. So then in second stage, we just freeze this encoder, and the idea is we pass all the frames in a video, and we extract some features. We apply a modality encoding, and with the audio, we also extract from the corrupted audio some features, we fuse them, and we predict magnitude spectrum, which is already pretty much the audio, reconstructed audio. The goal here is also magnitude spectrums are complex numbers, and I'm not going to get into why, but it's very difficult to predict the phase, so we can just use some classical methods, or we can use something called vocoders, which are networks specialized in mapping spectrograms into waveforms back without inferring the phase. So we train this, or we put in practice this method with in the grid corpus dataset, which is a very high quality dataset, but very small, of people saying sequences of nonsense words. For example,
Ben Bull at E4 now.
So as you can see, it's totally nonsense. And we tested against some metrics, which stands for perceptual quality, intelligibility, but for me the interesting one is mean absolute error, because we see in this x-axis, this is the length of signal that was corrupted. When it's very small, an audio-only model can already do the job. So if the gap is small, it makes sense that the audio-only can reconstruct from the boundaries. But when this gap grows up to, for example, 1.6 seconds, it's already too difficult to predict the speech content, because the information in the boundaries is not enough, right? So here we can see the audiovisual models, they do a much better job, and actually they can infer some sort of lip reading from the audio. Okay, so more or less the same takeaway here. When the gap is small, well, previous models, but audio-only models can do the job. Also, audiovisual models can do the job. But when the gap is very large, so we're talking about corrupted signals of 1.6 seconds, the audio model just collapses and can no longer generate meaningful content. Meanwhile, audiovisual models can still do some sort of lip reading, as I mentioned. Okay, so let's hear some examples.
Being green by R5, please.
This is the ground truth, and then we just manually mask it to simulate a corruption.
Being green by...
So this is what the network hears, and since there is a long gap corrupted, the audio-only model tends to do some mumbling.
Being green by...
Then the previous, let's call it state-of-the-art.
Being green by L6, please.
And realize that while the ground truth says being green by L5, please, this model now says be green by L6, please. And this has an important meaning. However, our model
being green by L5, please
correctly says being green by L5. And why all this happens? Essentially because the mapping between lip motion and audio phonemes is not bijective. So for example, if you look at a person saying the word elephant juice, it looks exactly the same as a person saying I love you. Because actually, for given a set of lip motions, they can produce different phonemes, while the the lip motions are the same. But as you saw, this data set we tried against is a little bit unnatural and too small. So we also tried in VoxLab dataset, which is more than 2,000 hours. We just got English subset. And
films together. They did this switch.
the idea is now we can predict, although this spectrum seems very blurry,
Comes together, they need to switch.
still encodes quite a lot of the original audio. So this goes farther in the direction of lip reading. So thank you, everyone, courtesy of ChatGPT, and hope to see you next year again.
Thank you, Juan. Okay, and now moving to our last talk, I want to thank again the speakers for keeping the time. And now we have Marco. Marco Baroni is an ICREA professor at the Department of Linguistics of the UPF, where he leads a team investigating language emergence in large language models. Marco is going to talk us about, can discrete information extraction prompts generalize across language models? Thank you, Marco.
Okay, all right, yeah. So, sorry. This is work that has actually been carried out mostly by our PhD student, Natael Carraz Rakotto-Nirina, but since he could not be here today, I'm presenting it. So we know by now that pre-trained language models contain a lot of knowledge, and so there is interest in finding good queries, that is, good prompts to get this knowledge out of the models. And a challenge that has been widely used to do this kind of research is the T-Rex slot filling task, where you are giving a subject, such as, say, Lana Del Rey, a relation such as place of birth, and the task is to formulate a prompt, a sequence of tokens, such as, say, was born in, such that if you combine that with the subject, a pre-trained model is most likely to return as most likely next token the correct completion, like in this case, Manhattan. However, at least since 2020, people have also tried, instead of crafting prompts by hand, to actually use algorithms to automatically machine generate optimal prompts. And in particular, a very successful approach in this domain has been the autoprompt method. Autoprompt takes as training data a set of examples of the task of interest. So for our T-Rex slot filling task, this could be tuples of subject, relation, object, a back-end frozen pre-trained language model, and uses semi-discrete search techniques to find a sequence of tokens that is most likely to return the right object given the subject and the induced prompt. And there is by now a lot of research that shows that autoprompts and similar methods are actually outperforming on a variety of tasks manual prompts, often by a large margin. And we also provide evidence for that in our paper. Interestingly, however, these machine-generated prompts are not very intuitive to us. So probably if you were going to try to retrieve information about somebody's place of birth, you might come out with something like was born in. It turns out that specifically for the birth language model, if you were instead going to ask Poxiar Pool Club in, that was more understandable. This would be more understandable to the language model as a way of asking for someone's place of birth. Or as another example, if the relation is a country's official language, you might think that it's reasonable to craft a prompt such as the official language of X is, but actually what works better is equal foreign citizens speaking. So what we first asked in our paper is like, okay, cool, it's interesting that when you optimize on a certain model, you get these weird prompts, but do then these prompts generalize from one model to the other? So could I, for example, train autoprompt on BERT base, say, take the prompts I obtain and try them on BART base, or maybe nowadays try them on ChatGPT? Perhaps not surprisingly, if you just use the vanilla autoprompt algorithm, the resulting prompts are not very transferable. So what you see on this slide is the black bars are accuracy when you train auto-prompt and then test on the same model. The orange bars are when you train auto-prompt on BERT base and then try to generalize to another model. This sort of works if the two models are very similar, like going from BERT base to BERT large. But say if you try to generalize, that's like the last block over there, to a different architecture model such as T5 large, you lose quite a bit of performance. It turns out, however, that with a very simple tweak, we can get transferable prompts. And this tweak is simply during the training phase of auto-prompt to expose it not to one, but to two frozen pre-trained language model backends. And if you do this, you get prompts that actually are not only transferable, but sometimes they even like outperform the prompts that you will get by directly training on the model of interest. So for example, here say you see that a model trained with this mixed strategy on BERT base and T5 large actually does better on BART large than a model that has been directly trained on BART large. So then we wondered, once we have these transferable prompts, what are their properties? In particular, we hope that they will also get more interpretable, more human language-like. It turns out instead that we get a mixed picture. So there are characteristics in which they become a bit more English-like. In particular, we see that they tend to be formed of real English words and not these strange combinations of subword tokens that we were finding with the original auto-prompt. And also, just like natural language, these transferable prompts seem to be robust to single token deletions. So it's no longer the case, for example, with original auto-prompts. Often if you delete the last token, you get down to random performance. These transferable prompts are more robust. But in other ways, actually, they become less language-like, less human language-like. In particular, according to some measure we devised, they appear to be less semantically transparent than the non-transferable prompts. And also, unlike in natural language, they seem to behave more like a bag of tokens, such that actually if you scramble them, you scramble the order of the tokens in the prompts, you actually often find just a very small decrease in performance. So, wrapping up, we already knew from previous research that you come up with machine-generated prompts that work very well for certain tasks, but they are opaque to us. We showed in our paper that just by a little tweak of the original auto-prompt algorithm, these opaque machine-generated prompts can also be made universal in the sense that they seem to work well on a number of out-of-the-box language models. And however, there is a complex picture in which these more transferable prompts are more English-like in certain ways, but actually less English-like in others, which suggests that more research is needed on characterizing these machine-generated prompts and maybe also on understanding how they come about. And actually, after our work, there were like other papers, one that is posted on this website, that showed that actually you can develop similar discrete transferable prompts that will also work when you train them on latest generation models such as ChatGPT, and in particular there they can be used for harmful purposes, such as like if you just ask ChatGPT, generate a step-by-step plan to destroy humanity, ChatGPT will tell you no. But if you instead ask it, generate a step-by-step plan to destroy humanity, equal, interface manual with steps instead, blah, 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 ChatGPT will gladly abide. So maybe the particular models we are working on now feel a bit obsolete, but I think the issue of these opaque machine-generated prompts and why they work is still an important one. And that's it. Thank you.
Thank you so much, Marco. Don't go away because I was about to invite all the speakers of the session here. And the good news is that we have like 10, 12 minutes more because the catering is arriving later. So, yeah. let's take advantage of this and please, questions. Okay, here. Thank you.
So I have a question for Juan. Maybe you explained it during the talk and I missed it. Which laws did you use in order to generate these spectrograms?
Sorry, no, I didn't mention it. We just used L1 laws, but of course there are more advanced things to generate better spectrums. We were more in the line of proving the concept than just getting the best performance out of the world.
Right, okay. So thank you.
Thank you.
Here.
Yeah, so I have a question for Joan. So in previous years in the symposium, you've talked about GANs, normalizing flows, whatever, all sorts of generative models. But today I didn't see them in the experiments that you ran, and you didn't talk about diffusion either. So could you comment of why they are not there? Why did you choose autoregressive models?
I guess two main reasons. One is because things change, and every year there are new models that work better than the ones before. Second reason is because what I was trying to generate here is discrete data, and all these models like diffusion models, normalizing flows and so on are more for continuous data. So I thought it was more natural to generate in the space in which this is than in trying to make it continuous and then use a continuous model. So,
thank you.
Okay.
Yeah. So I was wondering for this system that you developed to reprompt everything, why do you think it passes the alignment of these large language models? Because in the end, as far as I understand, it's an optimized prompt, but it still should have the same meaning, so it still should fall under the constraints of the alignment, right? So why is it not the case, or what do you think it's not the case?
You mean why the way in which ChatGPT, say, has been like optimized to avoid, for example, harmful questions, these prompts, why can they pass it? Yeah, so I think nobody really understands that at the moment. I suspect that they are just like so out of distribution that the way, like, you know, ChatGPT is probably optimized by kind of against human attacks, you know, against you asking how to build a bomb. And so it was just like not prepared to face this kind of strings at all. Thanks.
I have another question for Marco. Is there like some correlation between like the performance of these mixed, like the mixed derived prompts and like any overlap between the training sets for the different LLMs?
Training sets. So training sets we haven't really checked. I mean, I think nowadays most LLMs are really trained on very similar data,
exactly,
like I think pretty much the pile and the like. But that's actually a question that we would like to understand now. So now we have sort of like switched our research, like not so much on like let's get the best prompt, but let's try to understand why they arise. And one of the hypotheses is that it has something to do with the training data. Like there are like these very low frequency items, like the word Magikarp, that seems to appear very often in these prompts and seems to appear when you train them on different models. So is that like some weird thing about the pile which makes Magikarp so important? So I think it's a good question, but I don't know the answer.
Okay, thanks.
Hi, I also have a question for Marco. First of all, thank you for the talk. It was super interesting. With this whole new buzzword of like retrieval, augmented generation, RAG, and so on, is it changing in any way, all these auto prompting and so on? Like, do we see any change that now all of a sudden, since we have to retrieve on existing data, we have to adapt these kind of models, or can we still apply the same?
So I think that nowadays, like trying to use these machine-generated prompts to improve the performance of the model is sort of like obsolete. I think both because of better alignment, instruction tuning, and maybe now also these retrieval things. Really manual prompts are already like very good. So like I think this is no longer a need we have. So I think now the interest is more, on the one hand, why do these things exist? You know, like we actually look at them, they have like super low perplexity for the model. So why should the model sort of understand them and produce a reasonable answer to them? And then from the practical point of view, I think it's more on the side of adversarial attacks. Like, you know, they might not be better than human prompts, but still they can be used maybe to convey some information and bypass some model filter or something.
Okay, more questions? If not, I have one to the entire pool of presenters. Marco has already been talking a lot about large language models. How have large language models affected your own research?
At least personally speaking, as a mix between research and engineer, I use ChatGPT quite a lot every day, at least as coding partner, because it's very useful to give very specific and detailed tasks, and it gives you so much back. But besides that, I don't use it as a source of research knowledge because it's not very reliable. Maybe as a source of knowledge for classical problems, like, okay, I've never heard of this sort of filtering, but I know it's well known, so I may ask ChatGPT about it instead of Googling and passing through filtering good answers. But so far, so good.
Thank you, Juan. I was also asking, apart from using it as a partner, okay, or a personal assistant, let's say, I was also asking for the pressure to compare, for example, for me in machine translation, okay? So we use encoder-decoder still, but there is large language model, and here there are people logging a lot how you can do MT with large language models. So I was more referring about that, no? So about solving your, well, not your piano thing, but other tasks with just using large language models.
Yeah, I think in the case of music, it's large language models trained on text doesn't have any information. For example, I don't know if you give animates maybe about about a place, for example, you say, well, this place is called this one, no? And you give to the language model and can retrieve a lot of information, but for most of the music pieces, outside of the very, very high peak of the long tail, language models doesn't have too much information. Then it's also our research that people is carrying out, trying to create music-related language models and things like that.
Yeah. No, I also agree. Like, and in general, we have to think of more innovative ways to approach many different topics, because to a lot of our tasks, like, you can combine maybe 2-3 large language models and then you get a very good score. But then, we have to go a bit deeper, like, okay, how do they perform on very low resource languages, right? Like on very noisy conditions. And I guess there's still like a lot of things to research, but we have to take into account that we have these tools that maybe restrict a bit our research area right now.
Yeah, and also it's not about only the performance in like achieving the best score in something, but also the efficiency of the models and this kind of thing. So maybe doing a task that you can concatenate large language models to do so, but you can try to find a smaller model that can do so, and it maybe can run in a small device. So there's a lot of field to still working.
Great. Overall, I enjoyed a lot the session, and because of that, no? Because it was not about large language models. So even if it being language and speech, it was about more original architectures and experiments. I open the floor again for questions if there is somebody that have thought about something. Here, great. I encourage you to introduce yourself as well when you do the question.
Okay, so my name is Pau Torres, and I also work a little bit on, I actually work on music recognition, not so much on other music-related tasks, but for scores. So my question here is, when you try to rank the difficulty of the pieces, if I understood correctly, you have 3 different models, and then you try to average them or collect their information together. So my question was, have you found that any one particular variant or modality dominates over the others? And because my thought was trying to recognize music sheets.
Physical gesture is the answer. Yeah.
Sorry?
Physical gesture used to dominate, but in the last section there is a case study with a lot of scores, and there are examples of the opposite too, no? But basically the 3 dimension doesn't correlate too much, and have sense that doesn't correlate too much. But I think in general the physical gesture is dominating the other 2.
Thank you.
One last question? No? Then let's do the break. Thank you all. Thank you, speakers.
Hi. Hi, everyone. Welcome to the last session of the symposium. So it's my pleasure to introduce Ricardo Baeza Yates. Ricardo Baeza is the Director of Research at the Institute for Experiential AI at Northeastern University. He's also a part-time professor at the Department of Information and Communication Technologies of the Universitat Pompeu Fabra in Barcelona, and at the Department of Computing Science of Universidad de Chile in Santiago. His areas of expertise are web search, data mining, information retrieval, bias and ethics in AI, data science, and algorithms in general. I want to highlight that Ricardo was the Vice President of Research for Yahoo Labs from 2006 to 2014, at which point he became Chief Research Scientist at the company's headquarters in Sunnyvale in California until 2016. And during his tenure there, he founded and led the Yahoo Labs in Barcelona and Santiago de Chile from 2006 to 2015, oversaw Yahoo Labs in Haifa, Israel from 2008 to 2012, and started the London Lab in 2012. And among his many distinctions, Ricardo has the ACM Fellow and IEEE Fellow, and he has received many awards, including Premio Nacional de Informática Aplicada de España in 2018. So thank you, Ricardo, for being here. My first question for you is, you are the Director of Research at EAI Northeastern, and you are based in California, but you are also a full professor part-time at UPF here in Barcelona. Why is it interesting for you to stay connected to the academic community in Barcelona?
Well, thank you first for being here and the kind invitation and the kind introduction. So I always prefer short introductions. So I came to Barcelona as a career professor in 2004. I was already in love with the city in many ways. I came here when I was 17 years old in a trip to Europe, and was the nicest places here. And then just after my PhD, I did a stay at the UPC, and I had wonderful collaborations of research. And then in 1996, I did a sabbatical here, so I was coming back and forth many times. And I guess I'm a Barcelonian by heart. I mean, you basically are born in a random place. I think you should choose which is your city, and this is my city, and I hope I will die here. That will be my choice. So that's why I'm here.
Very nice. Then my second question for you. So we hear a lot about responsible AI, and I know that you actively participate as an expert in many global initiatives, committees, and advisory boards related to responsible AI. So my question is, in your opinion, what are the main risks of AI research and AI deployment?
Okay, I have prepared a question, that answer to that question here. So if you don't mind, I will. Because I think there are so many computer vision people that it's better that you see the answer. At least for me, that's what it works. So these are my kind of ranking of dangers today. Mental health. How many people know that the person committed suicide in March in Belgium after 6 weeks talking to a chatbot? You didn't know, right? Very few. Okay, please read the news. And he was, I guess, a PhD student, so was not any like random people. Disinformation. You can have any video today with the person that you want, with the voice that you want, saying whatever you want. We will see that in the next presidential election in the US. That will be the test for disinformation. But the truth is that we lost digital truth. It will be very hard to know what is real and what is not. A third one, discrimination. Well, you know about that. And then safety, privacy, and security. So these are the dangers, for me, the main 5 in somewhat ranking order. And what are the limitations? Pseudoscience. For example, people using faces to predict behavioral characteristics of people. This has already happened several times, even from famous universities. And the IRBs don't stop them. Basically, ethics is not looked at by IRBs. I'm glad that some universities have a real ethics committee. And ethical applications of machine learning. There are many. For example, using games to hire people, or for example, using data from other people to predict that you will not return your loan, even though it's the first time you ask for a loan. Banks are doing this all the time. Third, data doesn't capture the whole reality. In many problems, data is a very bad proxy of reality. Please check at that. Second, not enough data, and Fernando mentioned this, data, data, and data. But in many cases, you will never have enough data. 99% of the applications of the world will never have big data. So sorry, deep learning guys and girls, you cannot use deep learning. Data is not representative. Fernando talked about that. Model is biased and toxic. It's not only about data. Also, models may increase bias and may add additional bias. For example, the Bologna case of Deliveroo, or for example, can be very toxic, like language models and so on. And then we have the 2 worst ones that are nothing to do with technology, but very important, human incompetence. For example, a Facebook engineer using an English-trained model in France that decided that the town of Biche was forbidden. And there was no human in the loop for 3 weeks. And then our cognitive bias. Like we're working in problems that maybe are not the main problems of society. This is the one, cognitive bias, but there are many others. And this is an interesting book about small data, and I'm glad that Andrew and Jill last year in IEEE Spectrum said unvegan AI. And then the problem is that with all this, we are maybe fooling ourselves. For example, we are doing the wrong evaluation. Imagine if you have an elevator that says it works 99% of the time. Would you take it? I won't. But if the elevator says doesn't work 1% of the time, and when doesn't work, it stops, I take it because I know I'm safe. We should evaluate AI like we do with drugs, with food, with buildings, but not by just average success. So this is my answer.
Okay, so a lot of concerns. Let's try to think about solutions, right?
Yeah.
So my next questions for you are how would you define responsible AI, and what are the key elements of responsible AI? And finally, if you can maybe recommend us some good practices that research can follow to approach AI research responsibly.
Oh, by the way, you can check my article in European Review and my talk in YouTube about this. So thank you for the second question. I will use the new principles of ACM for responsible algorithmic systems. How many people know them? They're from October last year, so more than a year ago. No one. I'm really worried. Professionals should read what professionals recommend. And one of the 2 main authors of these principles, there are 9 principles. This is basically my main contribution. Legitimacy and competence. Show that your application is legitimate for society, and show that you have the competence to do it well. This is the main one for me. All the others are surely known, and you see when you need to apply them. So suggestions for responsible AI, and this is my view of responsible AI. So responsible AI is everything. You need to put it in every place of the pipeline, from the idea to the deployment of the application. So for example, to do this, you need to do ethical risk assessment. It's similar to a large infrastructure project where you do an environmental impact assessment to see if you are not damaging people or the environment. Validation and testing, but so important data there, the right data to validate. Operation, monitoring tools, check if the input is drifting, check if bias is amplified, check everything, and there are some startups that are working on this part. So this is about the main 5 principles that they are inside. You can read them. I'm sure you know them. But clearly we put minimizing harm, and because people think that this is only for humans, we put also check the environmental impact. Like, for example, TikTok plus ChatGPT are wasting a lot of electricity and water. And water is a very important resource. And the last one is, if it fails, you may need to do an audit, a third-party audit, completely independent. And if you go to the last one, it's too late. You have to go to court. And we have many examples of this in Europe and in the US. And one last point is that never do an audit of an algorithm that shouldn't exist. Why? Because you are legitimizing the algorithm. So please, before doing an audit, check that the application is legitimate. And if it's not, you say, sorry, we cannot do an audit, otherwise we'll be legitimizing your application.
Okay, thank you, Ricardo, for these insights. And I leave you leading the final session of the symposium. Thank you.
Thank you. So we'll start with the first presentation of 6. So the first speaker is Javier Ferrando from Polytechnic of Catalonia. He's a last year PhD student there, working on interpretability analysis of NLP models, and he will talk about how transformers use context to build predictions.
Okay. Yeah, hi everyone. Today I'm gonna talk about a paper presented in ACL earlier this year, explaining how transformers use context to build prediction. This is a joint work with Gerard, Yanis, and Marta. So first, this is an interpretability paper. So first, just a quick introduction on what is it about in NLP, and a very quick example of the type of interpretability that we deal with here. So an example here would be a transformer model like a bird, where we have a classifier on top of it, and it gives us a prediction given an input sentence, and we want to understand why the model made that prediction. And there's interpretability is a very broad field right now, but classic type of interpretation is called input attribution, where we score the different parts of the inputs, as words in this case, as being more or less relevant to the prediction made. So in this case, this is a positive example, and the interpretation could be like putting attention on the clever word for making the judgment that is a positive sentiment sentence. So that's the kind of interpretability. Now going into the paper, this paper, it's about going inside of the transformer. I'm gonna present probably a new perspective, maybe for some of you, of seeing the transformer. This is not as it is normally introduced. The way the interpretability recently is done in the transformer is focused on what is called the residual stream view, where the main component in the transformer is the residual stream or skip connection. That's the main component where the different words that get as input through the model gets processed, and the representations, you have one embedding at the beginning for each sentence, then it gets updated via the different blocks in the transformer. So we have attention and feed-forward networks. And yeah, if we are dealing with a language model, we do this autoregressively. But we can see or understand the transformer as a graph, like this one. So yeah, going to more into detail, we have an input embedding at some time step t that we are generating, and we have this residual stream is the current embedding, and at each layer we have the self-attention block that reads from the residual stream and writes something. So it adds a representation, a vector. And then we have the same for the MLP, that is the second block in the standard transformer. And at the end, we have a last layer representation where we project through the onto the vocabulary. We apply the softmax to get a probability distribution. We can get rid of the softmax. This is a nonlinearity that we get rid of for interpretation purposes. We can look at the logits. So these are the normalized scores before getting applying the softmax. So an interesting thing here is that if you remove the softmax, we have a projection at the end of the forward pass, and we can, since different blocks add into the residual stream, we can apply that projection inside each of the blocks, so that's equivalent. Then, instead of looking at the whole projection and all the logits of all the possible tokens, we can focus on a single word, so the single logits of that particular word. In that case, we are just doing the dot product with one vector corresponding to the unembedding, so this column of the output matrix. And we can do the same. We can do that dot product inside or at the output of each of the blocks. So mathematically, it's just we are, as shown there, the logit of a word. We are doing the dot product with that particular unembedded vector. And by linearity, we can apply that inside that operation. So what we get at the end is the logit of a word is a sum of terms, where each of the terms are the logits update of each of the blocks. So we have for each layer, the MLP adds a bit of logit, and the same for the attention. And we have the initial embedding, which also adds a logit value. So what we do here is we take advantage of that perspective and the way of understanding the model as logit updates for the different words. And we focus also on the attention mechanism. There's more detail in the paper, but essentially the idea here is that the self-attention mechanism together with the layer norm can be understood as a sum of vectors, where each of the vectors has been linearly transformed from its input. So its input is the residual stream from other tokens in the previous context. And at the end, this is a sum of vector together with a bias. So the idea here is we can also do this projection inside each of these independent terms in the sum. So at the end, what you get now is the logit of each word is not only the sum over the outputs logit updates of the MLPs, but also on these individual sub-updates done by each of the tokens inside the attention. So you get this whole decomposition. So what this allows us to see is, for each layer, what are the tokens in the context that are promoting a prediction or suppressing a prediction. So this is an example. When Paula and Marta got a coconut at the zoo, Marta decided to give the coconut to the model predicts Paula, so we can look where the logit updates came at each layer for predicting Paula, and we can see that the model decides this is an indirect object identification task. So the model is focusing on Paula, is copying actually that name to make the prediction, and that's done at the end, at the latest stages of the forward pass, so in the last layers. So we propose a second method here. The problem here is that throughout the layers, the residual streams, they lose identity of the initial token because they aggregate contextual information. So it's hard to tell if at the last layers a token is promoting another token, whether that was actually representing the input token of the context, or is just a mix of information. Not gonna go into details, but we have a previous work where we measure exactly that. We measure how much mixture of information there is in the intermediate steps of the forward pass, and we just apply that and combine it with this knowledge or understanding of the logit updates to track that information back to the inputs. The way this is measured is a recent way of analyzing or getting explanations in language models. Instead of focusing on just the logic updates for one particular token, we can measure what's the difference in logic updates. Why the model predicted one token and not the other. So you can take the difference of the sub-updates of the logics. So in this example would be a report about the impressionist. So now goes has, that's the correct prediction, but why the model picked has and not have. So you can take the difference in the logics to see where the model is actually promoting one and suppressing the other. So in interpretability, there is no ground truth, so it's hard to evaluate how good an interpretability method is. What we do here is we take 3 different data sets where we know there are 2 possible continuations given a context. One is the acceptable, and the other one in red here is the unacceptable. So here, the good thing about this kind of data set is that we know which parts in the context are making the prediction or one of the options right and not the other. So that's the evidence for this linguistic phenomena. So the model, the assumption here is that a good model that is solving this task should focus, or that those words should matter most for the correct prediction, and not the incorrect one. So given these data sets, we extract those words and we compute alignment between some interpretability methods and compare to this ground truth. So yeah, we compare with some existing methods based on gradient, which are very common type of methods. Also erasure, which work by deleting words in the context and seeing how the prediction changes. I'm not gonna go into details, but we compare with those baselines. And for the 2 methods that we propose here, overall for the 3 data sets, and also for, Blimp is just a collection of small data sets as well, we see that the methods that we propose tend to align more with the evidence of the linguistic phenomena. And that shows that models really are focusing on those cues to do the correct prediction. So yeah, also you can use this kind of analysis to analyze attention heads, and we observe that some attention heads do different, in the same layer, do different kind of jobs. Even some of them promote the incorrect prediction. That allows us to analyze where in the model is doing the correct alignment to get the correct prediction. We observe that tends to happen at the end, but for bigger models that happens slightly after mid layers. And we also apply this to the cross-attention in an encoder-decoder model for machine translation. The idea is that you can do the same analysis, and what we were interested here is to see whether the model was aligning with the source words to produce the correct prediction, and we saw that we can extract way better alignments than previous methods. So that shows the model is really, at some points in some layers, are doing a very good job at aligning with the source sentence. We go further with some neurons analysis inside the feed-forward networks. Not gonna go into detail, but you can check the paper. We realized that very small amount of neurons are in charge of promoting the correct predictions. I think that's interesting. And yeah, we have the code available, and thank you. Sorry.
Thank you. Remember that we will do all the questions at the end, and please try to keep the 10 minutes. So the second speaker is Deepam Goswami. He's a PhD student at the Learning and Machine Perception Group in the Computer Vision Center at the Autonomous University of Barcelona. He works on continuous learning problems in semantic segmentation, object detection, image classification, and test time adaptation. And he will talk about how exploiting heterogeneity of class distribution in exemplar-free continual learning.
Thank you for the introduction and the opportunity to give my presentation here. So I will be giving a presentation on exemplar-free continual learning. This paper I presented last week in NeurIPS, and this is a joint work with my co-authors, Yu Yang, Bartholomew, and Joost. And So I will start with a brief introduction of continual learning or incremental learning. So here we are not learning, we do not have access to the entire data set at one point of time. So let's say we have access to the data set which we call at task 1, and we train our model on this data, let's say with images of dogs. And then at task 2, we have images of cats, and we do not have access to data from the previous tasks. So we want to incrementally update a new knowledge into our model, and we want to train our model on new data without access to old data, but we want our model to be able to perform all the previous tasks. So this is the concept of incremental learning. And so what is the problem? Like when we train the model in such a way, we have this problem of catastrophic forgetting, where the model forgets the old classes. And so this is this setting of the incremental learning, and as an upper bound, we always take the joint training where we have access to all the different tasks of data. So one of the most common approaches in incremental learning is to have a small memory buffer, so where we save a small amount of data from all the old tasks. And this has been found in a lot of recent works, that exemplars are very efficient in reducing the forgetting of the networks. But what we are trying to do in our work here is it is exemplar free. So, but why exemplar free? Because there are memory restrictions in a lot of devices, and as well as because of privacy regulations. So if we really want to continually learn and train our models, we should aim for without storing the data, because it's important. So what is the setting which is commonly used in exemplar free continual learning? We call this warm start continual learning, because we divide the entire data set into two parts. One is the first part, which is the task 0. And recent works like Fetril, what they proposed is, so we train the feature extractor on this task 0, and then the rest of the task is equal, the rest of the data set is equally splitted, and we perform continual learning in these new tasks. And we do not have access to the old data, of course. So what Fetril shows that simply learning the classifier, continually learning the classifier, obtains state-of-the-art results in this setting. And this setting is more about exploiting the feature representations, which is learned in the first step, and trying to see how continual learning performs without having access to old data. So in our work, we are working with the nearest class mean classifier, which is commonly used to classify the features at test time. And what we observe is, like when we train our model on the first task, we get very good feature representations of the classes. But as soon as we move to the second task and onwards in the continual learning setting, we do not get very good feature representations. And what we observe that using the Euclidean distance for doing the nearest mean classification is suboptimal, and it is because the feature distributions are heterogeneous for the new classes. So it makes more sense to try the anisotropic Mahalanobis distance. So quick look into Mahalanobis distance is when we have a distribution of data in terms of the mean and the covariance matrix, we try to find the distance of a sample point with respect to a distribution. And we use the inverse of the covariance matrix in the formulation. So which is something in which it converges to Euclidean space when we have a identity matrix over here. So in Euclidean space, we assume identical variance and 0 covariances. So we try to show it in the feature representations that using a Euclidean distance is not the best idea when the feature representations are not very spherical. So we try to show it using Mahalanobis distance, where the contour lines indicate points at equal distance. So a point at this position is at the same distance from the prototype compared to a point at this position. So, but looking back, when did we actually start using the Euclidean metric? Because the Mahalanobis distance looks better. So before the neural networks, it was the Mahalanobis distance which was used with handcrafted features for classification. But as soon as we have the neural networks, we got very good representations. And that is the reason why a recent work proposed, not very recent, 2018, it proposed that we do not really need to use the Mahalanobis distance anymore, because the neural networks gave us very good feature representations, which are isotropic in nature, and we can actually effectively use the Euclidean distance. But that it turns out that is not the case with continual learning. For example, we try to illustrate how continual learning looks like in the embedding space. So in a joint training, when we have access to both old and new classes, all the classes at the same time, we observe that the feature space has very good representations. So it's totally fine to use NCM with a Euclidean distance. But as soon as we move into the continual learning settings, for example, we have this big problem of stability and plasticity trade-off in continual learning. So when we have a high stability model, we see that we don't want to forget the old classes. We see that the model retains the spherical representations of the old classes, but it never really learns good representations for the new classes. And at the same time, when we look at the high plasticity setting, the model learns good representations for the new classes, but it loses the spherical representations of the old classes. So this made us think, like, why use the Euclidean distance, and why not actually make the best use of whatever representations we have and use the Mahalanobis distance, which captures the feature distribution of the individual classes. So we propose this FICAM classifier, where we try to use the Mahalanobis distance in the embedding space for image classification. So basically, when we train our model in the first task, we get very good representations. But as soon as we move to the new tasks, and another important thing about the setting is we train our model on the first task, and then we freeze the feature extractor, and we obtain the feature embeddings for the new tasks images, and we see that the feature embeddings are not well clustered. But in joint training, this is what we have. So in continual learning, it's very difficult to get very good spherical representations of both old and new classes because of this stability plasticity dilemma. So we do experiments with our FICAM classifier, and we see that indeed, like for the old classes for which we have very good representations, Euclidean distance and Mahalanobis distance are doing quite good. But when we move to the new classes where we do not have good feature representations, the NCM with Euclidean distance is performing quite worse. And then we have like two variants of FICAM, where in one setting, in the common setting, we take like one common covariance matrix, which is shared with all the classes, and in the second setting, we take like one covariance matrix per class, which gives us very good performance as expected. But as it turns out, it's not so easy to use the Mahalanobis distance in the feature space because of certain problems. So we have to find the covariance matrix has to be invertible to be used in the formula, and this is a problem because the feature dimensions are very high. For example, in ResNets, we have 512 feature dimensions. So we perform approximation, which is covariance shrinkage, to get an invertible metric so that we can use it in the formulation. And another problem is because of the notable shift in the feature distributions between old and new classes, we notice very high variances for the new class. So we perform the correlation normalization of the covariance metrics from different classes. And the last thing we perform is Tukey's ladder of powers transformation to make the distributions more Gaussian. So you can see like this is the new classes in the center, and simply applying a Tukey's transformation makes them a better clustered compared to the initial state. And then we use the Mahalanobis distance in this feature space. So this is our contribution, and we classify the continual learning settings into two parts. One is the many shot, when you have access to all the data available in the data set. For instance, here we have like 5, 10, and 20 incremental tasks, and we report the average incremental accuracy. As you can observe that even though a lot of these recent methods, they proposed a lot of training strategies, learning the feature extractor for old and new classes, a simple Euclidean NCM is outperforming a bunch of those methods. So it makes sense to look how we can better do a NCM. And with the Mahalanobis distance, we try this. In this setting, we have a shared covariance matrix with all the classes. And in this setting, we have one covariance matrix per class, and we get very good competitive results. And we also try to see how this works in the few-shot continual learning setting, because most of the methods which are at present it either works for the many-shot setting or it either works for the few-shot setting. So, but what we do is entirely on the feature space, so it does not matter if we have access to a lot of data or very limited amount of data. So what we do over here is we simply take the state-of-the-art model Alice, the first step, and then we simply use our FICAM classifier, and we get like good improvements on the three few-shot learning benchmarks here. So just to conclude, so the stability plasticity trade-off in continual learning prevents classes from forming homogeneous clusters in the feature space, and thus it's suboptimal to use a Euclidean distance classifier, which we commonly use in a lot of tasks. And applying a simple Mahalanobis distance-based classifier obtains state-of-the-art results on many and few-shot incremental learning benchmarks. And we also have more experiments in our paper where we use pre-trained models, pre-trained VIT models, which are trained on ImageNet, and we simply perform Mahalanobis distance-based classification, and it achieves quite good results. Yeah, thanks. Thanks for listening.
That was perfect timing. So the next speaker is Yanis Kalantidis. He received his PhD from the National Technical University of Athens in 2014. He was then research scientist at Yahoo Labs, when I had the pleasure to be his skip manager in San Francisco, and then Facebook research in Menlo Park. He returned to Europe and joined Naval Labs in 2020 in Grenoble, Paris, and he's another Barcelona lover. And he works in generalization, self-supervised learning, adaptation, and multimodal learning, among other things. Yanis?
Thank you, Ricardo. Let me also say that my love for Barcelona started in 2010 when I interned at Yahoo Research Barcelona. And I've been planning my return since then, and it finally happened. Hello, everyone. I'm Yanis. I'm going to talk about how we can harness the power of Gen AI models for learning visual representations, learning better visual representations. And we are living in the era of generative AI, at least in the computer vision side. These are models like DALL-E and Stable Diffusion that are trained on images, on billions of images, right? And can produce high-quality, realistic images given a textual prompt. For example, you can give it the term cat, and it produces very nice images of cats. Or you can give it the Mona Lisa and some sort of text, right? And then it changes the image with respect to the text. Okay, so in this talk, I will talk about how we can utilize these generative AI models for what I care most about in research is to learn computer vision models that generalize better to different downstream tasks and datasets or test time distribution shifts. And I'm going to present two ways. The first one is trying to answer a very provocative question, which is, okay, you saw all these amazing images. Do we still need real images for learning visual representations? So we are all familiar with the classic supervised learning framework. For example, at ImageNet, you have a data set. It's 1 million images and the classes. We use these images to learn a visual encoder, such as the output matches the correct label, right? Now, what we asked is, can ImageNet be replaced by synthetic images? So what we did is we took the classes, only the class names, right? We have these labels, which are the class names from ImageNet, and we passed them through Stable Diffusion, which is a very famous model. And we got a data set that we named ImageNet SD that you can imagine it's as big as ImageNet, exactly the same images per class, everything. So instead of using real images, we used these synthetic images to train our encoder. As I mentioned, you need to specify a textual prompt, right, to these models. The obvious textual prompt is use the class name. If you do this, you get a number of issues, right, from semantic errors to domain issues to a general lack of diversity in the generated images. In our work, we propose a number of ways to address these issues, but the two that work best was, first of all, to append some sort of description for its class, which we can get from WordNet, for example, for ImageNet. And the second thing that is kind of a little bit less intuitive is to tell the model to rely less on the text. And this way, the images are not as good as what you would get with the kind of more default parameters for Stable Diffusion, but they are far more diverse, right? So we're sacrificing a little bit of realism for diversity. And that helps a lot. I am not staying with results. This is very high level. The summary of results is this. When we care about the classes that we train, the classes that the model has seen during training only synthetic images from, we cannot be very close to the top models. RSB is a very good model for ImageNet. Still, the model does kind of 50%, which is admirable for a task of 1,000 classes, right? So it can do the task, but not as good as, of course, having images from the task. However, if we take the weights, the model that we learn in this way, and then transfer this to other data sets by transfer learning a classifier for its data set, we can see that we can outperform even the best of models trained on ImageNet. And even with using 1x synthetic images in the paper, we have other experiments where we're not limited. We don't need 1 million images. We can generate 100 million images, and results get better and better, as we saw. Okay, this was the first work that I want to show. What if we replaced ImageNet with synthetic data? We train a visual encoder only on synthetic images and propose solutions for addressing all the issues that arise. And in the end, we get decent but inferior performance on the training task, and on par or better performance than the top models for transfer learning. And this is transfer learning to very interesting tasks like iNaturalist and very fine-grained classification tasks. Okay, so that was the first work. The second way of using these generative AI models is to maybe improve robustness by simulating domain shifts that we might encounter, and we know which domain shifts that we encounter. Can we use these Gen AI models to simulate them? So for that, I'm going to introduce you very quickly the task of visual localization. In visual localization, we have a database of images, and we know their poses, right? We know where the images are taken from. And we have a new query image that we don't know the pose. So we want to estimate the pose of the query image with the database images. How do we do that? It's usually done in 2 steps. The first step is to do image retrieval, to find the closest images from the database to the query image, right? And this is where visual representations are very important, right? And the second step is to get the top of those images and do fancier pose estimation, like a dense matching, so that you predict the actual pose. But one of the main challenges in this task is variations that are caused for images taken at different times, different seasons, with snow, in different conditions of weather or season, right? And what we argue here is that generative AI is a very good fit to tackle these challenges. Firstly, because, at least for the task of visual localization, you can express them very easily and very clearly in plain text, right? And the second thing is that we're learning these models by contrastive learning, so we have matching pairs. So we argue that we can utilize the fact that we have pairs to automatically verify the synthetic data, which is a very important thing. So this is what we did. We created textual prompts again, now using the most common domain shifts that you can have for visual localization, and we didn't have to identify them. There are benchmarks for that for many years. And for example, here is an image from our training set. We took this image and these prompts that we see here at dawn, at dusk, at noon, and we passed them to Stable Diffusion, and we got images. For each original image, we have 11 more variants. We call them variants, right? We used Instruct Pix2Pix for this, a model that has been named a few times today. Then what we do is we train our model using both the original and the synthetic images. Again, I'm not going to stay into the technical details, but what I want to mention is that this is a generation process that is completely automated, right? We cannot inspect all of the images that are generated. And if you look at them, in many, many cases, they look very good. You see at night with rain, it even puts here like, how do you say, reflections, right? So they look very well. But at other times, they don't. So for example, in this image down here, most of the characteristics of the scene are destroyed, right? The door stays, but the rest is destroyed. So when we're creating these variants in an automatic way, we might be destroying what is needed for the task, right? Because we want to learn from pairs of the same location. To tackle that, we took into account the fact that we're training on matching pairs. And we made a hypothesis of geometry that the geometric consistency should more or less remain the same when we substitute one of the 2 images with a synthetic variant. So here we have the original matching pair. We substitute the first image of Montjuic, by the way, with at night with rain. And we measure the correspondences that you get from some sort of dense matching. And we measure what is the ratio of correspondences that remain after we replace the image, right? And we see that this is a metric that could be used in a number of ways. One is to simply filter out cases like this, right, where there is almost no correspondences remaining, so this is a pair that we don't want to use. Or in other ways, like for sampling, we want to sample hard pairs, so we can use pairs that pass the filtering but are hard like the one on top more, right, to get harder pairs. So again, I'm not going to stay with results, but we tested this against the state of the art on a number of benchmarks of visual localization, very common benchmarks, and we see that with our method that we call red for lock, you can get gains. Am I doing good? 1 minute? Okay. You can get very good gains, very good news. Okay, so let me summarize. I presented 2 ways of utilizing Gen AI for improving visual representations. But if we look at the bigger picture, what I presented is 2 things. One, the first method, which is a way of doing image-free distillation of a Gen AI model that could be behind an API. You don't even need to have access to the model. You distill this beast into a purely visual encoder of arbitrary architecture. You want to create a mobile net, you can create a mobile net. The second work I presented is essentially utilizing the domain-specific knowledge that is inside this Gen AI model as data augmentation. We're using the original plus these augmented images, right? And what we did further is to use task priors for automatic validation, which is very important, which takes me to this slide, which is things like what Ricardo was saying right before, that training with generative AI model-generated data should be used with a lot of caution because it inherits and amplifies all the biases that are present in the Gen AI model. And usually it's not us who create this Gen AI model. Probably we don't even know what this training data is. Verification is crucial, and this should be used with extreme caution. And this is created by ChatGPT, both the caption and both the cartoon and the caption. Okay, yeah. So I recently moved permanently here. This is only part of the work we do in my team at Naver. These are other things that I like. If you see anything you like, come chat with me, please. I would love to meet more people here. And this is research with amazing authors, Bülent and Diane were in both papers, and more people in others. And thank you. How did I do? Okay?
Perfect, thank you. Perfect timing. So the next speaker is Imanol Estepa. He's a first-year PhD student at Barcelona University in the AI and Biomedical Applications Research Group. And his research interests involve self-supervised representation learning and generative algorithms. And he will talk about symbiotic neighbor constructive learning via self-attention and redundancy reduction.
So it's on? Yeah. Okay. Okay, so thank you, Ricardo, for your kind introduction. In this talk, I will talk about our latest paper in self-supervised learning in collaboration that we did in collaboration with NVIDIA and that we presented in the last ICCB. So this presentation is divided in 5 parts. First, I will talk a little bit about the state of the art and self-supervised learning. Then I will move to All for One, or proposal, where we try to solve the problems that the state of the art has. I will prove with results that we are actually solving these kind of problems. Then we will talk about the main ablation of All for One. And finally, I will give some conclusions, such as the limitations and final remarks.
The microphone closer to the mouse because it's not over.
Yeah, now? Like this? Okay. So in self-supervised learning, we don't use any kind of annotations. So in order to train the model, we take an image, we create 2 different augmentations from the image, we pass them through an encoder to obtain the embedding, a projector, which is basically a multi-layer perceptron, and finally, we say that we contrast these embeddings or images. When we are contrasting images, basically what we are doing is pulling together these 2 embeddings in the latent space. So we are training the model in a way that it's able to generate similar embeddings for images that are actually similar. Of course, this approach was the most basic contrastive learning approach, and it has a lot of faults. For example, the diversity is not very high. So as we are using 2 augmentations from the same source image, the thing is that diversity is very, very, very low. So researchers from Google improved this, proposing NCLR, which replaces the branch by a KNN algorithm that actually extracts a nearest neighbor using one of the branches as a query. The superset is basically a queue of embeddings that keep storing the embeddings generated by the encoders during the training. So when you extract the neighbor, you can basically contrast the neighbor with the original image, and this way you are increasing the diversity. In fact, this approach managed to obtain the state of the art in contrastive learning. The problem is that this still has some flaws. We detected that sometimes an NCLR extracts a neighbor that is not correct or that could be potentially improved. The thing is that when you are pulling together in the feature space the embeddings of 2 images that should not be together in that space, you are actually confusing the model rather than training it. So other authors tried to improve this because this was a performance decrease in the overall framework. To solve this, other authors proposed an approach that uses multiple neighbors. When you use multiple neighbors, you are like diluting the problem because probably you are extracting better neighbors rather than the ones that are incorrect. The thing is that in order to make this work, you need to pull together with all the neighbors, so the loss computation happens multiple times. So this approach has an efficiency decrease. In our approach, what we try to solve is avoiding this kind of efficiency decrease while also increasing the accuracy of the internal KNN. So moving to our approach, how are we improving this? This is our framework. It's called All for One. I know that at first could seem to be like much more complex than the previous ones, but it's easy when you see that it's basically 3 different objectives that act together in a symbiotic way in order to obtain the performance that we want. The first one is the basic nearest neighbor contrastive learning. The second one, centered contrast, is our novel objective that uses in an efficient way multiple neighbors. And finally, we introduce a feature or redundancy objective in order to increase the independence of the features. So now we are going one by one. This is the centered contrast. This will look like the framework only for that objective. And going step by step, we obtain the image, pass them through the encoder to obtain the embedding, and then we extract 5 neighbors. These 5 neighbors then go to the transformer encoder. And in the transformer encoder, we use or we leverage the self-attention mechanisms in order to extract the relevant information from these neighbors and extract what we call the centroid, which is basically a single embedding that contains information from all the neighbors. For the second branch, of course, we are putting positional encoding so that the transformer can learn where is the first neighbor, the second neighbor, and the third neighbor. So for the second branch, we do the same, extract the embedding, but here we divide the path in 2. In one path, we extract the embeddings, and in the other one, we maintain the original embedding. Why are we doing that? We are doing that because we have to remember that the neighbors extracted are nothing more than a vector. So we need to ensure the gradient flowing from the objective towards the online encoder, which then is going to be used in the downstream tasks. In order to maintain that, we simply introduce it by replacing the last neighbor with a representation. Then we go to the transformer encoder and we obtain the centroids. Then these 2 centroids are pulled together in the feature space. In a more visual way, we can see this process as basically taking multiple neighbors, combining the relevant information from these neighbors thanks to self-attention, and then pulling these 2 outputs together. Right now, what we are doing there is, instead of contrasting a pair of neighbors, we are contrasting the information of 10 different neighbors on a single computation step. The loss would be very similar to a common contrastive learning loss. So, moving to the final objective, which is the feature and contrast, here we are not focusing on the neighbors. We are focusing on the actual embeddings. So, we take the embeddings, and when we reach this point, we start treating the embeddings not like individual embeddings, but as a batch of embeddings. Why are we doing this? We want to increase the independency of the features. So now we are focusing on the features and not on the whole image embeddings. To do that, we inspired in Barlow twins, so we create the feature cross-correlation matrix. And then what we want is to maximize the diagonal of this cross-correlation matrix while minimizing the off-diagonal elements. This way, we are ensuring that, for example, the first feature of the embedding is different to the second one, etc. So we are increasing the independency. To do that, we basically target the identity matrix, and we do so with .loss function. So, wrapping up, the all-for-one unified objective would be the addition of these 3 loss functions, of course, with regularization parameters in the case you want to tune for different datasets or different tasks. Now, moving to the main results, we prove, for example, on the most common self-supervised learning benchmark, which is the linear classification, we prove that all-for-one not only outperforms previous nearest neighbor state-of-the-art, but also the rest of the contrastive learning or pure contrastive learning state-of-the-art on 3 different datasets. Also, we tried that on different backbones, such as the BIT backbones, because for us it was important to prove that we are also performing good on transformers, and on bigger datasets, such as the complete ImageNet. Also, we tried different downstream tasks, such as the low data regimes, where we basically are training the model with the 1% of the images and 10% of the images of the dataset. And we did that for ImageNet 100 and complete ImageNet. So, regarding the ablation, as we are using a model that has different objectives, we were worried about how these objectives behave individually. So that's why we did this ablation. So, for our surprise, even if our best results are with all the components, one of our improvements or proposed improvements was to increase the accuracy of the internal KNN algorithm that extracts the images. Still, our centroid contrast objective manages to increase that accuracy the most. The thing is that this accuracy finally was not all of the problem. Other factors are also affecting the problem, so that's why when we introduce other objectives, such as the one that focuses on the independency of the features, it increases the overall performance, even though the accuracy of the internal KNN is not as high as we would like. So, going for the conclusions, we have to say that even if All for One is a very promising self-supervised learning algorithm focused on contrastive learning, it still has some limitations. The first one is the computation efficiency. We try to make our approach as efficient as possible, but of course we are introducing 3 different objectives. So of course our approach stays in the middle between NNCLR, which uses only one neighbor, and approaches such as MinShift, which uses multiple neighbors. So then we also know that we introduced 3 new hyperparameters to tune. All the experiments I showed were like we handpicked some hyperparameters that were good, and we tried them for all the datasets. But we know that if you want All for One or extract everything from All for One, you need to tune these parameters for the datasets. And finally, the transformer encoder parameters. What we did was picking, as we didn't want to increase the efficiency decrease, we used a very small transformer encoder just to leverage the self-attention mechanisms. But still, we had yet to try another self-attention mechanisms to see if the stability maintains or if it happens things like, for example, the model collapse. So, as final All for One remarks, we can say that we created a symbiotic approach that is introducing an objective that leverages the nearest neighbors. It's able to use multiple nearest neighbors without losing that much efficiency, and in fact it's using them in an intelligent way. For example, if one of the neighbors is not correct, the transformer will be able to identify it and then put less attention to that and increase the rest of them. Also, it integrates for the first time the feature contrast to a nearest neighbor contrastive algorithm, and it proves that even if it could be contradictory, it actually improves the overall framework accuracy. And finally, we prove that All for One generalizes better than the rest of the nearest neighbor state-of-the-art algorithm, and it generates more rich representations. So that marks the end of my presentation. Thank you all for listening.
Thank you. So the next speaker is Belén Alastruey. She's an incoming PhD student at Meta and PSL University in Paris, and she will work on interpretability of NLP models. Before, during her master at UPC, she worked on speech translation and recognition. And today, she will talk about multi-view frequency attention alternative to CNN front end for automatic speech recognition.
Hi. Okay. So yeah, hi everyone. I'm Belén Alastruey, and I'm gonna present today the work Multi-View Frequency Attention Alternative to CNN Frontends for Automatic Speech Recognition. This was some work I did last year during an internship at Amazon Alexa, and I did it together with my team Lucas Drew, Jan Heeman, and Simon Whistler. So I'm going to start with an introduction. So for those of you that are not so familiar with speech tasks, when we are working with speech, we can either work with a waveform or with a spectrogram. And in this case, we are going to focus on spectrograms. So what is a spectrogram? It's this thing we have here. It basically can look like an image, but in fact, it's not exactly an image. So it has two axes. In the x-axis, we have time. So for example, if we have a longer sentence, this axis would be also longer. And then we have the frequency axis, which is the y-axis, that contains like some information about the sound frequency. So the way we understand it, it's actually a matrix. It's not an image. And then we just colorize it using a heat map. And then for every column of the spectrogram, we have some information about how relevant are each frequency ranges for that specific time step. So that's how we understand the spectrogram. And when we want to use a transformer-based system with one of these input features, we have an issue because transformer systems were originally created to be used on text, not on speech. And there's some differences. The main one is that the sequence length of a spectrogram is usually way longer than what we would have on text. And also the information is way more sparse. Therefore, we need to somehow pre-process it before feeding it into the transformer model. And to do this, there is this CNN module that comes before the transformer-based system. This is called frontend. And this is the goal of the frontend is what I was just stating, pre-processing the spectrogram, making the sequence length shorter using a stride on the CNN, and also making the information less sparse. So as I was saying, the main idea of this work is that the spectrograms are not images, and that CNN networks were originally created to be used on images and not on spectrograms. So as I was saying, the main differences are that spectrograms have two different axes, and each of them has a specific meaning. And these axes also have a structure. In the case of time, it's like a left-to-right structure, and in the case of the frequency one, it's a top-to-bottom structure. So this means that, for example, if this was an image, and we had, for example, a flower, and it was located like in this part of the image, or we have another image where the flower is located in this part of the image. In both cases, we still have an image that contains a flower. So the model will have the same information. But in the case of a spectrogram, if we have a specific pattern here, or if this pattern is here, the information is completely different, and the content of what the person is saying changes completely. So then when we use CNNs to pre-process spectrograms, or a CNN together with a transformer-based system, the transformer-based system is going to pre-process the spectrogram time-wise, and it's going to, for example, extract interactions between the different tokens time-wise, but we are never extracting this information on the frequency axis. We are basically ignoring the fact that the frequency axis also has a structure. So then, we are ignoring the meaning of the frequency axis. We are never extracting information of the interaction between the different frequencies, and we are treating all the frequency bins in the same way. So this means that, for example, in this case, that the relevant frequency ranges are these ones here in the lower part of the spectrogram, and these ones maybe could be ignored. The model is forced to allocate compute equally for all of them, and it cannot ignore those frequency bins that are empty. So basically, in this project, what we propose is a new front end of what we call frequency attention, and the main idea is to use self-attention frequency-wise so that we can solve these problems that I was just mentioning. Let's dive deep into the front end that we propose. So basically, it's inspired, or the first step, it's inspired on the vision transformers. Vision transformers extract patches from an image, and what we do is we also extract patches from the spectrogram, but then we just focus on the patches that correspond to a specific time range. And what we do is, for those that are in the same time range, we embed them using an embedding layer, and then we compute self-attention between these different tokens. So using the output of this self-attention layer, we would build the first token of the input sequence that we will feed into the transformer. And then we would move the time window to the next time range, and we would again do the same thing, like use the embedding layer and then self-attention, and we will build the second token, and then with all these tokens, we put them together, and that's the input sequence that we will have for the transformer. And something important to note here is that this is also reducing the sequence length and therefore reducing the data sparsity, but it's doing it in a smarter way and more like speech specific, because it's using this information that we know that the frequency axis has a meaning. So to go a bit deeper into how the front end looks, what I just said was the most simple version we had, but we can actually stack multiple attention layers instead of having just one. And we also have a hyperparameter here, of course, which is the size of the paths that we choose. So in order to give the model some more variability, what we do is we extract patches of different sizes, and then we pre-process them independently with different attention layers. At the end, we merge the different, this is what we call views. We merge them together using a pooling layer to obtain just a final sequence that we use as the input of the transformer system. I'm going to show the results now. So for the experiments, we use a conformer transducer system. This has a conformer encoder, an LSTM prediction network, and an optional joint network. So in some of the experiments, we have it, and on other experiments, we don't. This model has 74 million parameters, and it's trained on Alexa data and also evaluated on Alexa data. So for the front end specifically, we are only modifying 3.3 million parameters out of the 74 million parameters that the model has. So we are really modifying our really small part of the image. In the beginning, we thought that it would even be impossible to see something like a clear improvement just by modifying such a small part of the model. But what we do see is that there's improvements in all of our experiments with different combinations of layers and views, and with and without the joint network. We always obtain positive results, but on one specific case, using our front end. And this is in terms of relative order error rate, we cannot show absolute results. So finally, we wanted to know if these performance improvements we were getting were just like a random thing that the model was using self-attention to extract random information, or if it was actually doing what we intended it to do. And in order to check this, we ran an attribution modeling study. So for this study, we took spectrograms of the test set, and we used spec augment. Spec augment is a strategy used for data augmentation on speech tasks. It basically consists on taking the spectrogram and blocking by adding noise some frequency ranges, so this one here, for example, and time ranges. So this is done randomly on the spectrograms on the training set. And in this case, we use it on inference just to have like a clear idea of what information is useless, and then the model should not be using it. So for example, if we focus on this time range here, it's clear that the model should be able to discard this information here because it's information that is blocked and only has noise. Then we use ALTI attribution method that has already been mentioned in previous presentations. With this method, basically what we can obtain is out of an attention layer, we can track how much each of the outputs is being influenced by each of the inputs. So in our case, we are focusing here on a model that has only one layer and one view for simplicity reasons. And what we see here, so these are the input patches, and these are the output patches. And we can see that the embedded patches. So the embeddings that correspond to patches that had the noise added by a spec augment are completely ignored by all the outputs of the self-attention layer. But instead, this one here, that is information dense, then this one is actually influencing many of the output tokens. So basically, after seeing this, we saw that the front end that we propose is actually doing something meaningful. It's not doing or extracting random patterns. But still, in this scenario, we are adding noise in a very fake way. And we also wanted to see if this was actually working on the case where there's just like a noisy background. So we had a second study where we just add Gaussian noise into some spectrograms, and we had different amounts of noises. And what we see is that in general, there is a trend that the more noise we add, the better our frontends work compared to the baseline frontend. Specifically for the model that has 2 layers and 2 views, it even reaches a 20% of relative order rate improvement with respect to the baseline. So finally, some conclusions. So in this work, we propose the frequency attention frontend to preprocess spectrograms and speeds in transformer-based systems. The goal of our frontend is preprocessing the spectrogram in a smarter way compared to the usual approach of using CNNs that were actually just proposed for images, but then it was extended to spectrograms. We have seen that our frontend outperforms the baseline in almost every case and different combinations of layers and views. And we have seen that it's not only outperforming the baseline, but it also is able to block noise, and it's more robust to noise addition, and it can even reach a 20% of relative order rate improvements against the baseline in noisy conditions. Thank you.
Thank you. So the last speaker is Guillem Simeon. He's a PhD student at the Computational Science Lab at University of Pompeu Fabra, and his research interests are geometric deep learning applied to physics and chemistry, and graph neural networks in general, and he will talk about Cartesian tensor representations for efficient learning of molecular potentials.
Just a second. Excuse me.
I think this image is yours, so you have the wrong screen.
No, yeah, I mean this is the background. I think it should be here, this place, no?
Yes, you have to
Here,
clone
this one.
Yes.
No?
Within this place, let me see. Mirror.
Or single display. Keep changes.
So
Great.
now the presentation is here?
Yeah.
Okay.
Okay, so yeah, I'm Guillem, and this is the only talk about molecules here in this symposium, and it is weird because I mean this field has gained a lot of momentum, and I will take profit of this and do a crash course of 10 minutes about machine learning interatomic potentials, and in the end I will explain a little bit my contribution. So basically we are interested in modeling molecules. So modeling means, or simulating molecular systems means finding the interactions and computing forces and making the system move. And this is important because of drugs and materials and even for fundamental knowledge. But this field has a trade-off, which is if I want a lot of physical detail, if I want a lot of fundamental physics, the cost of calculation, blows up, okay? So if I want to go into detail a lot, I can only perform the simulations for tens of atoms, and this is not enough for practical purposes. So this is when deep learning comes into play, and I can put a lot of effort into building some data set with a very accurate ground truth, and hopefully I can train a neural network in a supervised learning setting, and this network should be able to generalize, okay? Then, if I go back to this trade-off, so basically the neural network would be here in this place, so I can produce accurate predictions in just the inference time of the neural network. So basically, how do we represent molecules? Because of course, one hidden layer multilayer perceptron is not enough. We are given as inputs atomic numbers and positions always, so we are not assuming bonds or anything, it's just a point cloud with labeled points. And we build a proximity graph. This means like the atoms are connected if they are close enough, so within some cutoff radius. And we use then a graph neural network to predict the energies, okay? There is a very nice property in neural networks, which is differentiability, and what we can do is we can compute the gradient of the output with respect to the input positions, and we get a conservative force field, because this is the definition of a conservative force, okay? So these models, since they are dealing with physical systems, we need to take into account the symmetries and the equivariance. Symmetries basically refer to the fact that some quantities remain constant under some transformation, and equivariance means that some other quantities transform accordingly to this transformation in a very rough sense, okay? So if we consider translations, for example, if I translate the molecule, the energy should remain the same because the coordinate system is arbitrary, but the vectors got displaced. So vectors are these vectors on top of the atoms got displaced, so these are equivariant. I can also consider rotations. The energy of the molecule is constant so it doesn't change when I rotate because, again, the coordinate system is arbitrary, but if I have vector on top of the nodes, this should rotate accordingly. So I need an equivariant model to predict these vectors. Also, I can consider reflections, and the same would happen. So in terms of group theory, we are talking about the Euclidean group in 3 dimensions. Rotations are the special orthogonal group. If I include reflections, I have the orthogonal group. If I don't consider them, the special Euclidean group, and everything as a whole is the Euclidean group, okay? So I need to use a model that produces an invariant quantity under the Euclidean group and can produce equivariant higher order geometric objects under the Euclidean group also. So now fancy state-of-the-art spherical tensor models and irreducible representations. So the question is, what are irreducible representations? And then, so I went to Math Stack Exchange, and Yo-Yo gave me a one-liner, a very abstract definition. I go to Google Images and I get this thing, and so it's like, where are the arrows here? I don't understand. So if there are some mathematicians here, just close your eyes and don't listen. I will explain it like I understand it. So basically what we do when we deal with the orthogonal group, you can think of expanding a vector in terms of spherical harmonics. You know spherical harmonics, I suppose. A lot more people is familiar with that. So when I do this on a vector, what I'm getting is for spherical harmonics are labeled with some number L, and then I can get tuples. Okay, this is the non-mathematical thing. So I can get tuples of numbers, okay? So basically, if I consider L equals 0, I get a single number, which is a scalar. It does not rotate. It's this point there. If I go to L equals 1, I get three elements, and I can show that they rotate as a vector, but with a change of basis, and so on. So I can keep building up with independent, let's say that you can think of these tuples as independent and higher order geometric objects that rotate in their own particular way, okay? And it turns out that spherical, so state-of-the-art models use this kind of weird objects up to L equals 3 to achieve state-of-the-art accuracies and performances, okay? So basically we have this graph with this proximity graph, this graph neural network, and atomic features are these sets of these weird objects that transform under rotations. So this represented, introducing this kind of representations represented a breakthrough in terms of accuracy and also in terms of data efficiency. However, it's not trivial to deal with the representations, and mixing them and building new features from them is complicated, and this involves tensor products, and these are expensive, okay? So over time, a very rich landscape of models so appeared. From 2018, this paper, I mean, it came out 1 week ago, and I wish I have had it like 2 years ago. This is like a pedagogical introduction to these systems. Very prominent researchers, in fact, contributed to this. And basically, we can see different kinds of models, the invariant models, which use invariant features, because I want to predict an invariant, which is the energy, so it's fine. Cartesian equivariant vectors, models, which use Cartesian vectors, the arrows that we are familiar with, and spherical equivariant GNNs, which are the complicated stuff, okay? And so here is my contribution, okay? It's TensorNet. And so this was accepted in NeurIPS, it was presented last week, and basically we thought like, okay, so we will take it easy, and in a Cartesian basis, a rank 2 tensor is just a 3x3 matrix whose components change under rotations or reflections, okay? In the same way that I cannot think of a vector just an array of 3 numbers, so I have a reference system and it rotates and the components change, I can think of a rank 2 tensor in the Cartesian basis as a matrix. When I change the coordinate system, the entries change of the matrix, okay? So we propose this because we can achieve computational efficiency, better computational efficiency than spherical tensor models. So it turns out, and this is very interesting, and this is the connection with the spherical models, that any matrix, any tensor X, it's a 3x3 matrix, I can rewrite it or decompose it into these 3 different components, okay? It just, if you work out the expression on the right, you get the original tensor. So basically there is a connection with this decomposition and spherical tensors. So the first term does not rotate because the trace is an invariant, so I can relate it to L equals 0. The second term is a skew symmetric, it has 3 degrees of freedom and it can be shown to rotate as a vector. And the last part has 5 degrees of freedom, so basically I am doing the same as before as the spherical models, but in another representation. So in the paper we lay out the machinery needed to build an equivariant model from that. And basically the key aspects are that I can work with the full object or the components at will. I don't need to keep them all the time. And the key part is that I can substitute these expensive tensor products for cheaper 3x3 matrix products. This is the network. I mean, I won't go into detail with that. And we benchmarked it and we showed that it was more parameter efficient than spherical models and faster than, if you are interested in more deep benchmarks, go into the paper. And so, yeah, that's it. So I wanted to say just that there is life beyond large language models, also images, and that in Barcelona we have both powerful biotech and pharmas and powerful AI companies. So it is the right place to perform this kind of research. So thanks a lot, and this is my team, and this work couldn't have been possible without them. So yeah, that's it.
Thank you. So we have time only for one question. I'm sorry. So anyone has a question? Well, that simplifies the problem. I learned at least about 2 people in Europe that I didn't see. I guess I don't know what is the problem. Well, one thing I didn't know them. The second, too many people. So, okay, thank you. And now, I don't know.
Okay, so let's proceed with the closing of this Deep Learning Barcelona Symposium. So, yeah, just one moment. Yeah, sure. Okay, yeah. So first of all, I would like to acknowledge all the organization institutions and all the people from these institutions that have helped to us to organize this event. We want also to thanks all the sponsors like MetaAI as our platinum sponsor, and all these gold sponsors, silver sponsors, and bronze sponsors. So thanks everyone for the support for having this event happening. And I would like also to give some special thanks to some people from work that has helped to us for these logistics. And also with the team of volunteers that have been led by these 2 students from UPC. So thank you very much, all of you, for helping on this event. Okay.
Wow, you are still here, almost 7 p.m., so thank you for being here. Good evening, everyone. Bon vespre a tothom. Realment, en aquesta jornada de Deep Learning hem vist una magnífica demostració no només de la potència, sinó del potencial que pot tenir aquesta tecnologia, no només per la recerca, sinó i sobretot per al bé comú. I us ho dic jo, que sent metge de formació només he pogut surfejar una mica per tot el que heu pogut explicar i veure a través dels pòsters, però certament això el que pot arribar a evolucionar, o si voleu, revolucionar el camp de la salut és espectacular. Mireu, he fet un post a Twitter que deia, per cert, em dic Marta Aymeric, soc la directora de l'eHealth Center de la UOC, he fet un post que deia extraordinària jornada sobre Deep Learning fa sortir espurnes de les neurones, de tanta intel·ligència humana junta, i compartim generosament tot el coneixement que heu arribat a compartir. Ha estat realment un honor, un privilegi, certament, poder coorganitzar des de l'eHealth Center de la UOC aquest esdeveniment que han reunit, segur, alguns, o si no tots, els cervells més potents, més brillants en aquesta àrea. Moltíssimes gràcies. Us vull donar molt sincerament les gràcies a tots vosaltres per compartir tots aquests vostres coneixements, experiències, visions, tot el que he pogut fer avui. I realment és a través d'aquesta col·laboració i intercanvi que podem garantir que el deep learning no només avanci, sinó que sobretot ho faci per servir al bé comú. A l'eHealth Center seguim compromesos amb la promoció de la recerca en aquest camp i no només això, sinó també la formació dels professionals per al segle XXI, cap als reptes que imposa el segle XXI. He après moltíssim, he après molt sobre el deep learning, sobre com pot revolucionar, sobretot en el meu camp, com poden transformar dades crues realment en insights clínics reals, com poden arribar a fer deteccions primerenques, bé, i tot el que se m'ha escapat, que és molt més del que he après, però tot i així, com us deia, he vibrat. Això ha estat una oportunitat, aquesta jornada ha estat una oportunitat per compartir els darrers avenços i per inspirar-nos mútuament a tots entre nosaltres i per establir col·laboracions segur, estic ben convençuda, per descobriments futurs extraordinaris. I després d'aquesta jornada espero que tots ens emportem no només el coneixement adquirit, sinó sobretot aquest entusiasme i dedicació renovats. La recerca clarament és un viatge constant, ple d'oportunitats i de futurs descobriments, però també de molts desafiaments, i només amb la col·laboració, compartint, podem arribar a atènyer realment aquells resultats que la faci molt més potent i eficaç per al benestar de la societat. Us animo a seguir col·laborant, innovant, creant i fent recerca. I ara sí, ara esteu convidats la copa de cava que us teniu més que merescuda. Enjoy the dessert cava you have next door and see you next year. Bye bye.